In this comprehensive and beginner-friendly course, you'll learn all the tools that you need to become an advanced object-oriented programmer, writing clean code and maintainable software. You'll learn fundamental OOP concepts, the solid principles, all 23 Gang of 4 software design patterns, and more. Experienced developer Danny Adams created this course.
Welcome to Mastering Design Patterns and Solid Principles in C#. So let me first give you a quick introduction on what you will learn in this course and what you need to know before getting started. So the aim of this course is to teach you how to design maintainable and reusable object-oriented software. And this is achieved first of all by learning the object-oriented programming principles such as encapsulation, abstraction, inheritance, polymorphism and coupling. You'll also learn the 5 solid principles, which are the single responsibility principle, the open-closed principle, the list-off substitution principle, the interface segregation principle, and the dependency inversion principle. You'll also learn unified modeling language, which is a way to graphically represent your software systems. So you can model classes and objects and the relationships between those classes and objects in a graphical way, and you can do this before you actually code out a solution. And you'll also learn the main 23 design patterns from the Gang of 4 book. The Gang of 4 design patterns consists of 23 design patterns from the original book, Design Patterns, Elements of Reusable Object-Oriented Software, written by 4 guys in the 1990s. And these patterns can be grouped into 3 categories. So there are creational design patterns, which are the different ways to create objects. There are structural design patterns, which are the relationships between those objects. And there are behavioral design patterns, which are the interaction or communication between those objects. So upon completion of this course, you will understand all 23 Gang of 4 design patterns and where to and where not to apply them in real applications. And you'll also learn the solid principles and some more advanced object-oriented programming concepts. And these are all of the 23 design patterns from the Gang of 4 book that we will be covering in this course. So you can see that there are 5 creational design patterns, 7 structural design patterns, and 11 behavioral design patterns. So what are design patterns and why should you learn them? So design patterns are essential in software development for several reasons. And first of all, they help to promote and provide proven solutions to recurring problems in software design. So instead of reinventing the wheel, developers can leverage these patterns to solve common issues efficiently. For example, to implement an undo feature in an application, developers could reach for the Memento design pattern. Design patterns establish a common language for developers to communicate efficiently and effectively about software designs, and this common vocabulary enhances collaboration and understanding among team members. Design patterns also promote scalable designs by providing flexible and adaptable solutions. They allow systems to evolve over time without extensive rework or architectural overhaul. And using design patterns often results in more maintainable code, as patterns encapsulate design decisions and promote modular, loosely coupled architectures, making it easier to understand, modify, and extend code bases. And some design patterns can help to improve performance by optimizing resource usage, reducing overhead, or facilitating efficient algorithms. Design patterns serve as a form of documentation for software designs, so by employing well-known patterns, developers can convey design intent more effectively, making code bases easier to understand for both current and future contributors. Design patterns embody best practices and principles of software design. They encapsulate years of collective knowledge and experience, guiding developers towards solutions that are more robust, reliable, and maintainable. And many design patterns are agnostic of programming languages or domains, so they can be used across different programming languages essentially. And they can be applied across different technologies and industries, making them valuable tools for developers working in diverse environments. So overall, design patterns facilitate the creation of high quality, maintainable software systems by providing reusable solutions to common design problems and promoting best practices in software development. And just as a note, don't worry too much if you don't quite understand everything I've said so far. And as everything will become much more clear as we implement and discuss each of the design patterns and object-oriented programming principles during the course. For example, many of you right now won't understand the difference between extending a code base versus modifying a code base, and all of these things will be revealed during the course. So here are some things that you should understand before starting this course. So this course is for developers that have at least a very basic knowledge of object-oriented programming and want to learn design patterns to become better, more complete developers. So here are some things that you should understand before starting this course. So you should understand what classes are. You should understand how to create objects from classes. Access modifiers such as public, private and protected, class properties or fields, and class methods. So as you can see, you just need to understand the very basics of object-oriented programming to find value in this course. Any other object-oriented programming concepts such as abstract classes, polymorphism, encapsulation will be fully explained in this course. And of course you will learn the very important object-oriented programming solid principles. So all the examples in this course are in C#, so it will be helpful if you understood the basic syntax of C#, as I won't be explaining the basic syntax. However, there are plenty of free and great videos on YouTube to help you get started with C# in very little time. So a little bit about me. I am currently a freelance software developer that builds full stack web applications, Shopify apps, mobile apps, WordPress plugins and themes. And I'm also a technical writer that enjoys writing technical blog posts, books, and making videos and courses. So here are some links where you can find me. So I have a YouTube channel, I have a Twitter account, I sell some products such as posters and PDFs on Gumroad. I have a freeCodeCamp blog where I write posts for freeCodeCamp, and I also have a blog on Dev2. There is also a full book version of this course available, and it includes everything that is covered in this video course. And having the book can help to make revision of these topics much easier, as you can quickly look up certain topics, principles and concepts, skim through and remind yourself of what we covered in this video, helping these topics to stick in your head. And if you're a heavy note taker like me, then it will also save you a lot of time, as everything we cover in this video will be written down here for you. So if this book sounds like it would be helpful to you to better learn these concepts, then you can get the book from Amazon in Kindle, ebook and physical print format. And there's also a PDF version available from Gumroad, and there should be links to those down in the description below. So for every design pattern or solid principle or object-oriented programming principle that we cover in this course, we will go over an example or two. And usually each example will include a bad example which violates a certain principle, and then we have a good example where we usually refactor the bad example to satisfy the principle that we are covering. And all code examples for this course can be found at this GitHub repo. Okay, so I'm now going to show you how you can set up your computer so that you can follow along with the examples in this course. So this course is all in C#, so we need to set up a sort of C# environment. So for me, I'm going to use Visual Studio Code as the text editor, and I've provided a link to a guide here to get you started and set up. So let's have a look at this guide. So if you click this link, it will take you through to this Getting Started with C# in VS Code guide. And it tells you everything that you need to download and then everything that you need to do to create a new C# application or project. So first of all, you need to download Visual Studio Code if you don't already have it. So you can download it here. And then you need to download the C# DevKit extension for VS Code. So you can download that by clicking this link, and you can install the C# DevKit extension. You can also do it from VS Code directly, so if you come into the extensions sort of tab, and then you can search for C# DevKit, and then you can install. I've already got it installed, so I don't need to do that. And the next thing you need to do is to download the .NET Software Development Kit, and you can download that from Microsoft, so you can download that here. So that's everything that you should need to get started developing with C#. So once you've done that, you can then create a new C# application. So if we come into Visual Studio Code here, we've just got a blank, no folders open. So what we can do is let's create a new C# project using the extension, the C# Dev Kit extension that we installed earlier. So you can press Shift Command P to open up the command palette, and then we can see we have some options here. So you can type in .NET : and then new project, and you can see you can click .NET new project, and then we want to select console app because we're going to create a very simple console app for all of our examples in this course, and that's just an app where we can basically log things to the console. So select console app, and then you need somewhere to actually store this project. So I'm just going to store it on my desktop for now. So I'm going to open that, and then I need to name the project. I'm just going to call it test because I've already created the actual project that we're going to use. You can call this something like design patterns in C#, tutorials or course or something like that, whatever you want. And then we just click create project, and you can see it's created this project in my desktop folder. So if we come to the File Explorer now and we go into our program.cs file, we can see that we have console.writeline hello world, and we can just run this file or this application, and we can see that we get hello world logged to the console. So that is how you set up with Visual Studio Code for .NET, and this is how I will be doing all of the examples in this course. But just as a note, feel free to use whatever text editor or setup that you want if you already have something set up for C#. Before we start learning any design patterns, it's important that you understand some fundamental object-oriented programming principles. So here are some concepts that you'll understand by completing this next section of the course. So you will understand encapsulation, abstraction, inheritance, polymorphism, coupling, and composition. So let's get started. So the first object-oriented programming principle that we're going to take a look at is encapsulation, which is a fundamental principle of object-oriented programming that involves bundling the data or attributes or fields and the methods or behaviors that operate on that data into a single unit called a class. And encapsulation helps in hiding the internal implementation details of a class by only exposing the necessary functionalities to the outside world. So if that doesn't make too much sense, don't worry, because we're now going to go through a simple example demonstrating encapsulation, and we'll first go through a bad example with no encapsulation, and then we'll refactor that example to use encapsulation. So first of all, we're going to create a new class called bad bank account. And this is going to have a single field called balance, and this is a public field. And then inside of our program.cs field, so that this is going to be a class, our program class is going to use or be a client of this bad bank account class. So we're going to say bad bank account, and we'll call this bad account equals new bad bank account, and we're going to set the balance equal to 100. So initially the balance is going to be 100, and let's just log that to the console, and let's run our program to make sure everything's working correctly, and we can see we get 100 logged to the console. So the issue with this solution is that because this is a public field, all clients, also all classes that use this class, can just directly change this balance field to whatever value they want. So if I change this to -50 and then run the program, we should get no issues. Okay. Now this is actually a problem, because let's just say that in our program bank accounts should not balances should not be allowed to be negative. Okay, so this is actually violating our program's logic. So in all of our clients, because we can just directly access this field, in all of our clients we then have to provide some sort of conditional statement. So we'd have to say, like, if the amount that we want to set the balance to is negative, then we can maybe throw some error or display the user some issue. And we wouldn't want to have to do this inside of every single client that uses bad bank accounts. Okay, so you can see that we have some issues here because we can set this to whatever we want because this is public. So let's now use encapsulation to solve this problem. So let's create a bank account class. And we're actually now going to make the balance field private so that it can't be accessed outside of this class. So let's actually create a constructor now so that we can set the initial balance of the bank account. And we'll say decimal balance. And what we're going to do is we're going to provide a method now called deposit, and then we can set the balance in here. Okay, so let's create a method called deposit. And we pass this an amount that we want to deposit. And then here what we can do is we can check that if the amount that we're trying to deposit is negative, then we can throw an error, because it doesn't make any sense to deposit a negative amount of money. You don't deposit minus $50 into a bank account. You only deposit positive numbers. So we can say if amount is less than or equal to 0, then we're going to throw a new argument exception, and we will say that deposit amount must be positive. So deposit amount must be positive. Okay, so that is preventing now users of this class from depositing negative amounts of money, and that actually solves our issue of actually having a negative balance, because we now can't have a negative balance when we deposit money. Okay, so what we can do now is just add the amount onto the balance. So we can say balance, this.balance plus equals the amount. So let's also create a method for withdrawing money from the bank account. So currently we can deposit money, but we also need to get money from the account. So let's create a withdraw method. So we can say public void withdraw, and then we need to provide an amount that we want to withdraw. Now again, we need to make sure that balance can't be negative, and so we need to make sure we don't try to withdraw an amount greater than our balance. So first of all, we can check if the amount is less than 0. So we can't withdraw a negative amount because that doesn't make any sense. So we're going to say if amount is less than or equal to 0, then we're going to throw a new argument exception. And we'll say withdrawal amount must be positive. So we'll say withdrawal amount must be positive. Okay. And we also need to check to see if the amount that we're trying to withdraw is greater than the amount that we have in the account, because that shouldn't be possible. So we're going to say if amount is greater than the balance, then we can throw invalid operation exception, and we can say insufficient funds. Okay. Otherwise, if we get down to here, then we can just subtract the amount from the balance. So we can say this.balance minus equals the amount. Okay, and it'd also be nice to, for the user to be able to actually see what their balance is. So let's provide a getter method. So a getter method is just a method that essentially allows the user to see a private, the value of a private field. So we can say public decimal, and then by convention what you do is you just basically prefix get onto the name of the field that we're trying to get. So we say get balance, and we're just going to return the balance. Okay, so now let's take a look at how we would use this new bank account class, where we have encapsulated the logic and the fields within this class and not made them available publicly to all users of this class. So we're going to, first of all, let's just remove everything from in here, and we're going to say bank account, and bank account equals new bank account, and we need to provide an initial amount, so we'll say 100. Okay, and let's actually log the balance to make sure that that has worked correctly. So we can get balance, and let's deposit an amount. So let's just say bank account dot deposit, and we'll deposit, say, $50, and we'll log the balance there. So let's put that up there, and then let's actually withdraw some money. So withdraw, let's withdraw 100, and then log to the console the balance. So that should be bank account. Okay, so let's make sure that this is all working correctly. So initially the balance should be 100. So we can see here that's correct. Then we deposit 50, so we now have 150. Then we take out 100, and we now have 50. So let's check if we actually try to initialize the account with a negative amount of money. So we should get an exception thrown. It just shouldn't allow us to do that. And as you can see, we get an exception. The deposit amount must be positive. So that's working correctly. What if we try to withdraw more than we have in the account? So here we have 150 in the account. Let's try to withdraw $200. And we should get an exception because we're trying to withdraw more than we have in the account, and the withdrawal amount must be positive. So you can see here we're trying to withdraw a negative amount. I wanted to actually withdraw a positive amount there, so let's just check that. And it says, it tells us that we have insufficient funds. So that is all working perfectly. So in this example, the bank account class encapsulates the account data, so the balance, and all the related methods, so deposit and withdraw, into a single unit. This bank account class is the sort of single unit, and the data members, the balance, are marked as private, encapsulating them within the class and preventing direct access from outside of the class. And getter methods, so get balance, are used to provide controlled access to the private data member, the balance field in this case. And methods deposit and withdraw are used to manipulate balance, ensuring that operations are performed safely and according to the business rules. So we can see here we have checks to make sure that nothing incorrect, so the sort of program logic can't actually be violated from outside of the class. And the main method, or inside of this program.cs file, we are demonstrating how to create an instance of bank account and interact with its properties and methods without needing to know the internal implementation details. So we can see that the user, or so this program class here, the user of the bank account class, can't directly access the balance field as it's marked as private. So the data is encapsulated within the class. Methods dictate the rules for how this data can be accessed and modified, ensuring that our program's correct rules and logic can't be violated by users or consumers of the bank account class. For example, it's no longer possible to withdraw more money than is in the account. And encapsulation of logic inside of the methods in bank accounts also means that users don't need to worry about the implementation details when we're interacting with a bank account object. For example, the user doesn't have to worry about the logic involved in withdrawing money. They can just call the withdraw method, and the implementation details of withdrawing money are hidden from the client and encapsulated. And if the user tries to do something stupid like deposit a negative amount of money, then the program will throw an error and the user will be notified. And encapsulation of logic within methods in bank accounts allows users to interact with bank account objects without needing to know or understand the internal implementation details of how withdrawals or deposits or other operations are carried out. Users of the bank account class can interact with it using simple intuitive methods like withdraw and deposit without needing to understand the complex logic behind these operations. So encapsulation abstracts away the complexity of the implementation details, allowing users to focus on the higher level functionality provided by the bank account class. So users only need to know the public interface of the bank account class, in other words, the public methods or properties, to use it effectively, while the internal implementation details remain hidden. So in summary, encapsulation allows for a clear separation between the public interface and the internal implementation of a class, providing users with a simplified and intuitive way to interact with objects while hiding the complexity of how those interactions are handled internally. Abstraction is an object-oriented programming principle that is used to reduce complexity by hiding the unnecessary details of a class to a user of that class. So a good example of this is that when you press a button on a TV remote, you don't have to worry about or interact directly with the internal circuit board. So for example, within a remote, there will be electrical impulses firing through a circuit board, and then some electromagnetic waves will come out of the remote and be received by the television. But you don't really need to understand any of that. If you want to change channel to channel 2, you just have to press the 2 and it'll change directly. It'll change to channel 2 and you don't have to worry about any of the complex details of how that happened. All of those details are abstracted away. So I've created an email service class here to demonstrate abstraction. So currently this class has no abstraction really. We have just a load of public methods that are available to any user of this email service class. So if we want to send an email, we create an email service object, and then we have to connect to the email server, authenticate, send the email. Then the user has to remember to also disconnect from the server once the email has been sent, or once we've finished, sending any emails or doing what we're doing with this email service class. So the issue with this solution is that all users of this class have to follow all of these steps in a specific order. And for example, if we add another method to the email service class, such as log some information, then all of the users of this class would then have to add an extra step, such as log. Okay, and we couldn't just change this in one place. We would have to edit all of our classes that were sending an email. So a better solution to this would be to make these methods private and only expose one method to users of this class, and that would be the send email method. So what we can do here is we can call all the methods, all the steps that are involved in sending an email, we can call them in the send email method, and then we can see we have an error now because these methods are no longer available. They are now private methods. So we only now have to call the send mail method. So if I just show you this, you can see that the only method available now is send email. And if we run the program, we get the exact same thing as we got before. But now users of the email service class now don't have to worry about the internal implementation details involved in sending an email. All the complexity has been abstracted away and encapsulated within this email service class. So now the user can send emails without having to know any of the details or any of the complexity. And without abstraction, you saw that the user had more decisions to make, because whenever we looked at the methods on this email service object, there was 3 more methods to choose from. There was connect, authenticate, or disconnect. And so the user then has more decisions to make. Whereas this, it's very simple. We can just call send email. It's very obvious how to send an email. So without abstraction, the user needs to know more information and understand the internal logic involved in sending an email. And importantly, if any of those private methods are changed, e.g., for example, they take another parameter. So let's say when connecting, we added another parameter such as, I don't know, a URL to an email server. Then all classes using the email service would then have to change. They would all have to add this extra parameter, and all those classes would have to be modified, and you risk adding bugs into previously working code. Whereas with this, with this solution where these methods are all kept abstracted away, we could just add the parameter to one method. We would only have to change the send email and say connect method. Inheritance involves creating new classes based on existing classes. So the new classes that we create are often called subclasses or derived classes, and they are based on the existing classes, which are known as superclasses or base classes. So a subclass inherits properties and behaviors from their superclass and can also add new features or override existing ones. Inheritance is often described in terms of an is-a relationship. For example, we may have a shape class, which could be a base class or a superclass, and a shape class could have subclasses which inherit from shape. So, and that relationship would be represented by inheritance pretty good, because for example, a circle is a shape. Okay, so shape could inherit. A circle could inherit a shape. So here's an example where a car or a bike class can inherit from a parent vehicle class. So we have a vehicle class here which has some properties, some C# properties for the brand of the vehicle, the model of the vehicle, the year of the vehicle, and some methods that can start or stop the vehicle. So all vehicles, whether they are cars, bikes, planes or boats, will have all of these kinds of information. So what we could do is create a car class and have all of these properties and methods in car class. So we could literally copy and paste them all in here, like so. And then we also have a bike class, and we could have, again, repeat everything and have the brand, model, year, start, stop methods all within bike. But we're going to have to repeat ourselves a lot with this. And if, for example, vehicles, we need some extra functionality for a vehicle that all vehicles have, then every single vehicle we would have to add a new method. And also if we changed, for example, the way we start a vehicle, then we would have to change that method in all of the vehicle classes rather than just in one place. So what we can do is we can use inheritance. We can see here that car is inheriting vehicle. So the way that you inherit a class in C# is by using this colon. So car inherits vehicle. And we can also make bike inherit vehicle as well. So now in our program.cs file, we are going to say we'll create a car object. So we'll say car equals new car, and that automatically gets imported. And we can say car. Let's first of all actually have a look at the shared properties. So bikes and cars now, because they both inherit vehicle, have access to all of these properties or methods within the class. So let's have a look at the shared stuff first. So we can say car.brand. Sorry, that should be lowercase. And we can say car.start and car.stop. And then also We can see that cars also have their own properties which are only available or only accessible on car objects, such as the number of doors, for example, because bikes don't have doors, so we cannot put that onto the vehicle class because bikes don't have doors, so that shouldn't be available on a bike class or a bike object. So then we can say the unique properties and methods to a car, such as the number of doors. So now when we run this program, we can see the vehicle is starting and the vehicle is stopping. So these are the inherited methods shared by bike and car or whatever vehicle we have, and we also have some unique methods which are individual or unique to the individual type of vehicle. So now if we change this to a bike object, let's just change it to a bike object, you can see we get an error because number of doors doesn't exist on bike, but these start and stop methods and also the brand are all available because they are inherited from this vehicle class. So one of the advantages of using inheritance is that it means that we don't have to write the commonly used fields and methods for every single type of vehicle. And also, if we want to change the start method, then we only have to change it in one place because we aren't writing the start method onto every single type of vehicle. It's just one method inside of the vehicle class, meaning that we only have to change it in one place. And another great thing about inheritance is that it allows for another very important object-oriented programming principle, which we're going to look at next, called polymorphism. Polymorphism is the ability of an object to take many forms. So poly means many and morph meaning forms. So I've got an example here where we have a parent vehicle class which stores the brand, model, year and has a couple of methods for starting and stopping a vehicle. And these are virtual methods, which in C# means that these methods can be overwrit by any subclasses or child classes. And we have a car child class which extends vehicle, meaning that it inherits these properties and methods from vehicle. And then what we're doing is we are overriding these start and stop methods in car because, for example, starting a car involves some different logic than, say, starting a motorcycle or starting a plane. So a motorcycle is also a vehicle and it overrides these start and stop methods, but there are different steps in starting a motorcycle, so we have to implement these methods inside of the motorcycle class. So you might be wondering, why do we bother extending vehicle with these start and stop methods when we're having to implement them or specify them within each individual type of vehicle? It doesn't really make sense. And the reason for this is because it allows us to use polymorphism, which essentially allows us to treat these objects in the same way. So let me demonstrate what I mean by what this means. So if we create a list of any object, so this can be any object in this list of vehicles, and then we just add some vehicles to this list. So we add a new car object and we give it a brand of Toyota, a model of Camry, year 2020, and then we add a new motorcycle. So let's just call this Harley Davidson. And let's give it a model of, let's see, Sportster. And let's give it a year of 2021. Okay, so now we have a list with two of these vehicle classes, but in this list we can have any objects. So we can add, a banana or a person. Even though we've called it vehicles, we can actually add anything to this list because it's just a list of objects. So let's say we want to perform some sort of vehicle inspection. So what we need to do is we need to loop through this list of objects. So we can say var vehicle in vehicles, And let's say we want to start the vehicle. So we want to test starting the vehicle. So we can call vehicle.start. But the start method isn't here, which is unexpected because these are all vehicles so far. We were expecting to be able to call this start method, but our program has no idea. It's not guaranteed that a start method exists on one of these objects because they're just any objects. They're not vehicles. So what we would have to actually do is we'd have to actually check what the type of this object is before we can call any methods. So for example, we would have to do this. If vehicle is of type car, we then have to cast this object into a car object. Okay, so we can say var car equals car vehicle. So we're casting it from a generic object into a object of type car, and now it's a car object. Now we know that it's a car object. We can then call car.start. Okay, but then if we want to also test, we also need to account for testing motorcycles and planes. So we then have to do another else if statement to say check if the vehicle is a motorcycle, for example. And if it is, we can say we can cast the object into a object of type motorcycle. And once we know it's a motorcycle object, we can call the start method. And then we would also have to do the same for plane. And the issue with this is, first of all, it's hard to read. We have to have a lot of if and else if conditional statements. And also, if we add more vehicles to our program, such as a boat, for example, then we also have to keep on modifying our client classes. The classes that are using these vehicle objects have to be modified, which is not good. We don't want to have to keep on modifying our code every time we add a vehicle. We just want to be able to add a vehicle and not have to keep on modifying our vehicle inspection logic. Okay, so how do we fix this? So first of all, rather than having a list of objects, we know that all of the objects in this list are of type vehicle because they're all extending the vehicle class. So we can say that this is a list of vehicle objects. And now when we loop through this list of vehicles, we know, because they're of type vehicle, and we know that all vehicles have this start and stop method, start and stop methods, we can simply just call vehicle.start. And that's it. It's that simple. So we've actually used polymorphism here because we're actually treating different types of objects as the same. We're just treating them as vehicles. Okay, we're not worrying about whether it's a car or a motorcycle or a plane. Because they're all vehicle classes which have these methods, we can just call the method directly and treat them all the same. Okay, so in this example, let's just sum things up. We have a list of vehicles containing instances of both car and motorcycle. And then we iterate through each vehicle in the list and perform a general inspection. So we're just starting the vehicle. That's just our simple inspection. And despite the vehicles being of different types, polymorphism allows us to treat them all as instances of the base vehicle class. The specific implementations of the start and stop methods for each vehicle type are invoked dynamically at runtime based on the actual type of each vehicle. And because the list can only contain objects that extend the vehicle class, we know that every object will share some common fields and methods, meaning that we can safely call them within the client code without having to worry about whether each specific vehicle has these fields or methods. So this demonstrates how polymorphism enables code to be written in a more generic and flexible manner, allowing for easy extension and maintenance of new types of vehicles as they are added to the system. So if we add another type of vehicle, we don't have to say else if vehicle is type of boat and then cast it to a boat and then call the start method, whatever the start method may be called on that boat, because we have no reason to actually call it start. We could call it start boat, and then we could call start boat. It doesn't even have to be called start if we don't extend the vehicle class. The vehicle class ensures that all vehicles have this start method, and we can treat all vehicles the same within our client code. Coupling refers to the degree of dependency between different classes. So high coupling means that classes are tightly interconnected, making it difficult to modify or maintain them independently, whereas low coupling indicates loose connections between classes, allowing for greater flexibility and ease of modification. If classes are tightly coupled, then modifying one class could break the other, which could break the whole program. So first of all, let's consider an example of where we have high coupling, and then we will improve this example by reducing the coupling. So let's first of all create a bad example. So we're going to create a email sender class, and within this email sender class we're going to have a method called send email, which takes a string message, and we're going to have some email sending logic such as connecting to the email server, authenticating, all that kind of stuff, but we're not going to worry about that. We're just going to log sending email, and then we're just going to concatenate the message. Okay, so then let's say that we have some sort of e-commerce application where a user can place orders. They can order certain items, and once they've ordered an item, they get an email to say that the order was placed successfully. So let's create this order class, and let's give it a method called place order, and then we have some place order logics, and this kind of logic will be inserting the order into the database, reducing the stock quantity of items that have been ordered, processing payment, all that kind of stuff, but we don't need to worry about that. And then once all that's been done, we can send a email to the user to say that the order has been placed successfully, reassuring the user. So we can send email and give them a message to say order placed successfully. Okay, then let's simulate a user actually placing an order. So we can say order equals new order, and we can say order dot place order. Okay, so let's run this program. As we can see, the order is placed successfully, and the user gets an email to say that the order is placed successfully. So this all looks okay, but in this example, the order class is tightly coupled to the email sender class because it directly creates an instance of the email sender class. Okay, we're calling the new keyword. This means that we're directly creating an instance of email sender, which makes the order class dependent on the implementation details of email sender. And any changes to the email sender class may require modifications to the order class. Okay, so if we make a change to email sender, we may have to also make modifications to the order class. Okay, and it just means that we may, if we change one class and also have to change another class, it means that we are risking introducing bugs into this class. We'd rather not have to modify this class if we change the implementation details of email sender. It should just be all contained within here. It shouldn't affect the order class. So let's now discuss how we can reduce the coupling. So to reduce coupling, we can introduce an abstraction or an interface between the order class and the email sender class. And this allows the order class to interact with the email sender class through an abstraction or an interface, making it easier to replace or modify the implementation of email sender without affecting the order class. Okay, so if that doesn't make too much sense, we'll go through an example now, and it should make more sense. So let's create an interface called iNotification service, and all classes that implement this interface should have a send notification method, which takes a message string. So now what we can do is we can go into email sender, and we can say that email sender implements notification service. Okay, and what we can do is if you press command and then dot, you can implement the interface. On Windows, I'm guessing that's control and dot. And what we can do is we can copy and paste this send email logic into this send notification method, and we can get rid of send email. Okay, now in our order class, we can see that we have an issue now because the send email class doesn't exist. So what we could do is call send notification, but you can see that this order class is still tightly coupled to this email sender. And the problem with this is it's not very flexible, because, for example, let's say that the user wants to be sent a text message once the order has been placed successfully. There's no way of doing this because the email sender is just hard coded into this placeholder method. There's no way of switching out the way that we send a notification to the user. So let's actually make that possible. So what we can do is we can add a private field, private read-only field of type iNotification service, and we'll call this notification service. We'll create a constructor. So whenever we create a new order object, we have to pass in the notification service that we want to use, and we can set that notification service field here. And then what we can do in the place order method, rather than having this email sender, we can just call notification service dot send notification. And of course, what we can do here is we can pass this a message of order placed successfully. Okay, so let's have a look how this now works. So we have an error here because we actually need to pass a notification service to any order objects when we are creating order objects. So we can pass an email sender and then place the order. And as you can see, we are sending email order placed successfully. Okay, so let's say that the user wants to have a notification by text message, so SMS. So we can create an SMS sender, and then what we will do, this needs to implement the iNotification service interface. We can implement the method, and what we can do is we can just say SMS message, and then we can just concatenate on the message. So now what we can do, if the user wants to be notified by SMS, we can just say new SMS sender. Now the reason we can switch out what kind of notification service we use is because in the order class we're saying that we have to pass any type of notification service, and because we now have this abstraction, this interface, SMS sender and the email sender are both of type or implement the notification service. So we can treat them in the same way here. We can pass either an SMS sender or we can pass an email sender. So now if we place the order, you can see here we're sending an email. We're now passing an SMS sender. And let's see what happens. We get an SMS message. Okay, and we were able to switch out this SMS. We were able to switch the type of notification service that we used without having to modify this order class. So in this improved example, we have decoupled the order class from the specific implementation of the notification service, allowing different implementations, for example, email sender or SMS notifier, SMS sender, whatever, to be easily substituted without modifying the order class. And this reduces coupling and improves the flexibility and maintainability of the code base. Composition involves creating complex objects by combining simple objects or components. In composition, objects are assembled together to form larger structures, with each component object maintaining its own state and behavior. Composition is often described in terms of a has-a relationship. So let's go through an example to show you what composition looks like. So first of all, we have a load of sort of items or parts that make up a car. For example, a car has a chassis, and here we just have a method called support. So it just says chassis is supporting the car. We have an engine with a start method. We have seats with a sit method, and we have some wheels with a rotate method. Okay, so these are all the parts that a car is composed of. So now if we have a look in the car class, we can see that we have a car class here that uses composition. It is essentially composed of these different parts. And I mentioned earlier that composition is often described in terms of a has-a relationship. Well, we can see here that a car has an engine, a car has wheels, a car has a chassis. So you can see this is a good example of a composition relationship. And in this example, the car class uses composition to assemble its components. The car class is composed of all of these items, where each component, for example the engine or the wheels, is a separate class responsible for its own functionality. And the car class contains instances of these component classes and delegates tasks to them. And you can see here in this start car method, you can see that this car class is delegating work to these component classes. It's saying engine start, wheels rotate, chassis support, seat sit. It's delegating that work to those classes rather than doing that kind of work itself. And so to start a car, all we have to do is create a car object. And I believe it is this one. And we run the start car method, and we run this this program, and we can see that all of this work has been delegated to each of these component classes. So as you can see, in summary, we have a car class which is composed of multiple components, and it delegates work to each of these components. So let's now take a look at the differences between composition and inheritance, and when you should probably use composition and when you should probably use inheritance. So let's first have a look at when you should use composition. So you should use composition when you need more flexibility in constructing objects by assembling smaller reusable components. So a good example for this is a car class which is built from multiple components or multiple smaller objects, such as an engine, wheels, chassis, its seats, its dashboard, GPS, all these kind of things a car can be constructed from or composed from. So a composition provides us with good flexibility in constructing objects from smaller reusable components. You should also reach for composition when there is no clear is-at relationship between classes, and a has-a relationship is more appropriate. So for example, a car is a engine doesn't make any sense, whereas a circle is a shape does make sense. So maybe inheritance would be an okay solution there, whereas with the car and the engine, a car has an engine, so composition would make more sense. So that seems to be a good solution to start with. And you should also use composition when you want to avoid the limitations of inheritance, such as tight coupling and also the fragile base class problem. And this is a problem which we are going to look into shortly. But for now, let's take a look at the advantages of inheritance and when you should probably reach for inheritance. So you should reach for inheritance when there is a clear is-a relationship between classes, and subclass objects can be treated as instances of their superclass. So for example, a circle or a square can be treated as shapes, for example, which is their superclass. Inheritance can also be used when you want to promote code reuse by inheriting properties and behaviors from existing classes. And inheritance can be used also when you want to leverage polymorphism to allow objects of different subclasses to be treated uniformly through their common superclass interface. So the fragile base class problem is a software design issue that arises in object-oriented programming when changes made to a base class can inadvertently break the functionality of derived classes. This problem occurs due to the tight coupling between base and derived classes in inheritance hierarchies. So let's now have a look at what are the issues caused by the fragile base class problem, and then we'll look into why we should probably use, generally you should probably reach for composition over inheritance for most of your solutions. So let's first of all consider a simple example. So let's say we have a shape class, which is our base class, and let's say we have lots of different derived classes or subclasses which are going to be actual shapes, such as a square, rectangle, circle, triangle, etc. Okay, so our shape class is our base class, and then we have lots of different derived classes. So first of all, one of the issues with using inheritance or having a fragile base class, not necessarily inheritance, but having a fragile base class, is inheritance coupling. So inheritance creates a strong coupling between the base class or the superclass and the derived classes or the subclasses. Any changes made to the base class can potentially affect the behavior of all derived classes. So if we change our shape class in our example, it could affect the behavior of all of our derived shape classes. Okay, so another issue is limited extensibility. So the fragile base class problem limits the extensibility of software systems, as modifications made to the base class can become increasingly risky and costly over time. Developers may avoid making necessary changes due to the fear of breaking existing functionality. And this is kind of known as brittle software, where making a change to one part of the program can cause all sorts of different parts of the program to break, making it brittle. So this is kind of, if we have like a base class where we have hundreds of different subclasses or derived classes, then you can kind of see that making changes to this base class becomes very risky, because it could have an effect on so many different derived subclasses, and it could cause all sorts of issues, and it can break a lot of the existing functionality. And this is very much a good example of having a fragile base class, where we have lots of derived classes over time, and making changes to this base class becomes very risky. So how can we mitigate or prevent having a fragile base class in our software? So to mitigate the fragile base class problem, software developers can use design principles such as the solid open-closed principle, and they can also use the dependency inversion principle, as well as using composition over inheritance. And these approaches promote loose coupling, encapsulation, and modular design, reducing the impact of changes in base classes. So generally, it's often recommended to use composition over inheritance. And the reason for this is because composition results in less coupling and more flexibility. And it's also easier to build classes out of various components than it is to try and find commonality between them and build a family tree, as you kind of have to do with inheritance. So there are still cases where inheritance makes more sense, but generally it's recommended to reach for composition more so than inheritance due to those reasons. So UML stands for Unified Modeling Language, and it is a language used to model our systems or our relationships between our classes in our program. And throughout this course I've decided to hand draw the UML diagrams as it's quicker for me and gives me more flexibility to annotate them. But you could also use a web app such as this one that I have linked here. And if I just show you this one, you can see that you can create your UML diagrams with a sort of GUI. But you can also hand draw them if you find that easier, and that's the case for me. So first of all, I'm going to show you how you can represent a simple class using UML. So let's say that we have a dog class, a public class dog, which has one field, which is just a private string with of name. And we also have a method called bark, which returns void and just logs a woof woof. So this can be represented in UML as this diagram. So at the top of the UML diagram, so we just have a sort of box here, and then we have three sections, and then we have the class name at the top, we have the fields listed in this next section, and then we have the methods listed in the bottom section. So if we have a look at this name field now, we can see that this is a private field. So first of all, we specify the access modifier. In this case, it's a negative sign, which means that this is a private field. The name of the field, which is name. And then we specify the the type of the field after a colon, which in this case, it is a string. And then we have the methods. So we have one method, and we have a plus sign here, which means that it's a public method. And it's called bark, and it has a return type of void. So after the colon, we can just leave a blank space, which means that it returns void. And if you use the modeling app that I referenced earlier, and then it would look something like this. So same thing, just a computer drawn version. So we've discussed all of this. And also I should just mention that if the access modifier is omitted, so if I've left the access modifier out, then you should just assume that fields are private and methods are public. Okay, so if I leave out the negative sign or the plus sign, you can just assume that this is a private field, and you should assume that this is a public method. Okay, so that's just a kind of convention that I've used throughout this book. Yeah. So now let's have a look at how we can represent inheritance relationships using UML. So inheritance relationships are represented by an arrow. So we can see here that the dog class inherits from or extends the animal class. So we have an animal class here, and it is extending, and dog is extending or inheriting from the animal class. Okay, so if we have a look at the how this would look in code, we have a public class dog, and in C# we represent inheritance with a colon. So we can see that dog inherits or extends the animal class, and this is like Inheritance is kind of like an is-are relationship. So here we're kind of saying like a dog is an animal. Okay, so that is inheritance. Composition is represented by an arrow with a filled diamond. So here's the filled diamond and here is an arrow. And composition is kind of like a has-at relationship. So we're saying dog has a size. Okay, so here's the sort of computer drawn version. So how would this look in code? So we have our dog class, and then we're saying that dog is composed of a size class. Okay, and here we have a field of size. Okay, and if you're unsure on what composition is exactly, and you know the difference between composition and inheritance, then I will be covering that shortly. Association relationships are represented by an arrow, and they're kind of similar to composition relationships. However, there is a difference between association and composition. So association, a good example for this is a person has a car. So a person has a field for owning a car, but a person is not composed of a car. A person holds a reference to a car so that it can interact with it, but a person can exist without a car. So this is an association relationship. Whereas with composition is when a child object wouldn't be able to exist without its parent object. For example, a hotel is composed of its rooms or holds reference to its rooms, and a hotel bathroom cannot exist without a hotel, without the hotel class. So if you destroy the hotel, then you also destroy the hotel bathroom. The hotel bathroom cannot exist by itself. Otherwise, it's just a bathroom. It's not a hotel bathroom. Also, if a customer is destroyed, their shopping cart and orders are lost too. Therefore, a customer is composed of shopping cart and orders. And if orders are lost, then order details and shipping info are also lost. So orders are composed of shipping info and order details. So that is the main difference between association and composition. Association is where if you destroy, say, a person class, then the car class can still exist because a person isn't composed of or sort of made up of cars. It's just that a person can own a car. So that the person can interact with the car. Whereas composition, on the other hand, is where if you destroy the sort of class that is made up of these other classes or composed of these other classes, then these other classes are also destroyed. So that's the difference between association and composition. So now we're going to have a look at dependency relationship, which is represented by a dashed arrow. So here you can see that dog has a dependency of documents. Okay, so what does this mean? So here we have a public class dog and we have a render method, and we pass a document to this render method. So, you know, presumably this means that we are rendering the dog onto some documents, and we can pass the documents into this render method. So above, document is not a field in this class, okay, but it is used somewhere in the class. In this case, it's a parameter to this render method, but it could also be a local variable defined in the render method. So within this render method, we could say var documents equals new documents, and then that would also mean that dog has a document dependency. So somewhere in dog class we have a reference or dependency to the document class. Okay, and that is a dependency relationship. So essentially we have a parameter or a local variable in one of the methods, and that is called a dependency relationship. So that is all of the UML that I want to discuss for this course. There are many other relationships that we could discuss, but that is all that you need to know for studying design patterns. So one final thing that you should understand before beginning to study design patterns are the 5 solid principles. So here are the 5 solid principles, and The design patterns that we're going to learn in this course are very much based on both object-oriented programming principles that we covered earlier, as well as these 5 solid principles. So they're very crucial to understand. So first of all, we're going to learn the S of the solid principle. So this is an acronym in case you've not noticed, and that is the single responsibility principle. We're going to also learn the open-close principle, the Liskov substitution principle, the interface segregation principle, and the dependency inversion principle. So by following these principles, developers can create software designs that are easier to understand, maintain, and extend, which leads to higher quality software that is more robust and adaptable to change. So let's get started learning the solid principles. So the first solid principle is the single responsibility principle, which states that a class should only have one reason to change, meaning that it should only have one responsibility or purpose. And this principle encourages you to create classes that are more focused and perform one single well-defined task rather than multiple tasks. So by breaking up classes into smaller, more focused units, makes code easier to understand, maintain, and test. So first of all, what we will do is we will create an example that violates the single responsibility principle, and then we will refactor that code so that it adheres to this principle. So first of all, what we're going to do is we're going to create a user class. And this is going to have 2 C# properties. So we're going to have a username, and we are going to have an email property. And we're also going to have in this user class a method for registering a user. So once they sign up to our platform, this should be register. This method will be called once while the user is signing up to our platform. And at the top, we're going to have some register user logic here. So this logic would be stuff like fetching the user from the database by their email, and if they already exist, maybe we could redirect them to the login page, all that kind of stuff related to registering a user, saving them to the database. And then once all that's done, we can send the user an email notification. Okay, so we're going to create an email sender class now for sending email notifications. And this email sender is going to have a send email method, which takes an email that we want to send the email to, and we will have a message. And in here we're just going to console log, and we'll say sending email to sending email to email, and then we will put the message. Okay, so now we can use this class to send the user an email notification once they've signed up successfully. So we can say email sender, and then the message, we will say welcome to our platform. Okay, so in this example, this user class is actually violating the single responsibility principle because it manages user data. Okay, so it contains all data related to a user, such as their username or email, and it also contains the logic for registering a user. Okay, so this class has more than one reason to change. So you can see here that the single responsibility principle states that a class should only have one reason to change, meaning that it should only have one responsibility or purpose. But this class has 2 reasons to change, because if we change, if we make modifications to our user data management, for example, we might add more fields here. We might add first name, gender, hobbies, age, all that kind of stuff. If we add that to our user, we would have to modify this class. We'd have to add more fields. But another reason that we could modify this class, or another reason why this class would need to be changed, is if we changed the logic of registering a user. For example, we may choose to fetch a user from the database by their username rather than by their email. So let's refactor this class so that it satisfies the single responsibility principle. So to do that, we can create a separate class called user service. So let's do that. And in this user service class, we will put all of the methods or all of the business logic related to registering a user, or maybe logging a user in, or updating a user. All those kind of methods can go into this user service. But we do need access to certain user data. So what we can do is we can just pass the user into this method, and then we can call user.email. Okay, so in this refactored code, the user class is now solely responsible for representing user data. Okay, so it has one responsibility, a single responsibility. And the user service class now handles user registration. This class can contain all sort of business logic related to users. So currently we only have a register function, but we could also have a login method or an update method to manage any sort of business logic related to a user. And this separation of responsibilities adheres to the single responsibility principle, and so it makes our code easier to understand, maintain, and extend. The open-close principle states that software entities, such as classes, modules, or functions, should be open for extension but closed for modification. And this principle promotes the idea that existing code should be able to be extended with new functionality without modifying its source code. So, and it encourages the use of abstraction and polymorphism to achieve this goal, allowing for code to be easily extended through inheritance or composition. So if that doesn't make much sense to you, we're now going to go through an example where we have a shape class hierarchy that calculates the area of different shapes. And initially this is going to violate the open-close principle, because when we add any new shapes, it requires modifying the existing code. So first of all, what we're going to do is we're going to create an enum for our types of shapes. Okay, so we're just going to support a circle and a rectangle initially. And we're going to create a class for shape. And this is going to be a class which stores the shape type and radius, length, and width. So it supports lots of different shapes. Okay. So I'm just going to paste those in. So we have a shape type, so it can be, for example, a rectangle or a circle. So it has a radius, so if the shape is a circle, we're going to set the radius. If it's a rectangle, we'll set the length and width. And then we're going to have a method for calculating the area of the shape. And we're going to have a switch statement, which takes in the type of the shape, and it's going to look at the type of the shape. So for example, if the shape type is circle, we are going to return pi r squared, which is the equation for calculating the area of a circle. So math.pow. So this is just the radius squared, radius to the power of 2. And if the shape type is a rectangle, we are going to return the length times the width. Okay, and if our shape type doesn't match any of the shape types here, then we're going to throw an exception to say that we do not support this shape type. Okay. So in this example, the shape class has a method for calculating the area of a shape based on the type of shape. So if we add a new shape, such as a triangle, so if we added a triangle in here, and then we wanted to support calculating the area of a triangle, it would require modifying this existing shape class. Okay, so if we add a new shape, every time we add a new shape, we have to modify this shape class. We may have to add new properties to support triangles. We may have to add things like the hypotenuse, the whatever the other sides of a triangle are, I've forgotten. And then we have to calculate the area of a triangle. Okay, so this class is just going to keep on getting modified every time we add a new shape. This calculate area method is just going to get bigger and bigger and bigger. It's going to be hard to understand, and every time we add a new shape, we risk adding bugs into code that has been tested and we know works. So this is a really poor way to implement this kind of application or functionality. So let's now refactor this code to adhere to the open-close principle, so that whenever we add a shape, we don't have to modify any existing code. So essentially we want to allow for extension, which means adding new classes to our code base. For example, we can extend our code base by adding a new shape, but we don't want to modify our existing class, existing source code. So now let's refactor this code using inheritance and polymorphism. So I think what I'm going to do is let's remove all of these properties from the shape class, and let's remove all of this. And what I'm going to do is I'm going to make this class abstract, meaning that we can create methods that essentially have no body. Okay, like that. So that when any classes that inherit this shape class now have to provide their own implementations of this calculate area method. So what we're going to do now is we're going to create individual shape classes. So we're going to create a circle class, and this is going to inherit shape. And when you can see we have an error here. So if I press Command and full stop, or I guess Control full stop on Windows, we can then implement this abstract class. So we now override this calculate area method from the shape abstract class. Okay, so this is an abstract class, and then we are providing concrete implementations of shapes. Okay, so circle is a concrete implementation of the shape class, and concrete basically meaning that it's not abstract, it's a proper normal class. So in here, to calculate area, we need to do pi r squared. So now we need to store a property for radius, and here we can just return math.pi times math.pow radius to the power of 2. Okay, so there's our circle class. And now we want to add a rectangle class. So let's add that. And a rectangle has a length and a width. So we'll add properties for length and width. And then to calculate the area of a rectangle, we just return the length times the width. Okay, but what we need to do here is make sure that we inherit the shape. Now it gives us an error because the shape, if we inherit shape, it's forcing all of the concrete shapes to implement the calculate area method. So let's implement that, and we just want to return the length times the width. Okay, so we've now refactored the code so that we have individual shape classes rather than having this shape class which kind of manages multiple shapes. And this actually also satisfies the single responsibility principle, because the shape class now isn't managing calculating the area. Well, it isn't managing multiple different types of shapes, and we now have individual shape classes rather than having the shape class manage all of the different types of shapes. So in this refactored code, we define an abstract shape class with an abstract calculate area method, and we define concrete shape classes, circle and rectangle, which inherit the shape class and provide their own implementations of the calculate area method. So now, with this new solution, whenever we add a new shape, such as a triangle, it would involve creating a new class which inherits from shape and implements the calculate area method without having to modify any existing code. So if we wanted to add a triangle shape, and we wanted to add the ability to calculate an area, we would just create a new triangle class which extends shape and includes the calculate area method, and that's it. We just extend our code base, we add a new class without having to modify any existing code. So we're not risking adding bugs into previously tested working code, and that satisfies the open close principle by allowing for extension without modification. So being able to add functionality without modifying existing code means that we don't have to worry as much about breaking existing working code and introducing bugs. So following the open close principle encourages us to design software so that we can add new features only by adding new code, and this helps us to build loosely coupled maintainable software. The Liskov substitution principle states that objects of a superclass should be replaceable with objects of its subclass without affecting the correctness of the program. So this principle ensures that inheritance hierarchies are well designed and that subclasses adhere to the contracts defined by their superclasses. And violations of this principle can lead to unexpected behavior or errors when substituting objects, making code harder to reason about and maintain. So this is very confusing, so let's consider an example involving a rectangle class and a square class which inherit from a common shape class. And initially this is going to violate the Liskov substitution principle by not adhering to the behavior expected from these classes, and then we'll fix it to ensure that the principle is respected. So first of all, we're going to create a shape class, and this is going to be an abstract class. This is going to sit at the very top of our sort of shape class hierarchy, and we're going to create a public abstract property for area. And so all shapes should have this area property. So next up, we're going to create a concrete implementation of our abstract shape class. So we're going to create a rectangle class. And this is going to inherit shape. And then we can press Command full stop, implement abstract class. and we can see VS Code automatically implements this area property for us. So if we look at a rectangle has a width and a height. So let's add properties for width and height, because we need those properties to be able to calculate the area of the rectangle. And the area of a rectangle is very simply just its width times its height. Okay, so that's a rectangle. We're now going to create a square class, and this is where things get slightly more interesting, because the way we're going to implement this square class is we are going to extend or inherit from the rectangle class. And why are we doing this? Because, well, a square is mathematically just a special type of rectangle where the width and the height are equal to each other. Okay, so that's our line of thinking. We're just thinking, right, a square class is a special type of rectangle. A square is a rectangle. So let's actually inherit the rectangle class. But we need to make a few modifications, because if we set the width on a square, then we need to make sure that it's equal to the height. And if we set the height on a square, then we need to make sure that the width is also set equal to the height, so that the side lengths are always the same and a square always remains square. So let's actually do that. So what we can do is we can override the width property, and we can say that the getter remains the same. We just return the width, the base referring to our base class, which in this case is rectangle. And then we can update the setter so that the base.width is equal to the base.height, which is equal to the value that we are setting to. Okay, so the width and the height are always going to be equal. And then we can do the same for the height, and I'm just going to save a little bit of time here and copy and paste that in. So as you can see, the getter just returns the height, and when we also set the width equal to the value that we are setting to. Okay, so a square always remains square. Okay, so now what we're going to do is we're going to write a test. And in the test, what we're going to do is we're going to make sure that our program is calculating areas correctly, or as expected. So we're going to create a rectangle, and we're going to set the rectangle's height equal to 10, and we're going to set the rectangle's width equal to 5. And then we can say that the expected area is going to be equal to 10 times 5, which equals 50. Okay, and then we can log the actual area that the rectangle calculates by calling rect.area. So if we run this program, we can see that the expected area is equal to the calculated area, and this test passes successfully. But now if we look at the Liskov substitution principle, objects of a superclass should be replaceable with objects of its subclass. So the superclass in this case is rectangle, and a rectangle subclass is square, because a square is a subclass of rectangle in this case, right? It inherits from rectangle. So, according to the Liskov substitution principle, we should be able to substitute a rectangle for a square, and our program should still be correct. So let's see if that works. So we substitute it for a square, run our program, and we can see that the expected area is 50, but the calculated area is 25, because when we set the width, it also sets the height to 5 as well. So then when it calculates the area, it's going to be returning height times width, which is 5 times 5, which equals 25. And this is not what we expected. So we are here violating the Liskov substitution principle. And you can kind of see how this makes it easier for our program to contain bugs, because if we treat a square as a rectangle, which according to our code we should be able to, we shouldn't get any errors, but we are getting errors. This test no longer passes. So let's refactor our program to satisfy the Liskov substitution principle. So what we are going to do is we're going to modify our square class so that it no longer inherits from rectangle. Okay, so what we're going to do is we're going to inherit from shape. Okay, we're just going to say a square as a shape and not a rectangle. Okay, so in a square, really, it doesn't really feel very correct to store width and height properties on a square. It doesn't really make much sense, because a square just has a side length, and all the side lengths are equal. It has 4 sides, and each side is an equal length. So really, we only need to store one property called side length. So if we create a public property for side length, and also we can see here that we are getting an error because we need to implement this shape abstract class by providing an area property, and the area is just going to be the side length squared, or the side length times the side length. Okay, so we now have a rectangle and a square, which are both shapes. They both inherit the shape class. So now let's create a test for our square and rectangle. So what I'm going to do is let's comment this out for now, and we'll create a new test. So we're going to just say shape rectangle equals new rectangle. And I think what we'll do actually is we'll just set the width and height when we create the rectangle, just to save a little bit of a few lines of code. Okay, and then what we will do is we will log the area of the rectangle. Okay, and then what we'll do is we'll also create a test for our square class. And as you can see here, both rectangle and square are shapes. They are classes of type shape. And we're going to create a new square, and we will set the side length equal to 5. And then we can say area of the square is equal to square dot area. Okay, so here we're expecting 25 because 5 times 5 is 25, and above we are expecting 20. Okay. Okay, perfect. So now what we can do is we can essentially we've redesigned the square class to directly set the side length. So now that now a square is correctly modeled as a subclass of shape, and it adheres to the Liskov substitution principle, because now all shapes are substitutable with each other, and they calculate their areas correctly, okay, or as expected. So how does this satisfy the Liskov substitution principle? Well, we've created a superclass called shape and subclasses rectangle and square, okay, and both rectangle and square maintain the correct expected behavior of a shape. And in our case, that is providing an area. And they should both behave appropriately when interacting with other parts of the program that expect shapes. So we can now treat rectangle and square as shape of type shape, and they both always calculate areas as we expect them to. The expected area of a square here, I mean, we haven't logged what the expected area is, but we could log that the expected area is going to be 25, and here we could log that the expected area is going to be 20. Okay, and whatever we change the side length to, whatever we set the side length to, it's always going to give us the correct area. Okay, so shapes now are always going to return the correct area. We have no problems with substituting shapes with other shapes and then calculating their areas. Okay, so now we are satisfying the Liskov substitution principle, and our program is less error prone. Okay, less prone to introducing bugs and less prone to unexpected behavior. The interface segregation principle states that clients should not be forced to depend on interfaces that they do not use. And this principle encourages the creation of fine-grained interfaces that contain only the methods required by the clients that use them. It helps to prevent the creation of fat interfaces that force clients to implement unnecessary methods, leading to cleaner and more maintainable code. So this may sound confusing again, but actually this principle is pretty straightforward. So let's consider an example that involves 2D and 3D shapes. And initially we're going to violate this interface segregation principle, and then we are going to refactor that code to adhere to the principle. So first of all, we're going to create an interface called iShape. And this is going to contain methods for calculating certain properties on a shape, such as area or volume. Okay, so now what we're going to do is we're going to create a circle class, a concrete circle class, and that's going to implement this iShape interface. Okay, so we're getting a red squiggly line here, which means that we need to implement this interface, or implement the methods on this interface. So a circle class is going to have a radius property. And what we're going to do is, to calculate the area of a circle, we just quite simply do pi r squared. So we're going to return pi times the radius to the power of 2. And then for calculating the volume, well, here we have an issue because circles don't actually have volumes because they are a 2D shape. All 2D shapes don't have volumes, they only have areas. So here we're being forced to implement this volume method from iShape, because iShape states that we must implement a volume method, otherwise we'll get an error. So what we're going to have to do here really is we're going to return an invalid operation exception, and we'll say that volume is volume not applicable for 2D shapes. Okay, so that is the circle, and now we're going to create a 3D shape now called sphere. So basically a ball, and this is also going to implement the iShape class. The iShape interface, and we press Command full stop or Control full stop, and we're going to implement the methods on this interface. So to calculate the area of a sphere, we have to do the radius to the power of 2 times pi times 4. That's just the equation for calculating the area of a sphere. So I'm just going to paste that in. So we have 4 times pi times the radius squared, and then the volume of a sphere is this equation. So it's 4/3 or 4/3 times pi times the radius cubed. Okay, so 4/3 pi r cubed. Okay, so this all looks okay. I think what we'll do next is we will create, we will actually use this solution. So let's create a circle. If we come into program.cs, and we will create a new circle from here, and we'll set the radius equal to 10, and let's log the area, and let's also log the volume. Okay, so according to VS Code, we have no problems here. This code should be safe to run, but if we run the code, we can see that we get an exception because volume is not applicable for 2D shapes. We are in our program we are calling circle.volume, and VS Code even suggests that we can call this function, this method, and everything looks okay. But when we run the code, we have a problem. So really, this volume method should not exist on Circle because it really, well, all 2D shapes don't have a volume, so it just doesn't make any sense. It's making our code more prone to bugs by allowing us to call this method on a circle. So it's easy to see that how violating this interface segregation principle can introduce bugs into a program, because above everything looks okay until we run the program and then we get the exception thrown. Because this I-shape interface is forcing us to implement volume methods on all of our shapes, even when it's not relevant. So how can we solve this problem? So let's refactor our code. So what we're going to do is we're going to segregate this I-shape interface into two separate interfaces. So we're going to create a I-shape 2D and an I-shape 3D. So this actually can be changed to 3D because 3D shapes have both an area and a volume. So I'm just going to rename this file to I-shape 3D. And I'm going to create another interface called I-shape 2D. And 2D shapes only have an area. They don't have a volume. Okay. And again, this should be an interface, not a class. Okay, so now we've segregated the I-shape interface into two separate, smaller, more sort of fine-grained interfaces that are more specific, okay, rather than large and sort of general. And now what this allows us to do is in our circle class, we can implement the I-shape 2D, and we can remove this volume method because we are no longer being forced to implement a volume method. And then in our sphere class, we can implement the 3D interface. And now if we go back into our program, we can see if we try to call volume on a 2D shape, we are now getting an error. So VS Code is straight away saying this method does not exist, basically. And it shouldn't exist because 2D shapes don't have volumes. So as you can see, the interface segregation principle ensures that clients are not forced to depend on methods that they do not use. Clients can now depend only on the interfaces that they need, promoting better code and reusability. And if you are unsure on what a client is, a client essentially just means classes that are using the shape interface. Okay, so for example, a circle is a client of the iShape 2D interface. The dependency inversion principle states that high-level modules should not depend on low-level modules. Both should depend on abstractions. So dependency inversion is the strategy of depending upon interfaces or abstract classes rather than upon concrete classes. This principle promotes decoupling between modules and promotes the use of interfaces or abstract classes to define dependencies, allowing for more flexible and testable code. So this probably doesn't make any sense whatsoever, so we're going to start with an example that first violates the dependency inversion principle, and then we are going to correct it. So first of all, I'm going to create an engine class. And the engine class is just going to contain a single method called start, which is just going to log engine started. Okay, and then we're going to create a car class. And car is going to be built up from different parts, and one of those parts is an engine. A car, of course, would also have wheels and a chassis and all different other things that it would be built up from, but we're just going to keep things simple for now and just include the engine. And we're going to have a constructor for this car, and in the constructor we're just going to set the engine, so we'll just say this.engine equals new engine. So we have this car class which has a direct dependency on this concrete engine class, and this car class is also going to contain a method for starting the car. And to start the car, we actually need to start the engine. So we can call engine.start, and we can just log car started. Okay, so in this example, the car class directly creates an instance of the engine class, leading to a tight coupling between car and engine. So if this particular engine class changes, it may affect the car class, which violates the dependency inversion principle. So if I just show you the UML diagram, what we have here, we have a car class which depends directly on a concrete engine class. Okay, so let's go back here. So how can we fix this issue? Well, first of all, let me just discuss what the issues with this solution are. So if we change the engine class, then it could break the car class. Okay, so that's a problem. If we change the implementation details of this engine class, it can affect the car class. And another thing is that this code isn't very flexible. So if we go into program.cs and we create a car, that's not the correct one. Let's see. Okay. We actually have no way, when we create a new car, we have no way of changing the type of engine that car is built with. So currently, if we want to change the type of engine, so say currently we only have one engine class, but say we have another class called electric engine, or I don't know, V6 engine, or some other powerful engine. There's no way of changing the engine type when we create a new car. You know, we can't just add the engine in here. We have to change it within the car class. Okay, so this isn't very flexible. So if we wanted to say electric engine, we would have to come in here and change it to electric engine, and obviously we would need to create that class. So this is not a very flexible or maintainable solution, because we're having to modify existing source code in order to change the type of engine that a car uses. So this isn't very good. So we can fix this to adhere to the dependency inversion principle. We can introduce an abstraction or an interface between car and engine, allowing car to depend on an abstraction instead of a concrete implementation. So let's come into our folder and create an interface called iEngine. And in here, we're going to say that all engines should have a start method. Then inside of our engine class, we can say that engine implements iEngine. Okay, so an engine is an engine, obviously, and we don't need to do anything here because our engine class already has a start method. And then in car, so currently we have car depending on the concrete implementation of an engine rather than an abstraction, such as an interface or an abstract class. So let's change this. So we can say that rather than engine being this concrete engine, we can say the engine is some type of engine, some abstract engine. And then within the car constructor, we can actually pass a type of engine that we want the car to be built with. So we can say this.engine equals engine. Okay. So the advantage of this method is that it provides us with a lot more flexibility, because now whenever we create a new car, we can, at runtime, we can pass in what type of engine that we want the car to be built with, like so. And currently we only have one type of engine, but let's just say we also had another type of engine that implements the iEngine interface, such as electric engine. Then we can create some sort of electric car. We can build this car up with an electric engine. Okay, so this is called dependency injection, where we inject the dependency into the class. Okay, and this is a very popular term that you may have heard before. Frameworks such as Laravel or Spring Boot use dependency injection throughout a lot of the framework. So let me show you the UML, so what this looks like. So beforehand we had car, which directly depended on engine, whereas now we've added this kind of abstraction, this interface between car and engine. So car now depends on this abstract engine interface, and engine implements the engine interface. Okay, so now we can create multiple different types of engines, each implementing this interface. So we could have a V6 engine which implements this engine interface, or an electric engine, and we can then inject that engine whenever we create a new car object into car to be built with that type of engine. So this has really improved the flexibility of our program. So a few advantages that I just want to mention of dependency injection are that dependency injection promotes loose coupling between components by removing direct dependencies, so that components rely on abstractions rather than concrete implementations, making them more independent and easier to maintain. And dependency injection simplifies unit testing by allowing components to be easily replaced with mock or stub implementations during testing. This enables isolated testing of individual components without relying on their dependencies. And as we discussed, it improves flexibility because we can swap out dependencies at runtime. And then one more thing that I just wanted to mention. So if we go to the dependency inversion principle definition, it states that high-level modules should not depend on low-level modules. Both should depend on abstractions. So we saw that car and engine are now depending on the iEngine interface, rather than on each other. But which of these is the high-level module and which is the low-level module? So the engine is actually considered the low-level module, or the low-level abstraction, because it deals with specific detailed operations related to power generation, whereas the car in this case would be considered the higher level abstraction or the higher level module, because it encompasses a broader scope, coordinating multiple components, including the engine. So currently we only have the engine, but in a real car would of course have multiple components, and to deliver the overall functionality of the vehicle. So the car is the higher level module and the engine is the lower level module, and the high level module no longer depends on the low level module. They both depend on an abstraction, and therefore our code is much more flexible and much more testable, easier to maintain, and that is due to the dependency inversion principle. So now we can start looking at design patterns, and there are three main groups of design patterns. There are creational design patterns, and these are related to the different ways to create objects. There are structural design patterns, and these design patterns are related to the relationships between those objects. And then we have behavioral design patterns, which are related to the interaction or communication between those objects. And first of all, we're going to have a look at the behavioral design patterns. Behavioral design patterns focus on how objects interact with each other and how they communicate to accomplish specific tasks. These patterns address communication, responsibility, and algorithmic issues in object-oriented software design. They help in defining clear and efficient communication mechanisms between objects and classes. These patterns help in making the design more flexible, extensible, and maintainable by promoting better communication and separation of concerns between objects and classes in the system. Each pattern addresses specific design issues and provides a standardized solution to common problems encountered in software development. So if you're unsure on what exactly these words mean, such as flexible, extensible, and maintainable, then throughout this course I'm going to be using these words a lot, and you're going to have they're going to become part of your programming vocabulary as you go along this course. And yeah, these are words that you're going to use quite often to describe the code that you are writing or analyzing. And here you can see that we state that these design patterns provide a standardized solution to common problems. So for example, if you need to implement some sort of undo mechanism in your program, then maybe the first design pattern that comes to mind could be something like the Memento pattern. These are design patterns are really nice tools, and when you're also analyzing other people's code, you're probably going to recognize certain words or certain words that are used in class names, and it's going to give you a sort of clue to the solution that the developer went with. So that being said, let's get started. The Memento pattern is used to restore an object to a previous state, and a common use case for the Memento pattern is when implementing an undo feature. For example, most text editors such as Microsoft Word have undo features where you can undo things by pressing Ctrl-Z on Windows or Command-Z on Mac. So here are some things that you might want to do in a text editor. So you might want to add a title to the document, such as test title. You might want to write some text, such as hello there, my name is Dan. And then you might want to update or change the title of the document to the life of a developer, my memoirs. And a simple way to implement this text editor in code would be to create a single editor class and have a field for title and content, and also have a field that stores each of the previous values for each field in some list. So here we have the UML for a editor class. It has a title field and a content field, both of type string. And then we have a previous titles field, which stores a list of all of the previous titles. So if we update the title, it will push the current title onto this list and then update the title. And the same thing for content. Okay, we have a previous content list too. But the problem with this solution is that every time we add a new field, such as author, date, or is published, we have to keep storing a list of previous states or all of the changes for each of the new fields. So you can see that this editor class is going to become very bloated with a large number of fields. And also, how would we actually implement the undo feature with this solution? Because if the user changed the title, then they changed the content, then pressed undo, the current implementation has no knowledge of what the user last did. It doesn't know whether the title last changed or the content last changed. And so when undo is pressed, our solution doesn't really know whether we should undo the title or undo the content, or both at the same time. So this isn't a great solution. So let's think of a better way of doing this. So instead of having multiple fields in the editor class, we could create a separate class to store the state of our editor at any given time. So here we have our editor class, title, content fields, and now we have a list of previous state objects, and this is a state object which stores the title and content of the editor at any given time. And note that this is a composition relationship represented by the diamond arrow, where editor is composed of or has a field of the editor state class, and it has a list of editor states. And this is a better solution because we can undo multiple times, and we also don't pollute the editor class with too many fields. We just have one field for storing a list of editor states. However, this solution is violating the single responsibility principle, as our editor class currently has multiple responsibilities. It is currently managing the state of the editor, so it is storing a list of states, and it's also providing the features that we need from an editor. So what we should do is we should take all the state management stuff out of the editor and put it somewhere else into some separate class, and this is what we end up with. So now we have a separate class called history, which is basically managing the list of states or list of previous states from our editor. So here we can see that we have a create state method inside of the editor, and the create state method simply returns an editor state object, or the current state of the editor. And that is represented by a dotted line arrow here. So we can see that editor has a dependency of editor state because one of its methods is returning an editor state object, which is the create state method, is returning this editor state object. And then we also have a history class, which has a field with a list of editor states, hence the diamond arrow or composition relationship represented here. So as history class, we have a backup method, and the backup method, whenever this is called, it will add onto the list of states the current editor state. So editor.createState returns the current state of the editor, and then we push or add it onto this states list, okay, which is storing our sort of history from the editor. And then we also have an undo method in this history class, which basically gets or pops off the last state from the states list. It then removes that state from the list and then restores the editor to that last state. So that is how we sort of implement the undo feature now. So this is actually the Memento pattern, this kind of represented by this UML diagram. But let's have a look at how the Memento pattern is represented in the Gang of Four book. So here are the abstract names that each class would be given in the Gang of Four book. So here we have the originator, which is analogous to our editor class. We have the Memento, which is basically our state object. And then we have the caretaker, which in our case is called the history object. And we can see that our solution actually differs slightly from the original Gang of Four Memento pattern, as our caretaker class, which is the history class, also has a field that stores a reference to the editor class, so that the history class can restore the editor state when the user clicks undo. So when the user goes into their history, clicks undo, then we have a reference to the editor class, so we can actually call editor.restore and pass in the state that we want to restore the editor to. And that's just nice, sort of convenient way of doing that, and it works for our kind of program or our application. So you can see that with these design patterns, they are not, you don't have to follow them exactly. You can change them slightly. It's just the general shape or idea that we can kind of follow. Okay, so you don't have to follow them exactly. They can be customized or slightly changed, but the general shape is still there. This is still the Memento pattern. Okay, so now what we're going to do is we're going to implement this solution in code so that it makes more sense to you. So first of all, we are going to create our editor class, or using the Gang of Four abstract name, that will be the originator. So let's come into here and create a new C# class called editor. And I'm just going to make a note to say that this is the originator. Okay, so our editor has currently just two fields. It has a public string field. Sorry, it has a property. It has a public property for title, which has a getter and a setter, and it has a public property called content, and we have a getter and setter for that. And we're now going to create the Memento, or the editor state class. Okay, so let's come into here and create a new C# class called editor state. And editor state is just going to store two fields, so it's going to have two private fields. And I'm going to make these read only, so that once the editor state is created, it cannot be changed. So that's going to just add to the robustness of our code, because once the editor state has been created, once we've took a backup of our editor, then we shouldn't then be able to edit that. Okay, it should just be sort of constant. So let's create a field for title and a private read-only string for content. Okay, so now what we're going to do is we're going to create a constructor, and in the constructor we can pass in the title and content, and then we're just going to set our title and content. And then what I want to also do is create a getter for title, so that we can actually retrieve the title for this current state. So we'll create a method called getTitle, and that is very simply just going to return the title. And we'll also create a getter, because we will need access to the content if we're going to restore the content and the title to previous states. We're going to restore the editor to a previous state, then we need to be able to actually get the title and the content from this editor state object. So let's create another getter called getContent, and we're just going to return the content. And what I'm also going to do here is, in this editor state object, I'm going to add some state metadata. Okay, and I'm going to make it private read only, and I'm just going to store the date that the state was created at, and I'm going to call this state created at. And what I'm going to do is, when a editor state object is created, we can set the state created at field equal to datetime.now. So whenever we create a backup we're kind of storing the date and time that the backup was created. Okay, so it's just like a little bit of extra metadata to give us a little bit more information about the state, or when the state was backed up. So let's also create a getter for this date field. So this is going to return a date time piece of data, and we're just going to return the state created at. Okay, so that's everything we needed to do in our Memento object. So I'll just make a note that this in the gang of 4 is referred to as the Memento object, the state object. Okay, so now what I'm going to do is I'm going to come back into our editor class, and I'm going to create a couple of methods. So I'm going to create a method called createState, which is going to return an editor state object. Okay, and this editor state is going to take the title and the content. Okay, so whenever we create a state, we're just simply returning the current state of the editor, the current title and the current content. Okay, and then to restore the editor to a previous state, we can create a restore method, which takes in an editor state object, and we can just simply set the title equal to that state's title. So we can say, let me change this actually, we'll just call this state, and we will say this is going to be equal to state.title, so get title, and then we'll set the content equal to state.get content. Okay, so that's everything we need to do in our editor class. We have our fields in the editor. We also have a method for creating a sort of backup, or a sort of state object of the current state of the editor. And we also have a restore method for restoring the editor to any previous state. Okay, so now what we're going to do is we need to make our sort of history class, or in the gang of 4, that will be referred to as our caretaker class. So we're calling it the history object, or the history class. And the history class stores a list of all the previous editor states. And we're going to call this states, and we'll just set it equal to a new list of editor states. And in our case, we're also going to store a reference to the editor class, the editor object. Okay, and then when we construct the history object, we need to actually pass in the editor that the history class is referring to. So let's create the constructor, and we're going to pass an editor as a parameter, and we're just going to set the editor equal to the editor that we pass into this history object upon object creation. Okay, so now we need to add our backup method. So let's create a public method called backup, and all this is going to do is it's going to add onto the states list the current state of the editor, and we have a createState method which does that for us. So that's pretty simple. And we also need a undo method. So this is going to allow us to restore the editor to its last backed up state. So what we need to do here is we need to just perform a check to say to check if we actually have any backed up states. So we can say if states.count equals 0, then we can just return. Okay, so if we don't have any backed up, if we have no states in our states list, then we can just return here. There's nothing to undo. Otherwise, we can get the last state from the editor. So the previous state, and that's going to be equal to states.last. We can then remove this state from the states list. So this is the equivalent of just popping the state off of the list, off of the end of the list. And then what we can do is we can call our editor, and we can call the restore method, and we can pass the last state or the previous state, and the editor will be restored to its previous state. And what I'm also going to do is a kind of nice method that we can add to this history class is one called show history, where we basically list all of the history, all of the backed up states that we have of our editor. So let's actually implement this. I'm just going to put a new line here, and I'm going to say history. Here's the list of mementos. And what we're going to do is we can loop through all of the states, and we can just console write state dot get. Actually, I think we need to add another method to the editor state class. Yeah, because I wanted to call a method called getName, but we actually haven't implemented that yet. So if we go back into our editor state class, we're going to create another method called getName. And this is just going to return something that we can display on the console to sort of represent the state. So let's see. So what we're going to do is we're going to log the created at date, and we will also log the title. Okay, so this is just basically going to be our kind of some way of a sort of unique identifier for the state object. So if we go back into history, we can see the error has disappeared, and now everything should be ready to start using. So now if we come into our program.cs file, let's actually test out our Memento pattern solution for this editor. So I'm going to create a new editor. I'm also going to create a history object, and we're going to pass the editor into this history object, and it says the namespace is missing, so let's see. So we need to move that into here, and let's see. Yeah, so we just need to change the namespace here, and hopefully that fixes things. Okay, good. And then what we can do is we can create a backup of our editor, so we can call the backup method. And then let's change the title to test. And then let's also back up the editor. Okay, so here we are backing up a sort of blank editor, and then we are backing up the editor where the title is changed to test. And then we can change the, let's change the content to hello there, my name is Dan. And then we can back up again. And then we'll change the title to my Mementos, why not? Okay, so now let's actually log out what the title of the editor is. And let's also log the content. Okay, so let's actually just check what is going on here. So we can see the title is what we last changed the title to, which is this, The Life of a Dev, which is correct. And the content is, hello there, my name is Dan. So this is correct. And now what we can do, let's test out our undo functionality. So let's call history.backup and, history.undo. And let's actually log the title and the content here after undoing. So let's see what we get here. Okay, so the title is now test, but the content has remained the same. So is this correct? So the last thing we did is we updated the title from test to the life of a dev. So the title should be test and the content should remain the same as hello there, my name is Dan. So that is correct. So that's working correctly. The state has been restored to its previous state, and that is working perfectly. Let's also test out our show history function. So if this was, I don't know, a web browser, I guess this would allow us to view the list of histories, I guess, or a list of web pages that we have visited. And you can see here the backups that we have of our editor or our list of mementos. We can see here we have one where the title is test and one where the title is blank. So this is working pretty good. And finally, let's call undo again and then log out the values. And we can see the title is test and the content has gone from this to nothing, which is correct. And then I guess if we do it one more time, we should just get a blank document. Okay, perfect. So our solution is working correctly. So when should you use the Memento pattern? So the Memento pattern can be used when you want to produce a snapshot of an object state and to be able to restore the object to a previous state. It's a commonly used pattern for implementing the undo feature, and so provides a common solution that a team of developers can quickly understand and get on the same page with. So what are some pros and cons of the Memento pattern? So one of the pros is that you can simplify the originator's code, which in our case was the editor class, by letting the caretaker or the history class maintain the history of the originator state, satisfying the single responsibility principle. And this kind of makes our code more easier to understand and improves the readability, and also means that our classes have sort of less reasons to change. You know, if we need to change the way that we store history, then we just need to update the history class. We don't need to touch the editor class. And one of the cons of this Memento pattern is that it can consume a lot of RAM or random access memory if lots of mementos are created. So if we have to create thousands of mementos, and potentially each memento could be storing a large amount of data. For example, if we wanted to restore a video to a previous state, if we had some sort of video editor application, then taking a backup of a whole video would consume a lot of RAM. So taking lots of mementos of this would be potentially very bad, because it could slow down the application or cause it to crash. So there are other design patterns that can be used to restore states if the memento pattern is causing too much RAM to be consumed. The state pattern allows an object to behave differently depending on the state that it is currently in. So say that you are writing a blog post using the popular content management system WordPress, And the document or post can be in one of three states. So it can be in draft, moderation, or under review by an admin, or it can be published. And there are also three types of user roles within WordPress. There are readers that can only read posts. There are editors that can read or edit posts. And there are admins that can read, edit, or create new posts or delete posts. And only admins can publish documents. Okay, so if a post is under moderation, then only an admin can publish that document. Or that post, I should say. So first of all, we're going to create a simple solution that uses if-else conditional statements to check the current state of the document to see whether the state of the document should be upgraded. So first of all, we're going to create an enum called document states, which is going to store all of the possible states for our document or our post. And we're going to have a draft state, a moderation state, and a published state. And we're also going to create an enum to store our possible user roles. And we have readers, editors, and admins. Okay. So now I'm going to create the document class or the post class, and in here we are going to store the current document state. Okay, so this is going to be of type document states, which means that it's going to be one of these values, either draft, moderation, or published. And this is going to be a property, so we're going to give it a getter and a setter. And we're going to do the same for the user role. Okay, so the current user role. Okay, so now what we're going to do is we're going to create our publish method. So let's create that. And this publish method is essentially responsible for updating or upgrading the state of the document to the next state. So what we're going to do is we're going to write some conditional statements here. So we're going to check if the state is in a draft state. Then we are going to upgrade the state to document states dot moderation. Okay, so we're going to upgrade from draft to moderation, the next or sort of step up, where the admin can review the state of the document. Else if the state is equal to the document states.moderation. So if we are currently in moderation state, then we need to check the user roles, because only admins can publish a document from moderation to published. So here we can say if are you kidding me? Keyboard's locked. What are you doing? Okay. So here we can say if current user role is equal to user roles dot admin. We can set the state of the document to published. Okay. Otherwise, we do nothing. So if the current user is not an admin, then they cannot upgrade the state of the document from this moderation state. So we do nothing. And then what we can say is else if state equals document states dot published, then we can basically do nothing, because there's no higher state than published. So technically we could get rid of this but we'll just leave it here so that it's clear that we are doing nothing if the document state is already published. And one other thing that we could also add up here is that if the document state is in a draft state, then we could also check to see if the current user role is an admin, and then just skip this moderation state and go straight to published. That's something that we could do. Otherwise, if the user is not an admin, then we go to this state. So that's something that we could do, but just for simplicity, we'll keep it as this. Okay, so let's actually try to use this solution. So if we go into program.cs and we create a new document, and we will need to import this from, let's see, should be from here. And let's set the document state to moderation. And then let's set the current user role to admin. And we will just log the document state. Okay, so let's run this to see what we have. And we can see that the document state is currently in moderation, which is correct. But now, if we try to publish the document, and we log the document state, let's see what we get. So the current user role is an admin, and the current document state is in moderation. So the admin has moderated or checked that the document is okay. They've then clicked the publish button, and now the document should be in a published state. So let's check if it is in a published state. Correct, so the document has gone from moderation to published. But if we change the user role to something less than admin, such as an editor, editors can't publish documents. They need to be checked by an admin before being published. So now we should see that the state is remains in moderation. And that is correct. We get 2 logs of moderation. So that is all working correctly. Now, can you spot the problems with the current document class? Okay, so if you take a look at the document class, can you spot any issues? Is it violating any of the solid principles, for example? So if you check out this publish method, we can see there's lots of if-else conditional statements, right? So what we're actually doing here is we are violating the open-closed principle, because if we add any other states or user roles, many of the document classes methods, such as this publish method, currently we only have one method, but a real document would have multiple methods. And we're going to have to modify all of these methods. So if we add another user role, we're going to have even more if-else statements, right? And this class is going to become extremely bloated with all of these if-else conditional statements in every single one of its methods, pretty much. And yeah, with more states, this class is going to become bloated, unwieldy, and difficult to understand. And the code is very difficult to maintain because any changes in logic may require changing state conditionals in every one of this document class's methods. So let's see how we can improve on our solution and solve some of the issues that we encountered by using the state pattern. So the state pattern suggests that we should create state classes for each possible state of the document object. Now, if you remember, we have 3 possible states. And those were draft, moderation, and published. So that means we should create 3 new classes for each of those possible states and extract all state-specific logic out of this document class and into these individual state objects. The document class will then store a reference to one of these state classes to represent the current state that the document is in. Then, instead of the document implementing state-specific behavior by itself, it delegates all state-related work to the state object that it has reference to. So here is the UML diagram that we are going to implement in code. So we have our document class, which stores reference to a state object, and it can be any one of these concrete state objects, provided that these concrete objects implement the state interface. Okay, so this is going to be an object of type state, which can be any one of these concrete state objects. And we're also going to store reference to the current user role. So then we just have a publish method which delegates all state related work to one of these concrete state objects. So we can see here above that document keeps reference to, or is composed of, represented by this diamond arrow, a state object. And notice that we are using polymorphism, as the state field in the document class can be any one of the concrete state classes, so draft, moderation, or published, as we are coding to an interface, not concrete classes. So we are coding to this state interface, not these individual concrete classes. And that improves flexibility. In documents, the publish method calls state.publish, and it delegates the work to the concrete state object. So why is this a good thing? Because our solution now satisfies the open-close principle. Because if we want to add a new state, so a new concrete state, we create a new concrete state class that implements the state interface. We essentially extend our code base, in other words, add new classes to our code base without having to modify any of the current existing classes, such as the document class. And beforehand, if you remember, if we added a new state, we had to modify existing code, the methods in the document class. Whereas now we just have to extend our code base by adding a new class that implements the state interface. So here's how the state pattern is represented in the Gang of Four book with its abstract class names. So we can see here that our document class is the context object, which is composed of a state object. And then we have a load of concrete states. So let's actually now implement this solution with the state pattern in code. Okay, so first of all, I'm going to create the document class. And I'm also going to create the state interface. And the state interface just has a single publish method. And if this was a real document, it would have more state-dependent methods such as render, but we're just going to keep it simple for this example with the one publish method. So I think now what I'm going to do is I'm going to create the document class, actually create it properly. So let's give it a field or property for storing the current state of the document, and we're also going to have store the user roles as well. So current user role. Okay, and then in the constructor, we're going to pass the current user role. And this should be a type user roles, and we're going to set the state equal to new draft state, and we have not actually made this class yet, so we'll create this shortly. And in here we're going to pass this document object. Okay, so by default, what we're saying here is that when we create a new document, the sort of default initial state of the document is just going to be the draft state. Okay, so then what we can do is we can also set the current user role. Okay, so now we're going to add our publish method. And in here, we are just going to simply call state.publish. Okay, so we're delegating all state-specific work to these concrete state objects, which we are going to create now. So let's create the draft state first of all. And all states should implement the state interface. Okay, so they all should have a publish method. And all states also need to store reference to the document object. So let's store a reference to that. And then we need a constructor. And we can set the document in the constructor. So what we do here is, so if we're in draft state and the user clicks publish, okay, so what we should do here is we should change the state of the document to the moderation state. We should upgrade from draft to moderation, okay, so that the admin can review the documents. So what we can do here is we can return a new moderation state, and we pass the document. Okay, and we need to pass the documents because each of these states need to have the ability to change the state field within the document. Okay, so now we get a red squiggly line here because we need to create this moderation state object. So we create a new C# class called moderation state. And in here, again, we need to store reference to the document. And we also, again, need to have a constructor where we set the document. And then remember, this needs to implement the state interface. And if we implement that interface, we will need to implement a publish method. And within the publish method, we can add our logic. So if we're currently in moderation state, so if we have a look at the old solution, we can see that if state equals moderation, we need to check the current user role. And if the current user role is an admin, then we can upgrade the state to published. Otherwise, we don't do anything. So that is the logic for when publish is clicked when we are currently in moderation state. So what we can do here is we can say if document dot current user role is equal to user roles dot admin, then we can upgrade the document state to published. Published state. And we pass the document. Okay, so let's now create this published state. And in here, we need to implement the state interface. And we also need the same as before. We need a reference to document, and we also need to initialize the document in the constructor. So let's do that. We can just copy and paste that in and change the name of the constructor. Okay, so what happens when a user clicks publish if we are already in the published state? Well, we should just do nothing. So we can just return, or we can just leave this blank. Okay, so we just do nothing basically. So I'll just write a comment. If already in published state. Okay, so that's pretty straightforward. So let's actually now have a look how we can use this state pattern solution. But before we do that, what I'm just going to do is I'm going to change I'm just going to copy and paste this enum into our good solutions folder. So let's add this in here. So this is a user roles enum. And we can paste those in. And that should hopefully enable us to use this state pattern solution. So let's see, so new document, and we need to import this, so should be that one, and we're going to use user roles dot editor, and we're just going to log the document state, so doc.state, and then we'll publish the document and console log, and then we'll publish again and log the doc.state. So let's run this. And we can see that initially we have a draft state, so that is correct. Whenever we create a new document, it is in draft state. And then the user role for this document is an editor. So when we publish a document that is in draft state, it should then go to moderation state, and that is correct. And if we publish again, we should stay in moderation state because the user is not an admin. So that is all working correctly. And let's now change the user role from editor to admin. So now we should go, initially we should have the draft state, then we should have moderation state, and then we should have the publish state, because admins can publish documents. So let's see if that works. And there we go, that is all working correctly. And it's also possible to actually change the state directly. So if we wanted to go back to draft state, we can just simply add in the draft state like so. And if we log the state of the document, we can see here that we go back into draft state. So now if we create any new states, we don't have to modify the document class, as its publish method is coded to an interface and so delegates the work to a concrete class. And as you can see here, the state class is coded to an interface, not a concrete state class, which means that the document class can use polymorphism to delegate the work to any of the concrete state classes. And this gives our program good flexibility. So let's now have a look at the pros and cons of the state pattern. So the state pattern can actually be overkill or over-engineering. For example, consider a simple stopwatch that has two states. So it has a running state, is running, or it has a is running state equals false. So it's either running or it isn't running, it's stopped. And if this is a very, very simple class, and we can be pretty certain that the stopwatch isn't going to get more complex. We're not going to have any more states than either stopped or started. And so using the state pattern and creating more classes here adds unnecessary complexity. So this class, even though it has a few conditional statements in its click method, it's pretty straightforward, and there's not really any need to go ahead and create separate state classes just for this stopwatch. It's pretty straightforward as it is, and we're not going to add any more states in the long run. So when to use the state pattern? So a good indication that you should use the state pattern is if you have a class that behaves differently depending on its state, and you have a large number of conditionals or if-else statements in the methods. So like we did before in this document class, it started to get pretty bloated. We were having lots of if-else statements to check the current state and then do some particular behavior. And this is a good indication that we should abstract this this sort of state dependent behavior into their own classes. So the state pattern can be used with abstract classes to reduce duplication. So in our case, we used an interface. We used the state interface, but you could also have used an abstract class where we kind of keep, maybe some fields or a few methods that are sort of shared between the concrete state objects. So it's also possible to use abstract classes to reduce code duplication. And you can also create a hierarchy of state classes and abstract common code into these abstract base classes. So the pros and cons of the state pattern. So some of the pros are that the state pattern improves readability and simplicity of the context class by eliminating conditionals. It satisfies the single responsibility principle by abstracting state-specific logic into separate classes, and it satisfies the open-close principle because we can introduce new states without modifying existing classes. So our code is open for extension but closed for modification. And one of the cons of this pattern, as we have just discussed with the stopwatch example, is that this pattern can be overkill if there are only a few states or if state logic rarely changes, for example, this class here. The strategy pattern is used to pass different algorithms or behaviors to an object. So first, let's consider an application that stores videos. Before storing a video, the video needs to be compressed using a specific compression algorithm such as MOV or MP4. Then, if necessary, apply an overlay to the video such as black and white or blur. So let's create a video storage class to handle this situation. So first of all, what we want to do is create some enums for the compressor types that we have and also for the overlays. So first of all, let's create the compressors, and this is going to be an enum, and we have MOV, MP4, WebM, and then let's create the overlays. So we're going to have another enum for overlays, and we're going to have no overlay. We're going to have black and white, and we're also going to have a blur overlay. Okay, and the reason we create these enums is because it's better practice than using hard-coded values. For example, if overlay is equal to, this should be just overlay, by the way. Let's see, will it let me? If overlay is equal to MOV. So this is bad practice because we're hard coding a literal string value into the conditional. And one of the reasons why this is a bad practice is because let's say we want to change the name of this extension, we would then have to search through all of the code and change the values one by one. Whereas if we have an enum and we want to change, the name of the MOV extension to MOVV, for example, then we can just use our VS Code or our text editor, and we can, on Mac, I can press function F2 and I can rename to MOVV, for example, and that will change all through the program. Okay, so that's why, one of the good reasons why using an enum is good practice. Okay, so now let's create our video storage class. So let's create a new class called video storage. And our video storage class is going to have two fields. It's going to have a compressor field. I'm just going to give this an underscore because it's a sort of convention in C#. And we're going to have an overlay. Okay. And now we need to create a constructor where we pass the compressor that we want to use, and we also pass the overlay that we want to use. But if the user doesn't want to use any overlay, what we can do is by default provide a default overlay of none. Okay, so if the user doesn't supply an overlay when they create the video storage object, then we're just going to apply no overlay. Then in here, we can just say compressor equals compressor, overlay equals overlay, so set the values of the fields. And then I'm just going to create a couple of setter methods here, so that once the video storage object is created, we can change the compression algorithm or the overlay that is used in the video storage object to store videos. So let's create a getter called setCompressor, and this is going to take a compressor, and we can just set the compressor. And we'll also do the same for overlay, so that the overlay can be updated, so that we can use the same video storage object with different overlays and compressors. Okay, and then we're going to create our store method, which will contain the logic for storing a video. Okay, so this is going to take a file name, and we're going to perform a check where we check if the compressor is equal to compressors.move, MOV. Then we will have some logic for compressing a video using MOV. But of course, that's beyond the scope of this course, so we're just going to log compressing using MOV. Okay, and then we're going to have another conditional. If it's an MP4, and then we can just copy this down and say compressing using MP4. And then we're going to have the same kind of thing for if the video is a WebM. If the compression algorithm is WebM. So this is all of our logic related to compressing the video. And then we also need some logic for applying an overlay to a video. So I'm just going to write overlay logic here. And then I'm just going to copy in this overlay logic to save some time. So let's copy that in. And I just need to change this to not all capitals. Okay, and then at the end we can simply store the video to the file location. So we will say storing video to file name, and this should be here. Okay, and then we can also concatenate on the extension as well. So compressors, actually compressor dot yeah, it's just the compressor, isn't it? Okay, so that will give us the file extension. Okay, so that is our video storage class. So let's now discuss some of the problems with this solution. So first of all, it violates the open-closed principle, because adding new compression algorithms or new overlays means that we have to modify the existing video storage class. So this working and tested code has to be modified, which risks introducing bugs to previously working code. And also developers could get lots of merge conflicts in Git, as multiple developers may have to edit one big class. For example, if one developer is working on compression algorithms and another developer is working on overlays, then both developers will be editing this video storage class, which means that developers can sort of step on each other's toes and things can get kind of difficult to work with and messy. Okay, so you can also see that this is a very bloated video storage class. This method is difficult to follow, even with just 3 overlays and 3 compressors. So you can imagine the more compressors and overlays we add, the more bloated and difficult to read this is going to be. So let's now try to solve this problem using the strategy pattern. So the UML below shows that when we create a video storage object, we pass it to the concrete compressor and overlay objects that we want to use. And this is polymorphism. So video storage can accept many different forms of compressor and overlay objects. Video storage is composed of compressor and overlay objects, as represented by the arrow with a diamond. And there are multiple concrete compressor and overlay implementations that extend the compressor and filter interfaces respectively. So you can see here we have our video storage class, which is composed of a compressor and an overlay. And our video storage class is talking to or coded to an interface, not a concrete implementation of a compressor or overlay. And this provides us with a lot of flexibility because we can very easily swap out the compressor that the video storage is using or the overlay, as long as they implement the compressor or overlay interfaces. Okay, so this is the strategy pattern. And now I'm going to show you how it looks with the abstract class names from the Gang of Four book. So you can see that our video storage class is known as the context, and the context is composed of or stores a reference to a strategy. Okay, and the strategy is represented by an interface, and then we have concrete strategies, each with some sort of method. Okay, so if we have a look at our solution, our video storage is the context, which has a reference to a strategy, and currently we have two different types of strategy in our video storage class. We have compressor and overlay strategies, or algorithms I guess you could call them. And then we have our concrete strategies, which implement these interfaces. Okay, and you can see here in the context or in the video storage class, when we call one of the methods, we are now delegating work to a concrete strategy, okay, rather than actually doing the logic within the context object itself with all the if, else conditional statements. We can just simply delegate the work to the concrete strategy object. So let's now implement this in code. So first of all, let's create the interfaces for our two strategies. Our two strategies being the compressor and the overlay. So I'm just going to create a new folder here called Good Example using the strategy design pattern. And in here, what I'm going to do is I'm going to create a compressor interface called iCompressor. And in C#, it's generally considered good practice to start interfaces with the letter I, so prefix with the letter I, so that it's clear that it's an interface and not just a class. And in here, we're going to have a single method called compress, which returns void. And then we're going to create another interface called iOverlay. And this is going to have a single method called apply. Okay, so now we have our interfaces or our strategy interfaces. We can create the concrete, our concrete strategy object classes, and we have two strategies. So we're going to need two sets of concrete strategy objects or classes. First of all, let's start with the compressors. So I'm going to create a new C# class called compressor MOV, and this needs to implement the iCompressor interface, and then we can implement this interface. And what we're going to do is we're just going to log compressing video using MOV. Okay, and then we're going to do the same for MP4 and WebM. So let's quickly do that. So we can say compressor MP 4. And I'm just going to copy this in to save some time. So it needs to implement the compressor interface, and then we can have our compress function method, and then we're going to do the same for compressor web m. Okay, so those are our concrete compressors. We can now create our concrete overlay strategies. So first of all, let's create the black and white. And this needs to implement the overlay interface. And we can implement that. And here we can just put applying black and white overlay. Okay. And then we also need a overlay for the blur strategy. And then we need and then let's actually call this, make sure that we prefix with compressor. And the reason I like to do this is because then they all kind of stay together in VS Code. So let's just change the name of this. And we just need our compressor for, our overlay for none. Actually, this should be overlay, sorry, apologies. And let's make sure this is correct. Okay, and yeah, what are we doing here? So this should be overlay. Okay, so let's change this to apply. Get rid of this. Okay, so that is correct. And now we need our no overlay class. So overlay none. And this should be overlay. Implement and not applying overlay. Okay, so now we need to create our video storage class. So what I'm going to do is I'm going to copy and paste the class from here, and then we're going to refactor this class to make it sort of satisfy the strategy pattern. So let's create a new class called video storage. I'm just going to paste in what we had before. Okay. So how do we refactor this to satisfy our strategy pattern? Well, first of all, we need, rather than coding to these enums, we're going to change this so that the compressor is coded to the compressor interface. And we're going to do the same for overlay. And we also need to update this to iCompressor. And this needs to be updated to iOverlay. Okay. And we also need to change this to iCompressor. This should be iOverlay. And now the biggest changes are going to be in our store method. So currently, all of the logic for compressing a video is stored in this store method, and also all of the logic for applying an overlay is in here. So what we can now do is we can get rid of all of this, and we can delegate this work to the concrete compressor and overlay objects. So video storage will have no knowledge of the implementation details of each compression and overlay algorithm. So we can say compressor.compress, and we can say overlay.apply. Okay, and in a real application, we probably need to pass the file name to this compress method and also the apply method, so it can get, or maybe pass a video object, something like that. But for now, we're just going to keep things simple, and we're just going to call the compress and apply methods. But as you can see, we no longer need to check what the compression algorithm should be. We also don't need to check what the overlay is that we are applying. We just simply call the compress and then compress method, and then we apply the overlay. So this is way more simple than we had before. So let's actually now have a look at how a client would use this solution. So we can create a video storage object. And it should be this one, and then we can pass in a compressor. So let's just pass in a MOV compressor. So we want to compress to MOV, and for the overlay, let's do black and white. Okay, so let's actually call the store method. And let's pass the file name. So let's just say the file location is videos / some movie. Okay, and then let's see what happens here. Okay, so we've compressed the video using MOV, applied black and white overlay, and then the video has been stored. Okay, so that's good. And because we added setter methods onto the video storage class, so if I just go back into here, we can see we added set compressor and set overlay methods. So that allows us to change the compressor or the overlay that we use within the video storage class. We don't have to create a new video storage object just to use a different compressor, for example. So say we wanted to use a MP4 this time, and the overlay, we wanted no overlay. So if we just said overlay none, oops, sorry, this should be just the compressor, and then we can call video storage.set overlay and pass overlay none, and then we call video storage dot store, and then we pass some location, videos dash some movie. We can actually compress and set an overlay for the same video, but we can use a different compression algorithm and a different overlay just by calling these set methods. Okay, so these setter methods give us a little bit more sort of flexibility with the way that we use the video storage object. Okay. So this is great. So this solution follows the open-closed principle. For example, to create a new compressor, so a new concrete compressor, we simply create a new class that extends the iCompressor interface, which is this, and our code is extended. So our code base is extended, meaning that we've just added a new class, and not modified, meaning that we don't have to modify any existing classes to add a compressor, and same for overlay. So now we can just extend our code base, so we can add a new overlay or add a new compressor, and we don't have to modify any existing code to do that. So you may be wondering, what is the difference between the strategy and state pattern? Because the two patterns probably seem quite similar to you. And the truth is, the two patterns are actually similar, and the difference between them varies depending on who you ask. And some popular answers to this question are that states store a reference to the context object that contains them, whereas strategies do not. States are allowed to replace themselves, in other words, to change the state of the context object to something else, while strategies are not. And strategies only handle a single specific task, while states provide the underlying implementation for everything or almost everything that the context object does. So when should you use the strategy pattern? A good rule of thumb for when it might be a good time to reach for the strategy pattern is when you have a class with a large number of conditional statements that switch between variants of the same algorithm. So in our video storage class, we saw that there were a large number of conditional statements that switch between variants of the same algorithm. So the algorithm being a compression algorithm and the variants being .mov or MP4. And we could see that by switching to the strategy pattern, we got rid of all of those kind of bloated, messy conditional statements. And the algorithm logic can be extracted into separate classes that implement the same interface. And that is what we did with our solution. We extracted the compression logic as well as the overlay logic into separate classes that implemented either a compressor or overlay interface. And the context object, in our case the video storage class, then delegates the work to these classes instead of implementing all of the algorithms itself. So the pros and cons of the strategy pattern. So the pros, it satisfies the open-close principle because we can add new strategies without modifying the context class. And we can swap algorithms used inside an object at runtime. So it provides lots of flexibility. And some of the cons of the strategy pattern are that clients have to be aware of the different algorithms and select the appropriate one. So in our program.cs file, we had to pass the we had to pass the strategy, the compression algorithm or the overlay object that we wanted to use. And if you only have a few algorithms that rarely change, then using the strategy pattern may be over-engineering because we're creating potentially lots of new classes, and it's not really necessary if there are only a few algorithms that aren't going to be changing often. The iterator pattern provides a way of iterating over an object without having to expose the object's internal structure, which may change at some point in the future. So changing the internals of an object should not affect its consumers. So this probably doesn't make too much sense to you, so let me show you what this means with an example. So here we have a shopping list class which stores a list of items, and we have a push method to add an item onto the list, a pop method to remove the last item on the list and then return it, and we have a getList method which returns the whole shopping list. And as you can see here, the shopping list is of type list. It is a list data structure, and each item in the list is of type string. So let's actually use this shopping list in our program.cs file. So I'm just pasting in here where to create a new shopping list called list, and then we're just pushing a few items onto the list, so milk, bread and steak. And now what we want to do is we want to loop over each item in the shopping list and log each of the items. So we can create a for loop starting from 0, and the loop will keep running until as long as I is less than the list length, and we can call count on here. So let's see, list.getList.count, and we want to increment I by 1. So this is giving us an error. Cannot convert type int to bool. So this should be as long as I is less than the length of the shopping list. Okay, so this is going to loop over each item in the shopping list and increment I by 1 each time. So let's have a look at each item in the list, and we can do that by saying list.getList, and we can access the nth, or the ith in this case, item in the list. And then we're just going to log this item. Okay, so let's run this program and see what we get returned. And you can see we have milk, bread and steak as expected. So this looks like a decent solution. However, there is one problem. And the clue, if I give you a clue what the problem could be, it's this sentence here. So changing the internals of an object should not affect its consumers. So if we change the internals of the shopping list object, meaning we change something within the shopping list class, then it should have no effect on its consumers. And currently this program.cs main method is a consumer of shopping list. Okay, so let me show you what the issue actually is. So if we changed the data structure inside of shopping list to a fixed length array, so if we just comment this out for now, and then we say private string, so a string array, list equals new string array, and it's a fixed length array of 50 items long. So if we change the data structure used to store shopping list items, and then let's just say that we updated all of these methods to push, pop and return the list. Okay, we're not going to do that for now because we don't really need to. But if we go into our program.cs, then it would actually cause an error, because fixed length arrays do not have a count field. And currently list.getList inside of our shopping list would return a fixed length array. Okay, it wouldn't return a list, and a fixed length array does not have a count field, so therefore it would cause an error. It would cause our program to break in this consumer. It affects this consumer. So by changing the internals of the shopping list object, it would affect its consumers. Any consumer that is iterating over the list will break. So we can fix this by using the Iterator pattern. So we can use the Iterator pattern to ensure that changing the internals, for example changing the list data structure, doesn't affect any of its consumers. So we can do this by adding some methods to the shopping list class to allow iterating over a shopping list without knowing about its internal representation. So here we have a UML diagram of the shopping list class, and we can see that we still have our push and pop methods, but we've added some extra methods to allow iterating over a shopping list. And you can see here we have a next method, a current method and a has next method. So what we've done here is we've added these three new methods to help consumers to iterate over the list data structure or just the object itself without having to have any knowledge of the internal data structures. So the next method goes to the next item in the list, the current method returns the current item, and the has next method checks if there is another item in the list. And with this structure, we don't know the internal representation of the list object. So if we change the data structure used in shopping list to store items, its consumers wouldn't break or need to be changed. We just have to perhaps update the iterator methods to account for the new data structure. So the problem with the above shopping list class is that it violates the solid single responsibility principle, because shopping list is now responsible for list management using push and pop, and it's also responsible for iteration using next, current, and has next. So to follow the single responsibility principle, we can put the iterator methods into a new class, and that class can be called Iterator. Okay, and as you can see, the shopping list has a dependency on Iterator. And as you can see here, we also have a method inside of our shopping list class called createIterator, and the createIterator method returns an instance of Iterator that allows consumers to iterate over shopping lists without knowing its internal details. However, we have another problem, because if the data structure inside of shopping list changes, then we will need a different iterator to manage it. So iterator needs to be an interface, and then we can have concrete classes for each data structure that implements iterator to ensure that they contain the iterator methods, the correct iterator methods, and the interface determines the capabilities that we need from a real concrete iterator. So the data structures could be an array, a list, a stack, etc. So here is our UML representation. We have our shopping list, which has a createIterator method, which returns an iterator. And we have an iterator interface here, and iterators should have a next, current, and has next method. And then we have our concrete representations of iterators, and each concrete iterator can be used to iterate over specific data structures. In this case, we have a list iterator for iterating over lists, and an array iterator for iterating over arrays. So we can see here that shopping list has a dependency to the iterator interface, as we discussed, because the createIterator method returns an object of type iterator, and the concrete iterator classes extend iterator and implement its methods. So here's how the solution looks using the gang of 4 abstract class names. So we have a collection class which contains the createIterator method, and obviously this is our shopping list class in our example. We have the iterator interface, okay, and createIterator returns an object of type iterator. And then we have our concrete iterators, okay. So now let's implement this in code. So let's now implement the shopping list using the iterator pattern. So I've created a good example folder here, and I've copy and pasted the shopping list from earlier into this new folder. And we're going to refactor this to satisfy the iterator pattern. So first of all, what we need to do is create an interface for the iterators. So I'm going to call this iIterator, and this needs 3 methods. So we need a method called next, we need a hasNext method, which has a return type of Boolean, and we also need a current method, which returns the current item in the loop. So currently, this current method only works with strings, and that's fine for our shopping list because we have a list of strings. However, what if we wanted to loop over a list of orders or customers or integers? So this iterator interface isn't very flexible. It can only work with lists of strings. So what we can actually do to make this more flexible is use a generic type and pass this to the current method. And if this doesn't make sense to you, it will make more sense when we use this iIterator interface shortly. So what we now need to do is create our concrete iterator classes. So we're actually going to create these as nested classes inside of this shopping list class. So let's create a nested iterator, and I'll explain why this is nested soon. So we're going to create a private class called list iterator, and this is a concrete class which is going to iterate over lists. So currently that's what we are that's the data structure that we are using for our list, and this needs to implement the iterator interface, and we can just pass a string data type to that. Now, as you can see, we get an error because we haven't implemented this interface. So let's do that. And let's now create some fields in this concrete iterator object. So we're going to have a shopping list field, because that's what we are looping over. And we will also have an index, so the current position in the loop. And then we also need a constructor, which takes a shopping list and we assign it to the shopping list field. Okay, so now let's update our current method. So this should return the current item in the list. So we can return the shopping list dot list, and then we can just pass the index like so, and this will return the item at the current index in the loop. And then next, let's implement this next method. So all next needs to do is increment the index by 1. So we can just say index equals index plus 1. And then the hasNext method needs to check if we are basically at the end of the list. So we can return index is less than shopping list.list.count. And here we do have access to the count field because we know that we are iterating over a list, because this is a list iterator. Okay, so we just need to put a colon there. Okay, so this is all looking okay. And then in the in our shopping list class, we just need to do one more thing, and that is to create a new method called createIterator, which is going to return the correct iterator. Okay, so in this case we need a list iterator because we are using a data type of list. So let's create this method, and this has a return type of iterator, which allows us to use multiple different types of concrete iterators. So we can return any concrete iterator and it isn't going to cause our clients to break. So here we're going to pass a string because we are iterating over strings, and we can call this createIterator. And this needs to return new list iterator. And we pass the current shopping list. Okay, so that is all looking good. So let's actually test this solution out. So we are no longer going to need this, so let's remove that. And let's create our new iterator. So we can say iterator. In fact, let's just do this. We can say var iterator equals hold on a second. So okay, so we can say var iterator equals list.createIterator. So now we have our iterator. And now what we can do is we can create a while loop. So we can say while the iterator has next. We can console write iterator.current, so get the current item in the iteration cycle, and then we just call the iterator.next method to go to the next item in the list. So let's log this out, and as you can see we still get milk, bread and steak as we would expect. And the advantage of this is now we can safely change the data structure in shopping list, and the code in all of our consumers will still run. Because if you look at our shopping list, currently we have a list of strings, but if we change this to a fixed length array, we could create a new class called fixed length array iterator, which implements the iIterator interface, and it provides these methods. And then in our program.cs file, this would still work because we're just interacting with the methods that are specified on this interface. So because we are effectively coding to an interface, we now don't have to worry about the specific internals of the object that we are iterating over. So when should you use the iterator pattern? So it's a good idea to employ the iterator pattern when your collection possesses a complex internal data structure, or a data structure that is likely to change, so that clients can iterate over the collection without any knowledge of the data structure. So if the internal data structure of an object or of a class changes, then it shouldn't affect the clients. So what are the pros and cons of the iterator pattern? So one of the pros is that it satisfies the single responsibility principle, because the traversal logic is abstracted into a separate class or separate classes. And it also satisfies the open-close principle, because you can create new collections and iterators without breaking the code that uses them. And one of the cons of the iterator pattern is that it can be over-engineering if your app only works with simple collections. The command pattern is a behavioral design pattern that encapsulates a request as an object, allowing you to parameterize clients with queues, requests, or operations. It enables you to decouple the sender from the receiver and provides flexibility in the execution of commands and supports undoable operations. So that probably makes absolutely no sense. So let's make it make sense by going through an example. So we're going to create a remote control that is connected to a light that can either be switched on or off. So first of all, let's create the light. So this is going to be a standard class with two methods, and it's going to be one method called turn on, and we're just going to log light is on, and then we're going to create another method called turn off, and we're just going to log light is off. Okay, so this is the receiver class. This is receiving from the remote. Okay, and then we're going to create the remote control class. Okay, so this is going to be like our invoker class. This is invoking some command to the light, which is receiving the command. So in here, our remote control is going to store a reference to the light, and we will set the light in the constructor. And then we're going to have a method called press button. So it's going to be a very simple remote with one button for now. And this is going to have one parameter, which is a Boolean, and this is whether, if it's true, then we want to turn the light on. If it's false, then we are going to turn the light off. So we're just going to have a simple if statement. So if turn on, then we will call the turn on method on the light. Otherwise, we just turn the light off. And let's now have a look at how a client would use this solution. So in remote control, we pass the light object that we want to control. Okay, and then we can call remote control dot press button, and if we pass true, we should turn the light on, and if we pass false, we should turn the light off. So let's run this program, and we can see that we get light is on and then light is off. Okay, but there actually are some issues with this solution. So in this example, the remote control class directly calls methods on the concrete light object. Okay, so we pass a light object to the remote control, and we are directly calling methods on this concrete light class, because here we can see we're calling light turn on and light turn off. So this direct coupling between remote control and light makes it challenging to extend the functionality or introduce new commands without modifying the remote control class. So for example, suppose that we want to add the functionality to dim the light in addition to being able to turn the light on and off. So if we were to continue with this implementation, then we would need to modify the remote control class directly. If we wanted to add a method to dim the light, then we would need, if we wanted to add functionality to be able to dim the light, then we need to edit this remote control class. For example, we'd create a method called dim light, and we would call light.dimLight, for example. This doesn't exist at the moment, but this is, something what we could do. So this actually violates the solid open-close principle, and it makes it challenging to extend the functionality without having to modify existing code. And as you've already seen multiple times by now, this isn't ideal. So here is the UML for our current solution. So we have a remote control, which is composed of a light object, and it's tightly coupled to this concrete light object because it's calling methods directly that are contained within this light object. So light is tightly coupled to remote control. If we want to add new features, then we have to modify remote control. So let's have a look at how we can improve this solution and make it satisfy the open-close principle so that we don't have to modify existing code to add new features. We can ideally just create some new class or extend our code base. So we have a look at the command pattern UML. We can see here that rather than having remote control talk directly to the light object, instead we can pass a command to remote control, and then whenever the button is pressed, we can simply call command.execute. And we can see here that this command is an interface. So the remote control is now talking to an interface rather than concrete objects. And this provides us with a lot of flexibility because now we can create multiple concrete commands, and we can pass any of those commands as long as it implements this command interface to the remote control. And the remote control needs no knowledge of the specific command that it is working with. Okay, and then we can see here that the commands have an association relationship to light so that they can interact with the light. For turn on, it just needs to call the light.turnOn method. So using the command pattern, we can decouple remote control. So this is the sender class from the light class, which is the receiver. And then to add new functionality, such as dimming the light, we can extend our code base by adding a new dim command without having to modify the remote control class. So if we created a dim class, we could then in the client just pass this command to remote control without having to modify the remote control. And the remote control is composed of a command, as we just discussed, and the concrete commands turn on and turn off, implement, command, and store a reference to light. So let's implement our remote control and light sort of example using the command pattern. So I've created a new folder called good light, so we're going to use the command pattern here. So this is going to be like a good example. And first of all, we're going to create the command interface. So let's create a new interface called iCommand. And this is going to have a single method called execute. And we are also now going to create our remote control class. And our remote control class, or our invoker class, is now going to store a reference to a command. So it's going to be composed of a command object. And we're going to code to an interface here so that we can use polymorphism. And we're going to pass a command into the constructor. Okay. And then what we're going to do is we're also going to add a set command method. So this is going to allow the client to swap commands at runtime. So we're going to create a public void method called setCommand, and this is going to take a command object. So any command object, any command that implements the iCommand interface, and here we can just set the command. And we're also going to have our press button method. And now all we have to do is call the execute method on the command object. And this will execute whatever command we have passed to our remote control. Okay, so let's now create the receiver or the light class. And this is pretty much the same as we had before, so I'm just going to copy those methods in. So you can see here we have a turn on, turn off, and I've also added a dim method so that we can now dim the light as well. And now we can create our concrete commands, so let's go ahead and do that. So let's first of all create a turn on command. And this is going to implement the iCommand interface. So if we implement this interface, we have our execute method, and what we need to do here is we need to store a reference to the object that we are kind of controlling. And in this case, it is the light class. So let's add that in. And then we can pass that into the constructor. Okay. And the light here, this light field, can only be set in the constructor. We're not going to add any setter methods. So basically a command is immutable, so meaning that it can't be changed once it is created. And for our execute method, we can now simply just call the turn on method on the light object. Okay, so let's also create our turn off command. So again, we're going to implement the iCommand interface. Okay, and it's going to be pretty similar to the turn off command. So, the turn on command. And let's copy that in, and we just need to change this to turn off. So we pass a light object into the constructor of the turn off command. And let's also create our dim command. And again, it's going to be pretty similar. But we just need to rename the constructor. And we also need to implement the iCommand interface and call light.dim. Okay, pretty straightforward. So let's now have a look at how a client would use this solution. So if we go into program.cs and create a light, and let's also create our remote. And actually, we don't need to import that. So it's seen here, as you can see here, it's telling us that we need to pass some command object. So initially, I think it's a good idea to actually turn on the light. So let's pass the turn on command. And we also need to pass the light to the command. Okay, and now let's press the button. So if we press the button, we've passed a turn on command. So the remote is just going to execute this turn on command. So let's call the press button. And if we run this, you can see that we get the light is on. So the light has been switched on. And now if we want to say dim the light, so it's too bright, we can call remote.set command, and we can pass the dim command. And then if we press the button and run this, we can see that we get the light is dim. Okay, so we have lots of flexibility now in terms of what command we use, and whenever we want to create a new a command or new functionality for our remote, we can simply extend our code base by creating a new concrete command class without having to touch our invoker class or our remote class. The command pattern is also commonly used in UI frameworks, especially for handling user interactions with buttons or menu items. Each button or menu item can be associated with a specific command object, allowing the framework to execute the appropriate action when the user interacts with the UI element. And this decouples the UI components from the actual operations that they perform, which provides flexibility and maintainability in UI development. Additionally, the command pattern facilitates features such as undo or redo functionality and event logging in UI applications. So here's how a UI framework that implements the command pattern might look. So above this green line we have the framework, and we have a button class which is like our invoker, and this is composed of a command, and you can see the button or the UI component is talking to the command interface, not a concrete command class, and it's also not talking directly to the receiver. So we also have our concrete commands here. So currently we just have an add user command, but we could also have things like delete user or update user. And then this talks to a user service, which actually performs the business logic related to adding a user. So the framework would be the code that you couldn't edit. So for example, some UI package, and the app part is the part that you would create. So the custom code, your actual app that you are building. And you would create concrete commands that extend the command interface that is found in the UI package. And your concrete commands keep a reference to a class that contains the business logic, as we discussed, such as a user service. And this contains the methods related to adding, updating, or deleting users. So this is going to be maybe interacting with your database. A simpler solution, so if we didn't use the command pattern, and we sort of come up with a sort of more obvious solution, and this would be to create a load of button subclasses for each place where a button is used. And these subclasses would contain the code that should happen when the button is clicked. So here we have some sort of abstract button class. This might be from maybe the UI framework. And then our code, or in our application, we would then create a load of button subclasses, where each subclass contains the logic that should happen when, for example, a button is clicked. And the problem with this approach is that we could end up with a huge number of subclasses, and this would be okay if there was no risk of breaking the code in these subclasses every time that the base button class is modified. But if we update our UI library, and that includes a breaking change to the button class, then it could break all of our button subclasses. So this is a very fragile solution. And also, some operations such as copy need to be called from multiple places. For example, a user can click the copy button, press Ctrl+C, or right-click and then select copy from a context menu. With this solution, we'd either have to duplicate the copy logic in multiple places, or make shortcuts and context menus dependent on buttons, which is a very bad solution. So the command pattern solves this issue by essentially breaking the app into layers, following the good software design principle called the principle of separation of concerns. So the command pattern has broke the app into two layers. We have the GUI and the business logic. And the GUI is responsible for rendering things on the screen, capturing user input and showing results. Then when it comes to the important stuff, such as validating the info from a contact form and sending an email, the GUI delegates that task to the underlying layer of the business logic. So if we have a look at the gang of 4 UML, you can see here that we have our light class, or our sort of button class. This will be called the invoker class in the gang of 4 book. We then have our command interface with some sort of execute method. And we usually, I think, have a single execute method in the sort of command interface. Then each command will implement this command interface and have a execute command. And then we have a receiver where the concrete commands sort of delegate the work to this receiver class. And we can see that the invoker is completely decoupled from the receiver, and this provides us with lots of flexibility because we can now use polymorphism to pass different command objects to the invoker, and the invoker needs no specific knowledge of the command that it's being passed. Another advantage of the command pattern is that it gives us the ability to implement undo functionality. So for example, say we have a text editor like VS Code that allows the user to highlight some text, then the user could click a button and make some text in the HTML document italics, which just means slanted. So here we have the UML diagram for implementing this undo functionality. So above we create a new interface called undoable command, which extends the command interface. And this is because all undoable commands are still commands. They're just special types of commands that can execute both forwards or backwards with the execute and unexecute command methods. So why not add the unexecute method to the command interface itself? Well, it's because not every command is undoable. For example, making text italics is undoable, but saving a document or zooming in or out is not. And if you can remember the solid interface segregation principle, it basically states that classes should not be forced to implement methods that they do not need. So it's much better to create this separate undoable command interface. So we then implement these methods in the concrete command classes. So for example, here we have an italic command which implements both the execute and unexecute methods from the undoable command interface. Okay, so we can also use the Memento pattern, which we discussed earlier, to implement undo mechanisms. But what's the difference between Memento and the command pattern when it comes to undo operations? So with the Memento pattern, if you can remember, we store the changes in the state of an object. So in other words, we store multiple snapshots of the state over time. And sometimes storing these snapshots can be expensive. For example, videos are large files that take up lots of memory. And in those situations, it's better to use the command pattern because every command knows how to undo itself. So we don't have to store multiple snapshots of an object. For example, think of the resize operation. If a user resizes a video, we only have to store the previous dimension of that video. We don't have to store the entire snapshot of the video object. So here's how we will implement the command pattern with undo capability. So here we have some slightly confusing UML, but we have an undo command, a new class called undo command that we have created to handle all undo operations. So the way this works is that it pops the last command from history and then calls the unexecute method on that command, as all commands know how to unexecute themselves. So this is kind of confusing to talk through and just look at the diagram. So it's going to make much more sense when we go through this in code. So let's do that. Okay, so I have created here an undoable folder where we're going to put our code solution in here. So first of all, let's create a HTML document class. So in this class, this is where we are going to implement our business logic. So this class will know nothing about commands. It's simply the business layer of our application. Okay, so let's first of all create a property for the content of the HTML document, and we will have a getter and a setter, and we'll also include here now a public void make italic method, and this is where we're going to have our business logic. So basically the HTML document knows how to make itself bold. So what we can do in here is we can set the content equal to the content wrapped in HTML italic tags. Okay, like so. So what we will do next is we will create the command interface with the execute method. And we'll also create the undoable command interface, which extends the command interface. And this extends command. Okay, so that means that it gains the execute method from command, and we will also add an unexecute method. And undoable command extends command, which means that every undoable command is actually also a command object. Okay, so next up we're going to create our command history class, which is a class that's going to keep track of the commands that we've applied. So let's create that class called history. And in here we're going to store a list of undoable commands. And we'll just call this commands. And we will set it equal to a new list. And then we're going to create a push method. So we're going to create a few methods which will allow us to easily interact with the history class. So we'll create a method called public void push. And this is going to take an undoable command. And we can just call commands.add command. And we'll also create a pop method for removing the last item on the commands list. And this returns that last item. So we get the last command from the list, then we remove it from the lists. And then finally we return it. Okay, so we pop it off the list and remove it from the list, then we return that last item. And we're also going to have a method called size for getting the current length of the commands list. And this is going to be useful in another class a little bit later on. So let's create this. And we just want to return commands.count. Okay, so what we're going to do here with this size method is we just simply check that we have some commands in the commands list, and if we do, then we can unexecute them, for example. So that's why we are using this. We're sort of adding in this size method. So what we can do now is we can create our concrete italic command class. So let's go ahead and create a new class called italic command, and this needs to implement the undoable command interface. So let's implement that interface. So we have an execute method and an unexecute method for undoing the command. So we need some fields up here. So we need to store reference to the HTML document. So let's store a reference to that. We also need a field for the previous content. And we'll initialize that to an empty string. And we also need to store reference to the history object. Okay, so we're going to need to create a constructor now to set these values. And what we need to do is we need to pass the history object as well. Okay. And then we can implement our execute and unexecute methods. So when we execute, what we want to do is we need to get the current content in the HTML document and set it to previous content. We can then make the document italic, and we can push this command object, so this command object, onto the history class. Okay, so we are getting the current content from the document, storing it into previous content. We then make the document italic, and then we push this command object onto the history list. So let's do that. So we can say previous content is equal to doc.content. And then we can say doc.make italic. And we are delegating this work to the doc business object. Okay, so we're not doing this work within the command, we're delegating to the document business object. And then we call history.push. And we want to push this command onto the history list. Now for unexecuting, all we need to do is we call doc.content equals previous content. Okay, so we go back to what the content was before we executed the command. So that's pretty straightforward. But we're now going to create a new class called undo command, and this is going to sort of manage all of the undoable commands. So this is going to make more sense shortly, so stick with me. So let's create a new class called undo command, and this is going to implement the command interface. And what we need to do here is we need to store a reference to the history class, and we can pass this into the constructor. So in the execute method, what we want to do is we want to check if the history has any commands in its list. So if it does, then we can pop the last item, the last command off of the list, and then we can call its onExecute method. So let's do that. So we can say if history.size is greater than 0. So if we have any commands on the list, then what we can do is we can pop the last item off the list. And we want this should be history.pop. And we can say last command dot execute. Unexecute. Okay, so we unexecute the command. And again, here we are delegating the this undo logic to the undoable command object. So this is going to make a little bit more sense when we actually use this solution. So let me show you how this is used in a client. So first of all, let's create a HTML document. And let's also create our history object. And we don't need that. And let's set the HTML document's content equal to hello world. And let's just log what the content is. Okay, so let's run this program, see what we get. And we get hello world as expected. So what we want to do next is let's try and make the content italic. So to do that, we can create an italic command object. And we pass in the HTML doc and the history object. Okay. We can then call the execute command on the italic command. The execute method on the italic command. So let's actually log the content now. So we would expect this hello world to now be wrapped in italic HTML tags. So let's run this and see what we get. And as you can see, it's working correctly. So it's executed the italic command and made the content in the HTML document italic. So the last thing we need to test out is the undo command. So what we can do here is we can create a new undo command. So undo command equals new undo command. And in here, we need to pass the history object that we are working with. And we can call undo command dot execute. And then we can log the content. So we would expect the content now to have no italic tags around it. So you can see here that we are back to having just regular text that isn't italics. Okay, so that's pretty good. So you can see here, let's have a look at this undo command. So undo command that we call undo command.execute. So if we have a look at this execute method, we are getting the last command from history. So if we have a look at our history, first of all, we create this new italic command, which is an undoable command, and we call execute. And when we call execute, this command is going to be pushed onto the history class, the history list. And then when we call the undo command, it essentially pops this command that we just executed off of the history and calls unexecute on this command to essentially revert the content to what it was previously. So when should you use the command pattern? So you can use the command pattern when you want to implement reversible operations. The command pattern is probably the most popular pattern for implementing the undo or redo functionality, and it uses less RAM than the Memento pattern, which has to back up the whole state of the object. And the command pattern is great when you want to queue operations or schedule their execution, as command objects can be serialized, which just means converting the objects into strings, and then you can store them in databases or send them over networks. Then at a later time, these can be converted back into objects and executed. So what are the pros and cons of the command pattern? So first of all, it satisfies the single responsibility principle, as classes that invoke operations are decoupled from classes that perform these operations. It also satisfies the open-close principle, as new commands can be added to the code base without having to modify existing code. One of the negatives or cons of the command pattern is that code can become more complex as you're adding a new layer between senders and receivers. So if your program is fairly simple with not too many operations, then using the command pattern can be overkill or over-engineering. The template method allows you to define a template method or skeleton for an operation. The specific steps can then be implemented in subclasses. So suppose we are designing some software that will be installed on a machine that makes hot beverages. At the beginning, we just had tea and coffee, but after some feedback from customers, we needed to add some more beverages, such as chamomile tea. So we started out pretty simple, making a separate class for each hot beverage. But as the number of beverages grows, we see a lot of code duplication. So if we have a look at this example here, we have tea, coffee and chamomile, each with a make beverage method. And we can see inside of the make beverage method, we are calling the boil water method and a pour into cup method. And these methods are actually, or these steps are used in tea, coffee and chamomile. In fact, they're used in all beverages. All hot beverages require boiling water and pouring that water into a cup. But we also have some methods that differ between the different beverages. For example, the brew method may require different amounts of time, and the add condiments method will differ as well, because different beverages will require different condiments. For example, tea, it might be possible to add, say, milk and lemon, whereas with coffee, it may be possible to add cream. So one of the issues is with this solution is that as the number of beverages grows, we see a lot of code duplication. So we are duplicating this boil water and pour into cup logic in each of the beverages. And we also have no way of ensuring that each class follows a particular structure, which means that the client code will have to include lots of if-else conditional statements to pick the proper course of action depending on the particular beverage class. So I have made a tea class, and we're just going to add some methods for boiling water, pouring the water into the cup and brewing the tea. So we also need a method to see if the customer wants condiments, and then we need to add those condiments to the beverage or to the tea. So let's create a method called add condiments. And what we're going to do here is we're going to check if the customer wants condiments. So we're actually going to create a method called customer wants condiments. And if they do, then we're just going to add some lemon to the tea. So let's create this customer wants condiments method. And this is going to be a method that returns a Boolean value. So what we're going to do is we're going to log to the console a question. So we're going to say, would you like lemon with your tea? And the user is going to be able to input yes or no. Okay, so now what we need to do is we need to read the user's input from the console. So we can say console.read line. Okay, and then we can simply return the input dot to lowercase. So we take the user input, so it should be either a Y or a no, and we make it lowercase, and we check if it is equal to yes. So if the user inputted Y for yes, then this will return true, meaning that the customer wants condiments, and so we add some lemon to the tea. Okay, so pretty straightforward. So now we just need to make one final method, and that is going to be called make beverage. And this is where we basically call all of these methods in the correct order to make the tea. So I'm just going to paste those in to save some time. Okay, so we boil the water, pour it into the cup, brew the tea, and then check if the user wants condiments, and if so, we add them to the tea. So pretty straightforward. So let's actually go ahead and test this out. So let's clear out our program.cs file, and we're going to create a new tea object. And we're going to call tea.makeBeverage. Okay, so let's see how this works. So we have boiling water, pouring water into cup, brewing tea for 3 minutes, and then it says, would you like lemon with your tea? So if I input Y, whoops, so if I come into the console, Y and enter, let's see what we get here. Okay, so it says adding lemon to the tea. So this is working correctly. If I say put no, so N, let's see what happens. Okay, nothing happens, so that's perfect. Okay, so this is working correctly. So now let's also go ahead and create a coffee class for creating coffee beverages. So okay, so let's now also create a coffee class for making coffee. So what I'm going to do is I'm just going to paste in these methods for making coffee just to save some time, because it's largely the same as the tea class. So as you can see, we have boil water, pour water into cup. So these methods are identical to the methods in this tea class. And then we have the brew method, which brews the coffee for 5 minutes. So slightly different to brewing tea. And we also have the add condiments, where rather than adding lemon, we add cream to the coffee. So we can see that we have two methods that are identical to the ones in tea. So the issue is that the more of these beverages that we create, we're having a lot of code duplication. So there are two good ways to solve this issue of code duplication, and they are polymorphism and inheritance. So first of all, we're going to use polymorphism, which actually leads to a design pattern that we covered earlier. So let's see if you can spot which design pattern that is. So here we have our solution using polymorphism. So here we provide a common beverage interface to force all concrete beverages to follow a specific structure. We then have a beverage maker class that manages preparing the different beverages. And this beverage maker class includes the common operations for making all beverages, such as boiling water and pouring it into a cup. And it also includes operations specific to each beverage. But these operations are delegated to each of the concrete beverages. So this beverage maker actually talks to or is coded to a beverage interface, meaning that we can use polymorphism. So we can pass different concrete beverages into the beverage maker, and then this beverage maker can simply call beverage.prepare. It doesn't actually care about the specific concrete beverage class that's been passed to it, because it's coded to an interface, it can just call prepare. So we are essentially using polymorphism to make things nice and flexible. And so now when we create a new beverage, so if we get some more feedback from a customer that we need to, and we want to add a new beverage, we want to start selling a new beverage, then we can just create a new concrete beverage class that implements the beverage interface. Okay, and we only have to include in these concrete classes code that is specific or unique to that beverage, because the sort of shared code is placed inside of this beverage maker class. So by using polymorphism here, we have inadvertently used the strategy pattern. So you can see here, this is the strategy pattern UML, where our context object is the beverage maker, and we have a strategy interface, and in our case this is the beverage interface, and then our concrete strategies are our beverages. Let's now implement this strategy pattern or polymorphism solution into code. So first of all, I'm going to create an interface called beverage, and I'm going to add a prepare method. Okay, so now let's create our T class that implements the beverage interface. So this beverage interface is kind of like our command interface, our strategy interface. Okay, and then we're going to create our concrete strategies, which are basically our concrete beverage classes. So first of all, let's create the T class, and this is going to implement the beverage class. So let's implement this interface, and what I'm going to do is I'm just going to copy and paste in some of the methods that we had before. So we had the brew method and the add condiments method, and also the customer wants condiments method. So let's add those in, and these are the kind of methods that are unique to this specific concrete beverage. Okay, so now what we can do is we can, inside of the prepare method, we can call brew and add condiments. Okay, so if you can remember before, if we go into T, beforehand we also had a boil water and pour into cup method before we called brew and add condiments. But now we are going to create a separate class so that this kind of these two steps can basically be shared between all of the beverages to reduce code duplication. So let's continue, and let's create a coffee class. So this is another sort of concrete strategy class, and this implements our strategy interface, which is the beverage interface. So if we implement that, and I'm just going to copy and paste the brew, add condiments, and the customer wants condiments methods into this class to save some time. And let's see, what did we do here? Okay, so I think that's okay. Yeah. Okay, so now in the prepare method, we can call brew and add condiments. Okay. So we can also do the same for chamomile. So let's create a chamomile class. So this is another concrete beverage, and this needs to implement beverage. And I'm just going to, for chamomile, let's say chamomile is very simple, because all we really have to do with chamomile is put the tea into the cup and brew it. We don't really have to add condiments to chamomile. Okay, So we can just call the brew method. So let's create a brew method, and let's just brew chamomile for three minutes. Okay, so to prepare chamomile, all we need to do is brew it, basically. That's the only specific step to chamomile, brewing it for 3 minutes. So now we can create our beverage maker class, and this is going to contain our sort of shared code. So first of all, we need a field for referencing the particular beverage that we are going to be making. And this is coded to the beverage interface, allowing us to pass different types of beverage into the beverage maker class. And then we're going to need a constructor where we set the beverage. And we also need a set beverage method so that we can easily change the beverage that we want to prepare. And in here, we are just going to set beverage equal to beverage. Okay. So next up, we need a boil water and pour into cup methods. So let me just copy and paste those in. So okay, so these are our shared methods or shared steps. Every single beverage, we have to boil some water and then pour it into the cup. So then what we can do is we can have a method called make beverage. And in here, we can have our common operations. So the operations or steps that every single beverage has to follow. And those are boil water and pour into cup. And then we can call our unique operations by simply calling beverage.prepare. And as you can see, our beverage maker needs no specific knowledge of the particular beverage that it's preparing, because we are coding to an interface using polymorphism. We can just call the prepare method, and it will call the prepare method on any of the concrete beverages. Okay, so now if we go into a client and show how a client might use this solution. So first of all, we would create a beverage maker. And in here, we pass the beverage that we want to make. So let's say we want a cup of tea. And we have the beverage maker dot make beverage. So let's see how this works. Okay, so boiling water, pouring boiled water into the cup. So those are our shared methods, which are actually inside of the beverage maker class. So you can see here, when we say make beverage, we call these common operations from within the make beverage, within the beverage maker class, and then we call the unique operations. So in this case, we brew the tea for 3 minutes, and then we ask the customer if they would like lemon with their tea. I do, and I get lemon in my tea. Perfect. So let's say we want to now make a coffee. So we say beverage maker dot set beverage, and we can say new coffee, and we can call beverage maker dot make beverage. Now this time it will call the two shared methods, and then it will call the methods specific to making a coffee. So first of all, it's making the tea, so let's do the tea, and then it makes the coffee, and it asks if I want cream with the coffee. Yes, and let's see, it adds cream to the coffee. So this is working perfectly. So let's just summarize what we have done here. So inside of Beverage Maker, we define the common behavior for making a beverage, and that is boil water and pour water into cup. And we have an interface called beverage, and this has a prepare method. And we also have our concrete beverage implementations for chamomile, coffee and tea, all of which implement the beverage interface. And this allows us to treat all beverages the same way in the beverage maker class. And from here, from the beverage maker class, we specify the beverage when we create the beverage maker object, or we can set the beverage here. And then we are delegating or forwarding the execution of tasks related to making a specific beverage to a concrete beverage object. And this is the strategy pattern. So we've just solved this problem using polymorphism, which actually led to us using the strategy pattern. But we could also solve this problem using inheritance. So tea, coffee and chamomile have things in common. So we can create an abstract class called beverage that implements the prepare method. But after we've boiled the water and poured it into the cup, what happens next is unknown in the abstract beverage class, as it depends on the particular beverage. And these beverage specific steps will be determined later on when the beverage class is extended by the concrete classes. So we can provide a base abstract class called beverage that contains all common operations for making a beverage. And we can provide methods called brew and add condiments, which can be implemented or overridden in the concrete beverage classes. So you can see here we have our beverage class with a prepare method, and you can see we have the brew and add condiments methods, which are sort of doled out in grey, which is implying that they are not implemented in this beverage class. They are abstract methods which need to be implemented in the concrete tea, coffee and chamomile classes. So you can see here this prepare method is known as a template method. So it's providing a template for the steps involved for preparing a beverage. So we have the boil water and pour into cup methods, which are defined in the beverage class itself. Okay, because these are our shared methods that are used by all beverages. And then we have brew and add condiments, which are to be defined later on when this beverage class is extended. So this prepare method is acting as a template method. Okay, and this is known as the template method pattern. So the beverage class has a template method that provides the common setup and structure for preparing a beverage. And here's how the template method pattern is shown in the Gang of 4 book. So we have an abstract class with a template method, a public template method, which calls the some abstract methods in a particular order. Okay, so then we have our concrete methods, our concrete classes that implement those methods. And the template method will call those methods in a particular sequence. So we have an abstract class with a concrete implementation of the common shared template method, and the abstract methods that will be implemented within the concrete classes can be used to alter the behavior of the template method. And we can also give the primitive operations a default implementation and leave it up to the subclasses to either take them as they are or override them. In this case, we refer to these methods as hooks or hook operations. So you can see here in this abstract class these sort of methods that are to be implemented in the concrete classes are not doled out anymore. So we're providing a default implementation for these methods, and it is now optional in these concrete classes whether they are sort of overridden. So we have method 1 and method 2 here with default implementations within this class, and we've just decided in this concrete class in particular, in this example, we're just overriding method 1 and leaving method 2 to its default implementation within the abstract class. So we're not going to bother to override it, we're just going to take it as it is. and we refer to these kind of methods as hooks. So let's now implement the template method pattern in code. So here we have our base beverage class, and currently we have our template method with all of the steps involved in creating a beverage. Now if you remember, the boil water and the pour into cup steps are shared between all of the concrete beverage classes. So we can actually implement these two steps inside of this beverage class. So let's copy and paste those in just to save a little bit of time. So here we boil the water and pour into the cup. So those are the first two steps that every beverage has. Now in this template method, we can now provide we need to provide a brew and add condiments methods. So I think for brew, what we will do is we will make it a virtual method. So in fact, actually we'll make it an abstract method, which means that all subclasses must implement this brew method. Okay, so every concrete brew needs to specify how long to brew the beverage for. So what we'll do is we will create a protected, an abstract void brew, and it will just be like this. So we must provide this brew method inside of all of our concrete beverages. Now we can see that we are getting an error because this class now needs to be an abstract class because it has an abstract method. Now let's also create this add condiments method. So the add condiments method, what we're going to do is we're going to create this method with a default implementation. So we will say protected virtual, meaning that it can optionally be overridden in its subclasses. And what we're going to do is we're going to provide a default implementation of an empty body, which basically means that we don't add any condiments by default. Okay, so that's our base abstract beverage class. So now what we can do is we can create the concrete classes. So let's start off with the T class. And T needs to inherit from beverage. And we also need to implement this abstract class. So the only method that we have to implement is this brew method because it's an abstract method. And in here, we can just say brewing tea for 3 mins. Okay. And then optionally, we can provide a add condiments method here. So we can override this default implementation. So this is essentially a hook method. So I think what we're going to do is we'll just copy this from inside of what we did before. So let's copy and paste that in. And what we need to do is we need to say that we are overriding this method from the beverage class. And we have an error here. Let me check. So we need to make sure that this is protected to match the method signature from the beverage class. Okay, so that all looks okay. And just to save some time, I'm not going to make the coffee class, but I'll just make the chamomile class because that is a little bit different to the tea class. So chamomile. And again, we need to inherit from beverage. And then we need to implement the abstract class. So here we'll just we'll say brew chamomile for 3 mins. And this is all we need to do for the chamomile class because chamomiles don't have any optional condiments. So that is everything we need to do there. So let's now have a look at how a client would actually use this solution. So if we go into our client and we create a tea beverage, and let's make sure we're using the correct namespace here. So this is the template method, and we can just call tea.prepare. And then run this program. And we can see we get these are the 2 shared steps, the boiling the water and the pouring into the cup. Then we have our sort of concrete class specific logic here. Brewing the tea for 3 mins, and it asks us, would you like lemon with your tea? And we get lemon in our tea. And then for the chamomile, we can do the same thing pretty much. And there are no optional condiments, so it just makes the beverage automatically without us having to answer any questions. So this is a nice and simple solution for clients to make beverages. All beverages provide a simple API, a simple and consistent API with a prepare method. And the rest of the complexities are abstracted away as the clients require no knowledge of those complexities. Let's now have a look at the differences between the template method pattern and the strategy pattern, as we've just previously used both to solve the same problem. So you can use the template method pattern when you have an algorithm with a fixed structure, but with certain steps that need to be customized or implemented differently by subclasses. And this pattern is ideal when you want to define a common algorithm skeleton, or in other words, the template method, in a base class and allow subclasses to selectively override specific steps to provide their own implementations of those specific steps. And the template method pattern is suitable when the overall algorithm structure remains consistent, but specific parts of the algorithm can vary based on different requirements or contexts. And for the strategy pattern, you can use the strategy pattern when you want to define a family of interchangeable algorithms or behaviors and encapsulate each algorithm into its own class. And the strategy pattern is ideal when you need to dynamically select and switch between different algorithms at runtime, depending on the situation or context. And the strategy pattern is suitable when you want to decouple the client code from specific algorithm implementations, allowing for greater flexibility and extensibility. So in summary, if you primarily need to customize or override specific steps of an algorithm while keeping the overall structure intact, the template method pattern is a good choice. On the other hand, if you need to encapsulate entire algorithms or behaviors as interchangeable components that can be dynamically selected or replaced, the strategy pattern is probably more appropriate. So both patterns have their strengths and are used to address different design scenarios. The choice between them depends on the specific requirements and design goals of your application. So when should you use the template method pattern? You can use this pattern when you want to allow clients to implement only particular steps in an algorithm and not the whole algorithm. It's a good pattern to use when you have a bunch of classes with the same logic or algorithm, but with differences in a few steps. So if the algorithm changes, it only has to be modified in one place, and that is the base class. So the pros and cons of the template method pattern. So the pros, we can reduce code duplication by having the sort of shared logic or methods in the base class that can be inherited. And clients are only allowed to modify certain steps in an algorithm, which reduces the risk of breaking clients if the algorithm changes. And some of the cons are that some clients may be limited by the provided template, and template methods can be hard to maintain if they have a lot of steps. The observer pattern involves an object known as the subject maintaining a list of dependent objects called observers and notifying them automatically of any state changes. So that may not make too much sense to you, so let's go through an example to learn the observer pattern. So here we have an Excel document with two spreadsheets, spreadsheet 1 and spreadsheet 2. And in spreadsheet 1 we have a data source, which is essentially just a 2-column table with city in the left-hand column and number of dogs in each of those cities in the right-hand column. And then we also have a bar chart with dogs on the y-axis and the city name on the x-axis. And this bar chart is essentially built from this data source. And then in spreadsheet 2 we have a sum. So we have one of the cells is basically summing up the number of dogs to get the total number of dogs in all of the cities. So let's first of all come up with a naive or sort of obvious solution to this problem. So we have a data source object which has a list of observers. So the observers are going to be sheet 2, so spreadsheet 2, which is calculating the total number of dogs. And we have a bar chart, which is producing a bar chart from the data source. So here we also have the values of the data source and a getter and setter for getting and setting the values in the data source. Now the problem with this solution is that we have tight coupling to the concrete observer objects, which are spreadsheet 2 and the bar chart, meaning that we need conditional statements to check the object type before we actually update the observers. So this will probably make a lot more sense as we implement this solution in code, so let's do that. So first of all, let's create a new folder for the observer pattern. And what we will do in here, first of all, is create our spreadsheet 2 class. So our sheet 2 will have a field for storing the total. It will also have a getter, which just returns the total. And then we'll have a method for actually calculating the total. And this will take a list of integers. And we'll keep track of the sum in a variable called sum, and we'll initialize that to 0. And what we're going to do is we're going to loop through each value in this values list. And we're going to add it to this sum variable. So we can do sum plus equals value. And then let's just log what the value is. And return the total at the end. Okay, so that's everything we need in this spreadsheet 2 class. So let's now create our bar chart class. And in here we're going to have a single method called render. And this is going to take the list of integer values from the data source. And we're just going to keep it simple and log rendering bar chart. Okay, so obviously if this was a proper bar chart, we'd need to pass in probably an object with keys and values, or some sort of dictionary where we have the key as maybe the city and the value as the value. But we're just going to keep things simple for now and just pass a list of integers because we're not actually going to be drawing a bar chart. So finally we can create our data source class, and this class is going to store a list of the dependent objects, or essentially the observers that rely on the data source, and those being sheet 2 and bar chart, so that when the values in the data source are changed, the data source can update those dependent objects. So let's create the data source. And in here, we're going to have a list of values. So this is kind of analogous to our number of dogs in each of the cities, basically. And we'll create a new list of integers. And we'll also create a list of dependent objects, or our observer objects. And these are just going to be sort of type objects. We're not going to specify the exact type of object, so that we can pass in either bar charts or sheet 2s or any object that needs to be updated when the data source values are changed. So we're going to call this dependents. We could also call it observers, but dependents will do for now. And we'll just initialize that to a list of objects. So next up, we're going to create a getter for the values so that the other objects can get the values. And we just return the values there. And then we'll also create a setter method called setValues. And this needs to be a list of integers. And we just set values equal to values. Now in here, whenever we update these values, we also need to notify our bar chart and sheet 2 so that the bar chart can re-render itself with the new values and sheet 2 can recalculate the total. So what we're going to do is we are going to loop through all of our dependents, or all of our dependent observer objects. So we can say for dependent in dependents, and this needs to be a for each loop, sorry. And in here, we need to check the type of the dependent, the object type. So we can say if dependent is sheet 2, then we can cast the dependent to a sheet 2 object by writing dependent as sheet 2, and this will allow us to recalculate the total. And then in here we need to pass in the new values. Okay, and we also can check if the dependent is a bar chart. And if it is a bar chart, we can then cast the dependent object to a object of type bar chart, and we can call the render method to re-render the bar chart with the new set of values. Okay, so that's actually everything we need to do for this setValues method. But now we also need a way of adding dependents to our data source so that we can actually control which objects are going to observe this data source. So for that, we can create a method called addDependent. And in here, we can pass any object. And we quite simply just add this on to our list. Okay, and we also want to create a method for removing dependents. And in here we can pass the object that we want to remove. And we can call dependent.remove and pass that dependent. Okay, so that's everything that we need in data source. So we have our sheet 2 and bar chart observers, and we also have our data source. So now let's have a look at how we could use this solution in a client. So let's clear this out and create a new data source object. And let's also create our sheet 2 and bar chart observers. And now we need to add these objects to the data source as dependents. So we can call data source.addDependent and pass in sheet 2. So this can be any object. And we can also add our bar chart. Okay. And then what we can do is we can set some values in the data source. And in here, we're just going to pass a simple list of integers. So we can say 5, 5, 1, 10. And let's actually run the program now to see what we get. So we can see here when we called set values, it has actually updated the total in the sheet 2, and it's the total is 21, which is correct, and it's also re-rendered the bar chart with these new values. So if we then call the set values method again, and we just set the values to say 1, 2, 3, run the program, and we should then get a new total, and we should also get the bar chart re-rendered, which we do. So this is all working perfectly. However, there are some issues with this solution. So can you see what solid principles we are violating? So maybe take 30 seconds or a minute to have a look at the solution that we've just come up with and see if you can spot what solid principles are being violated. And the two of the most obvious principles that we are violating are, first of all, the single responsibility principle, because this data source class actually has two responsibilities. It is storing data, so managing data storage, and it is also managing the dependent observer objects. So it has two reasons to change. And we also are violating the open-close principle, because every time that we create a new observer object, we have to modify data source. So if we create, I don't know, pie chart, we then have to modify data source. We have to come in here and check if the dependent is of type pie chart, and then call the appropriate method to actually update that pie chart with the new values. So we are violating the open-close principle. And this is because we are programming to concrete objects rather than to a generic interface. So how do we solve the issues that we spotted in our last solution? So we were violating the single responsibility principle, and we were also violating the open-close principle. So to solve the single responsibility principle, we could actually create a separate class for managing the dependent observer objects. And to solve the open-close principle, we can ensure that all of our observer objects, so sheet 2 and bar chart in this example, implement a common interface so that they provide consistent methods allowing us to use polymorphism in the data source class. So it's now time to introduce the observer pattern. So for the observer pattern, we have an abstract class called the subject, and in the subject we have some methods for managing observers. So this is like our separate class for managing the dependent observer objects. And in here we have a method for adding an observer, for removing an observer, and for notifying the observers or updating the observers. We then have our data source class, which manages the values in the data source, as well as a getter and setter for those values. And we can see here that the data source is inheriting the observer methods from this subject class. We then have the subject talking to an observer interface, which has a single update method. And we can see here that the subject is composed of observer objects. So this will store a list of observer objects. Okay, and you can see here that this abstract subject class is coded to an interface and not the concrete observer classes. And as you can see here, we have our two concrete observers, the sheet 2 and bar chart, which implement the observer interface, allowing us to use polymorphism. Okay, because this subject class, when it notifies the observers, doesn't have to check what type of object we're dealing with, because it knows that they are of type observer. It can just call the update method without knowing the specifics. So this actually This solution now follows the open-close principle, as we can extend our application by adding new observer classes without having to modify the data source class. So for example, tomorrow we may want to add another spreadsheet that finds the average of the data source values, and to do that we can just create a new sheet 3 class that implements observer, and the data class doesn't care, it just talks to the observer interface. And set values in the data source will simply loop through all of its observers and call the update method on each. And this is polymorphic behavior. A different update method will be called depending on the observer, but data source doesn't care, or it doesn't need to know what the specific concrete observers are. Each concrete implementation figures out how to update themselves. So if we have a look at the gang of 4 observer pattern here, we can see that we have the abstract subject class with 3 methods for managing the observers, the list of observers, and we have an attach, detach, and notify. So that's basically the same as what we had up here: add, remove, and notify, or add, detach, and notify. Then we have our observer interface with its update method, and we have our concrete subject and our concrete observers. So very similar to the solution that we have up here. So the observer pattern is also known as the pub and sub pattern, so the publish and subscribe pattern. And the subject, which is the publisher, publishes changes in its state, and the subscribers, or the observers, subscribe to those events. So let's now refactor our code to use the observer pattern. So let's now refactor our code using the observer pattern. So first of all, we're going to create an observer interface. And in here we give it a single method called update. And then we can refactor our concrete observers. So we have bar chart, which needs to implement observer. And we can see here we get a red squiggly line indicating that we have an error because we are not implementing the observer update method. So here we can simply change this method to update, but we still get an error because we are not actually using the same method signature. So if we go into this observer interface, we can see that update doesn't have any parameters. So we need to remove this parameter. But we still need a way of getting the values from the data source. So what we can do, instead of passing them to this update method, we can store a field of type data source and pass the data source object into the constructor whenever we create a new bar chart. Okay, so that's everything we need to do for our bar chart class. So let's now go into our second observer, which is sheet 2. So again, we need to implement the observer interface, and then we also need to implement the methods. So we get an update method here. So what do we need to do in this update method? So I'm just going to move this up a little bit. So let's move it to here. And what we want to do is we want to set the total to the sum of the values. So currently we don't have any way to access the values. So again, let's create a new field for the data source. And we'll pass that via the constructor. And now what we can simply do is set the total field equal to calculate total, and we can pass the values by getting them from the data source object. So here we can just say total is equal to calculate total, and then we can get the values from the data source object, which we have passed into this object. Okay, so that is everything that we need to do for the sheet 2 class. So now what we can do is we can create our subject class, which is going to be the class that manages observers. So let's create that class. And here we need to first of all create a field for keeping the list of observer objects. Okay, so then we need to add our 3 methods for managing observers. So we need a way of adding observers, removing observers, and also notifying all the observers in the list that our sort of source object has changed. So first of all, let's create the add observer method. And then here we pass the observer that we want to add to the list. And we can just call observers.add observer. And then for the remove observer, and again we pass the observer to this method that we want to remove, and we just call observers.remove, and we pass the observer. Okay, and finally we need a way of, we need a method to notify our observers. So here we can see we're getting a suggestion for each observer in observers, and that's what we need to do. And we can just call observer.update. So we can call observer.update. Okay, so here we can see we are using polymorphism to update the observers. This subject class doesn't need to know anything about the actual specific concrete observers that are in this list. It just needs to know that they are some sort of observer, so that we can then use polymorphism and just call the update method. So this is a nice, flexible, clean, maintainable way of notifying the observer objects, even though they may be even though they are different types of objects. So next we need to refactor our data source class. So in here we no longer are managing the observers, so we can remove this dependence list. And let's see, so we have our getValues method, so we want to keep this, okay, because this is used in our observer, in our concrete observers. And the setValue method can now be cleaned up. So we can see before we were storing a list of just objects, and we had to actually check the type of object and then cast it to the type that it was found to be, so that we can could call the update method on that object. So what we can do now is we can actually get rid of this large block of code and simply just call the notify observers method. But we can't do that yet because we actually haven't inherited the subject class. So let's inherit that. And now we will have all of the methods from this subject class. So we've inherited them, which means that we can just call notify observers. So this is much cleaner. And we also no longer need to have these add and remove methods, because this class is no longer managing the observers. So that is much cleaner. So that should be everything that we need to do. So let's now go into the program.cs file and let's change this to observer.goodExample. So let's see, what do we need to do differently here? So we are creating a new data source. So let's see. Let's actually start again here. So we'll say data source equals new data source. And let's create our observers. So we'll create a sheet 2. And And actually this should be our good example, sorry. I'm not sure why we are getting an error here. Let's see. So what did we do here? Let's see. So we're using lowercase s here actually, so let's just use a lowercase s. Actually no, we'll change this here to be correct, so let's correct this. So if I use function F2, let's change that to the correct casing, and then come back into program.cs. There we go, the error goes away. So now for sheet 2, this is our first or second observer, I guess. We need to pass the data source object into here. And we also need to create our bar chart class. And again, pass the data source into that object. And let's see, And what did we do here? Let's see. For some reason I decided to not use, not uppercase the second word. Again, let's see. Okay, so hopefully that fixes that issue. Okay, there we go. So now we can add our observers to the data source object. So let's do that. Okay, so now if we set the values in the data source, it should then notify our observer objects and cause them to be updated. So let's try that. And we're going to pass an array of values, 5, 5, 1, and 10. And let's run this program to see if our observers are notified and updated correctly. So here the sum is 21, which is correct, and we are rendering the bar chart with new values. So if we also, if we change the values now to 1, 2, 3, so let's see what we get now. We can see that the total is updated correctly and the bar chart is rendered with new values. So this is all working perfectly. So we can see here, let's have a look at how using the observer pattern has improved our solution and made it more flexible and maintainable. So if we look first of all in the data source class, we can see that this is now satisfying the single responsibility principle, because data source is now only managing the values. It is not managing observers. The observers methods and the observer list are all managed by this subject class. Okay, so now this subject class has a sole responsibility for managing observers, and a good advantage of this is that this subject class could now be used for any other class that needs to be observed. So this is a much more flexible and maintainable solution. And the second thing that we've done is, because we are now using an observer interface and forcing all observers to implement this observer interface, we can now use polymorphism inside of our subject class. So we can see here that we can simply call observer.update and treat all observers as though they are the same object, without having to check the type of object and then call that correct specific method on the observer. We know that they have an update method because they are implementing the observer interface, and we can just use polymorphism, which makes our solution much more clean and flexible. So we're now going to have a look at the different types of communication styles that can be used when implementing the observer pattern. So beforehand, the observers get notified of a change, but they don't know what has changed. And one solution is to add a parameter to the observer update method. And this is known as a push style of communication, as the subject pushes the changes to the observers. So beforehand, the way that our observers got the values from data source is by actually storing the data source in a field within the class. And then when we need to get the values from data source, we call a method on data source. So a push style communication would be different. So we wouldn't actually store a field for the data source within the observer, and we would actually push the values to this update method. So this update method would have some sort of parameter, and that could be any object or just some sort of generic type for flexibility. So the push style has the advantage that the concrete observers don't depend on or have any knowledge of or coupling to the concrete subject. Okay, so the problem with this solution, with this push style solution, is that what if each observer needs a different set of values? And this is where we could use a pull style of communication, where the observer stores a reference to the concrete subject. Then whenever it's notified of a change, it pulls or queries the data it needs from the concrete subject. And you can see here, this is actually the solution that we used for our example, where we have our concrete observers that keep a reference to the concrete subject. And you can see here, sheet 2 and our bar chart both have a field with reference to the concrete data source object, which is passed in via a constructor. And then whenever it needs any values, it can pull them or query them using this getValues method. So you can see the difference here between push style and pull style. With push style, we are pushing the values to the update method by passing them as arguments. And this means that the concrete observer doesn't need to be coupled to the concrete subject. However, it's not as flexible as the pull style, where the concrete observer keeps a reference to the concrete subject, allowing it to query any of the values that it needs. So again, the concrete observer stores a reference to the concrete subject in pull style, and we give concrete subjects a getValue method so that the concrete observers can get the data that it needs, and this gives us more flexibility. However, we do have coupling here between the concrete classes, but this isn't actually a bad type of coupling. A bad coupling would be between the concrete subject and concrete observer. So if we basically reverse this arrow, and this is because these observers could change in the future, and we may also introduce more observers. And the concrete subject would then have to keep reference to all of the different types of concrete observer. So this would not satisfy the open-close principle, because every time we added a new observer, we would have to update the concrete subject. And we don't want to change our concrete subject class, data source in our example, every time there is a new observer. So in reality, we never have zero coupling in software. What matters the most is the direction of the relationship. And in this case, the direction is okay. So with pull style communication, we pass the concrete subject, the data source, to the observer, just like we did when implementing our observer pattern for our data source with the bar chart and sheet 2 observers. The mediator pattern defines an object called the mediator that describes how a set of objects interact with each other, therefore reducing lots of chaotic dependencies between those objects. So let's go through an example so that you can understand the mediator pattern in an easy, intuitive way. So let's say that we have a blog that lists all of your blog posts, and you can select a post, then edit that post title. So you can see here initially when the page loads, we have state 1, where we have a sort of list of blog posts, and none of those posts are initially selected. So that's the initial state, no posts are selected. And then the user can select an article from the posts container. So this is the post container, and in this case they've just selected post 3, and a sort of text input is then populated on the right hand side of the screen with the title of the post. And then the save button becomes enabled, so the user can then update the title of that post within this text box. And the save button is disabled if no title is provided. So if the user deletes all the characters from this text box, then the post button is disabled, and also if no post is selected, then the save button is also disabled. So you can see here the save button is disabled because no title is provided. So we need some components for this application. So first of all, we have a list box that contains the posts. So this is the list box. Then we have a text box for editing the title and a button that can either be disabled or enabled. And the above classes, list box, text box, and button, will come from a UI framework, so we do not have access to the source code to these UI components. Again, when an article is selected from the list box, the text box should be populated and the button enabled. And when we clear the text box, the button should become disabled. So the question becomes, how do these classes talk to each other? So they should be able to, ideally, be able to talk to each other without knowledge of each other. And one solution would be to use inheritance. So we can see here at the top, we have our UI framework classes that we cannot touch, so we don't have access to these. This is just like an installed package. And we have a list box, text box, and a button class. And then we can extend each of those classes to create our own sort of custom versions of these classes. So we can extend list box to create our own post list box class. Then we have a title text box, which extends or inherits from text box. And same again for button, for the save button. And then these sort of custom classes that extend the UI library classes can then talk to each other like this. So we can see here that posts list box holds a reference to the title text box. Then we can create an onSelect method so that when a post is selected from the list, it calls, it sets the text on the text box and enables the save button. And then within title text box, we have an onChange method. So whenever the user types some characters into the box or deletes some characters, we check to see if the text is an empty string, and if it is, we disable the save button. And we can see in save button, it holds a reference to the title text box, because when the button is clicked, if the button is enabled, then it will get the text from the text box and save it to the database. Okay, so the problem with this solution is that as our form gets more complex, there becomes lots of dependencies or connections between these classes. And also the logic for this form is spread all over the place. It's spread between all of these classes. So to see what's going on in this form, you have to look at multiple classes, and it's very difficult to understand and maintain. So we can solve this problem using the Mediator pattern. And using the Mediator pattern, the UI components don't need to know about each other, as all of the interaction logic is in this dialog box, which is the Mediator. So whenever a UI component changes, it notifies its owner, which is the dialog box, by calling the changed method and passing itself. So each of these components are UI control components, and it passes itself as an argument to this change method, which then handles updating all of the other components. So this will make a lot more sense as we implement this in code. So let's go ahead and do that. So I've created a new folder called Mediator, and then first of all we're going to create our dialog box Mediator class. Okay, so this class plays the role of mediator. So every time a UI component changes its state, it will call its group's dialog box. So this is actually going to be an abstract class. So let's change that to abstract. And we're going to provide a public abstract method called changed that will take a UI control or UI component. And this hasn't been created yet, so we are getting an error. And you might be wondering why this is actually an abstract class and not an interface. And that is because in a real GUI framework, we would provide some concrete methods as well as these abstract methods. So that is why I've created this as an abstract class. So next up, let's create this abstract UI control class. So the abstract UI control class is going to ensure that each UI component gets put into a dialog box. And a dialog box is essentially just a group of UI components. So we're going to need a field called dialog of type dialog box, and we're going to call this owner. So all UI components can be grouped into a dialog box and know and can talk to their owner. So this allows the owner to change other UI components accordingly. So all UI control components need a single dialog box or mediator owner. And we can now create a constructor here where we can pass the owner to the UI control. So we're specifying, which class should be the owner. Okay. So now we have our UI control class. Okay, so next up we can create our concrete UI components that extend the UI control class. So first of all, I'm going to create the listbox class. And this needs to extend UI control. So let's actually generate a constructor to satisfy this UI control class. And you can see here what we are doing is we are passing a dialog box or mediator owner to the listbox constructor and setting the owner in the base UI control class. So next up, what we need to do is a listbox. We need to be able to select a post. So what we'll do is we'll just simply store a private string called selection and set that to an empty string. And then we'll create a couple of getters and setters for setting the selected post inside of the list box. So let's first of all create a getter function or getter method called getSelection, and this will just return the selection. And then we'll have a setSelection, and we will set the selection. And what we need to do here is we actually need to now notify the owner that this class has changed. So if we select a title from the list box, selection will be updated, and we need to let the other components know that this class has changed. So what we do is we notify the owner by calling owner.changed, and then we pass this UI control class or object to the changed method. And then within the owner can see that this list box has changed, and he can then update the other components, so the text box and the button, accordingly. So next up we're going to create the concrete text box class. And this is going to again extend UI control or inherit from UI control. And then we need to generate the constructor so that it satisfies the UI control class. And text box is just going to have a simple text field. Initialized to an empty string. And then we need to create again our getters and setters for this text field. So we set the text, and again we need to notify the owner, which is a dialog box, a sort of mediator class, that this class has changed. So we call the changed method, and we pass this text box object. And finally, our final concrete UI control component is the button. So let's create a class called button, and this is going to extend UI control. We then need to generate the constructor, just the same as before, and a button class just needs to store a field to state whether the button is enabled or disabled. And we need some getters and setters for this is enabled field. And again, we need to inform the owner that the button has changed. Okay, so here again we are telling the mediator that this button object, have changed. So finally what we need to do is create the posts dialog box that's going to contain all of the UI components for our post title editing application. And it's going to update these components depending on which component called the changed method. So that's going to make more sense as we actually create this class. So we're going to create posts dialog box, and this class needs to extend dialog box. So this is kind of like our concrete mediator class. So let's implement the abstract class. So it needs to have this changed method. And what we'll do first is we will create all of our fields for all the UI components. So we need a list box, a text box, and a button. We now need a constructor so that we can pass all of our UI components to this concrete mediator, the post dialog box. So let's create a constructor. And what we're actually going to do is we're just going to initialize them inside of the constructor rather than pass them. So we'll say post listbox equals new listbox. And if you can remember, within each UI control component, we need to actually pass the owner. And the owner is just going to be this. So then we do the same for all of the other components. And also in the constructor, we're going to set the save button to disabled, because initially the save button needs to be disabled. So next up, let's actually add the logic inside of our changed method. So what we need to do in here is we need to check what the UI control is. So if the UI control is equal to a posts list box, or the post list box, then what we need to do is we're going to set the title text box. So we'll say title text box dot set text, and we're going to set that equal to the posts list box dot get selection. Okay, and we also need to enable the save button. And what we should do is we should set enable here. Okay, so you can see that if the UI control is a post list box, so if the post list box has changed, then that means that a post has been selected. So therefore we need to update the title text box with the selected post title, and we need to enable the save button. Okay, so that is pretty straightforward. Then we need another conditional to say that if the UI control is equal to a title text box, so this means that the title text box has changed, so the user has entered a title or deleted some characters from the title. So what we need to do here is we check to see if the title is empty. So we can create a Boolean So here we are checking if the title text box is empty, and then what we can do is we can set we can get the save button and set enabled equal to the opposite of is title empty. So if the title is empty, then the save button will be disabled, whereas if the title isn't empty, then the save button will be enabled. Okay, so that is all the logic we need. However, you can see that this is a little bit bloated, this change method. So what we can do is we can create a couple of sort of helper methods now. So it would be nicer if we could just call handle post changed to handle the post list box changing and sort of abstract this logic into its own separate method. So let's create a private void called handle, and let's capitalize that actually, handle post changed. And we can paste the logic down here, and let's capitalize this. And let's do the same for our text box logic. So handle title changed. And let's cut this and put it all in its own separate method. Okay, so that's a little bit tidier, much clearer what is going on here. And so now that is pretty much everything we need to do. So notice how clear it is now, because all of our business logic for our application is centered inside of this one post dialog box, our sort of concrete mediator. So our sort of logic isn't spread out over multiple UI components. So this is much more readable, much more clear what is going on. So let's now create a method inside of this post dialog box to simulate a user interaction. So what I'm going to do is I'm going to create a method called simulate user interaction. And what we're going to do is we're going to essentially say that the user has selected a post, and the post title is post 2. And we're going to log to the console the title inside of the text box, and we're going to check if the button is enabled. Okay, so this is just a sort of method to simulate a user interaction. So the user selects a post from the post box, and then we're just checking to make sure that the title text box is updated correctly. So this should be post 2, and we're also checking that the button is enabled. So now let's go into our program.cs file and check that this all is working correctly. So let's create a posts dialog box. And then let's simulate a user interaction and run this program. And as we can see, the title text box has been updated correctly. It has been populated to post 2, which is correct, and the button is enabled, which is perfect. So that's all working correctly. So let's also test out that the user enters no title. So if we come back to our posts dialog box and let's set the title to an empty string. So essentially the user has selected post 2 and then they have deleted the title from the post from this title input box. And then if we go to our program.cs file and run this, let's see what we get. So we can see that the title text box is empty, which is correct. And we can see that the button is no longer enabled, so that the user cannot save a post with no title. So this is all working perfectly. So here is the gang of 4 UML for the Mediator pattern. So here we have an abstract class called the Mediator, and this was analogous to our dialog box class in our example. We then have a concrete mediator, so this was like our posts dialog box, which extends the mediator class. We then have an abstract class called colleague. In our case, we didn't make it abstract, and our colleague class was the UI control class. And you can see here that UI control class, or the colleague, is associated to or sort of stores a reference to its mediator, so its owner. And you can see here our UI control, which is our colleague, stores reference to the dialog box or its owner, which is the mediator class. Okay, we then have our concrete colleague classes. So these are, in our example, were our UI components, so text box, list box, and button. And you can see here that we then have our concrete mediator. So this was our posts dialog box, which stores reference to all of the UI components that it owns. Okay, so the concrete colleagues are all unrelated or uncoupled from each other. They talk to each other indirectly via the mediator, allowing them to be reused in different contexts. For example, we are not coupling a list box to a text box or a button. The only coupling that we have is between the concrete mediator and the concrete colleagues. And this is fine because in our example, the posts dialog box needs to know about all of its UI components so that they can interact with each other. The mediator pattern can be used with the observer pattern. So one problem with our previous solution is that the changed method on the posts dialog box can get bulky as we add more UI components, which means that we'll have lots of if-else conditional statements to see what components has changed. So you can see here this was our changed component, and we're checking what type of UI control has changed, then handling it accordingly. So you can see how this can get bulky as we have more UI controls in our dialog box. So to solve this, we can actually implement the mediator pattern using the observer pattern. So let's just remind ourselves of what the observer pattern looks like. So we have an abstract class, or which is called the subject, and this has 3 methods. So we have an attach, detach, and notify. And this subject class will sort of manage a list of observers. And then we have our concrete subject, which is the class which is being observed. We then have an observer interface, which has a single update method. And we then have our concrete observers, which implement this observer interface. And each of these observers has an update method for updating the observer whenever the concrete subject has changed. And whenever it changes, the concrete subject calls this notify method. It loops through all of the observers and calls this update method on each of the observers. So below now we have the UI controls, which are our subjects. So we have list box, text box, and button, and these are our subjects. Okay, so these are the components which are being observed. And we then have our posts dialog box in the middle here, and this is the observer. So whenever a UI control changes, the posts dialog box gets notified. So let's actually implement this in code so that it becomes clear what is going on. So I've created a new folder called Mediator with Observer, where we're going to create our new solution with the observer pattern. So let's also create a folder called UI Framework, and this is essentially going to be the code that we would not have access to within our application. So it's some sort of UI library that we have installed. And within here, I'm going to create a delegate called Event Handler. So I'm going to first of all create this as a class, and then we will modify it into a delegate. So let's remove all of this. And this needs to be a delegate. And we need to return void. So in C# we can use delegates to specify what an event handler or a callback method should look like. So here we're saying that event handler methods should return void and receive no arguments. And just stick with me because this doesn't really make much sense just yet, but it will make more sense as we develop this solution further. So next we're going to create the UI control class, which is our subject class from the observer pattern. So let's just extend this out a little bit. And we're going to create a class called UI control. And yeah, as I said, this is the subject class from the observer pattern. So this is going to basically manage our event handlers. So it's going to keep a list of callback methods for updating the other UI components when a user interacts with them. So let's create a list of event handlers. And we're going to need a method for adding event handlers to this list. Okay, so we add the event handler onto the list, and we also need a method for notifying the event handlers. Or calling the event handlers, I should say. So we're going to call this notify event handlers, and we are going to loop through all of the event handlers, and we're just going to simply invoke each event handler method. Okay, so let's just call this handler. Okay, so just to sort of explain what we're doing here. So each UI component is going to extend this UI control class, meaning that we can add certain event handlers to each UI control component. And whenever, so for example, the posts list box, what we can do is we can give it or add an event handler to this component. And then whenever the post is selected, we can call this notify event handlers method, which loops through all of the methods and calls them. So in our case, the posts, whenever a post is selected from the post list box, it should update the title text box and enable the button. So again, this is going to make more sense a little bit further down the line, so just stick with me for now. So now what we're going to do is we're going to create our concrete UI components. So first of all, let's create the list box. And this needs to extend UI control. And now what I'm going to do is just copy and paste the code that we essentially had before. So here we have our selected post, we have our getter, and we have our setter. And whenever we set the selection, we are calling this notify event handlers method, which we get from UI control. So now let's create our text box. And again, we inherit from UI control. And I'm just going to copy and paste this in because, again, it's the same as what we had beforehand. Okay. So again, we can set the text, get the text, and whenever we set the text, we are going to notify the event handlers that have been attached to text box. And our final concrete UI component, the button class, which inherits again from UI control. And again, I'm just going to copy and paste this in because it is the same as what we had beforehand. Okay. So again, we have our set enabled method, which notifies the event handlers or invokes the event handlers that are attached to the button. Okay, so now that is basically all of the code that we need for our UI framework, or the code that we have basically downloaded or installed that we don't have access to. So now we can actually create our custom code, which is going to be our posts dialog box. So this is essentially now our application. So we've basically installed this framework, and now we are going to use this framework. So in posts dialog box, so I just want to mention actually before we create any more code, that post dialog box is now going to be both a mediator containing all of the business logic for how UI components should interact with each other, as well as being an observer, which receives notice whenever a UI component changes. So it's now both a mediator and an observer. So first of all, let's declare the fields for the UI components. And we can see here we need to import these classes from our UI framework folder. And then I'm going to create a constructor where we can initialize these fields. Okay. And now what we need to do is we need to add our event handler methods to each UI component. So before we do that, we actually want to add our methods for handling events. So if we have a look at what we did before in the Mediator example, if we go to our posts dialog box, we have our handle post changed method, and we also have a handle title change method. So let's copy and paste those in. Okay. Because these are going to now be our event handlers, okay, that we can attach to each of these UI components. So now what we can do is we can call posts list box, add an event handler, and the event handler that we want to add is the handle post change event handler. Or let's give it a better name of post selected. Okay. And let's also add an event handler to the title text box. And I'm going to change this to title changed. Okay. So that's pretty clear what's going on here. So as you can see, if we compare this to beforehand in our post dialog box, we had to check which UI control had changed. Whereas now, because we are just adding event handlers to each of the UI controls, we no longer need to check which UI control has changed. So it's a lot tidier. And as we add more components, this is going to be a lot cleaner than the solution that we had beforehand. So now what we can do is add a method to simulate a user interaction. So let me copy and paste that in to save some time. So here we go. So what we're doing here is we are simulating a post being selected from the post list box, And we're then going to log out to check whether the title text box and the button has been updated correctly. So now let's go into our program.cs file and test all of this out. So let's create a posts dialog box. And this should be posts dialog box. Mediator with observer. And we then need to simulate a user interaction, so we can call that method. And then we can run the program to test that all of the components have been updated correctly. And as we can see here, the title text box is post 2 and the button is enabled. So let's come back into our post text box now and basically simulate the user deleting the title and check that our other components have been updated correctly. So as you can see, the title text box is now empty and the button enabled is false, which is exactly as it should be. So let's now just take a quick look at what we have done to summarize what is going on here. So you can see here in our post dialog box constructor that we set our components equal to our UI components, and then we are adding event handlers to each of the UI components. So let's have a look at this post list box. We add an event handler called post selected, and if we take a look inside of our list box, we can see that whenever we set a selection, we are calling the notify event handlers method, which comes from this UI control component, and this method loops through all of the event handlers that we attached. And if you remember, in post dialog box we just attach this post selected method, and what we do is this method is then invoked. So you can see here we call this method, and this method then updates the title text box and the save button accordingly. So this is great because we have now combined the mediator pattern with the observer pattern and reduced the ugly bulky conditionals that we previously had in the post dialog box. The chain of responsibility pattern allows building a chain of objects to handle a request. A request is passed through a chain of handlers, each capable of either handling the request or passing it to the next handler in the chain. So to understand this, let's go through an example where we first create a simple naive solution, then refactor it into something more maintainable using the chain of responsibility pattern. So let's say that we have a web page that contains some information that only admins of the website can access, such as a page that allows an admin to manage the website's users. For example, create new users, get information, update user information, etc. So say that a user makes a request to the website server, but before returning the web page, the user's data must be validated. So for example, we could trim any white space around the user entered data. We need to authenticate the user. So for example, check their username and password are correct, and then log some information onto the server about this request. And if any of those steps fail, then access denied is returned to the user. So here is an illustration. So we have the user's request here, which goes to the server, which validates, authenticates, and logs some information. And if any of these steps fail, so if the authentication fails, then the user, then access denied is returned to the user. Otherwise, we can return the web page to the user. So let's now code up a straightforward solution for this example. So I've created a new folder called Chain of Responsibility for this example. We're going to first create the HTTP request class. So in here we need four fields. So the first two fields are going to be the user input fields, so that they are going to be username And we're also going to create a second field for the password of the user. And these are going to be sent with the HTTP request. And we're also going to provide a couple of other fields. So these are actually going to be C# properties. And the first one is going to be validated username. And that needs to be a string. And the second one is going to be validated password. Okay, so when the username and password pass through validation, then these fields will be populated with the validated username. For example, if username is a string with some white space at the front, then the validated username will just be this without the white space. Okay, so it's essentially cleaning up the user input data. So let's also create a constructor so that the username and password can be set. And we'll also create a getUsername method. And also a getter for the password. Okay, so that's everything we need in our HTTP request object. So let's also create a class for the validator now, which is going to validate our user input data that is attached to this request object. So let's call this validator. And we'll have a method called validate. And this takes the HTTP request object. And let's actually get the username and password from the request object. And let's also get the password. And then we're just going to do some simple validation. And in this case, we're just going to trim the white space around the input strings for username and password. So to do that, we can call username.trim and password.trim. And then we can set that to the validated username and validated password on the request object. Okay. So that's all we need to do in our validator class. Now for the authenticator. So once the request has been validated, we can pass it to the authenticator class. So let's create that class now. And let's get the username and password again. And we're just going to keep it simple here, and we're just going to check if the username is equal to Danny and the password is equal to 123. And if so, this will return true, meaning that the user has been authenticated. Okay, so that is everything we need for the authenticator class. And finally, the final step, once we've been through validation and authentication, we can perform some logging. So let's create a new class called logger. And in here we will provide a single method for logging to the console. Okay, and finally we need to create a web server class. So let's go ahead and do that. And this needs to have a method called handle, which is going to handle the request. So let's go ahead and create the handle method. And this is going to take a HTTP request. Okay, so now what we can do is we can actually put everything we have done together. So first of all, let's validate the request. And we can call the validate method on the validator. And we can pass the request. So that will populate the request object with the validated username and password. So in our case, we're just trimming the username and password. And we can now create the authenticator. And for this, we can call authenticator.authenticate. And again, we can pass the request object. So in a sort of real web server, we perhaps do something like throw an error if the user wasn't authenticated, or maybe we could return a web page with access denied, something like that. But just to keep things simple for now, we're just going to call the function, call this authenticate method, and not worry about whether it's true or false. Okay, and then finally, we're going to create a logger object, and then we're just going to log. And in here, we pass the request object. Okay, so that's everything we need for now. So now let's have a look at how we would actually use this solution in a client. So first of all, let's create our web server. And let's also create our request object. And it should be this one. And I'm going to pass the username and password into this. So this is kind of like our user input data, or perhaps some data that was stored in the user session. And this is the username and the password. And in this case, this would actually authenticate the user, because we want to check if the password and username is Danny and 123. And it is in this case, so that would be an authenticated user. And then we can call the server.handle method, and we can pass the request object. So let's run this and see what we get. Okay, so everything seems to be working okay. The log file has logged to the console, so that all seems to be working okay. Now this seems like an okay solution. It's pretty straightforward. However, there are some problems with this approach. So with this solution, the order of operations, so if we go into our main sort of web server class, which brings everything together, we can see here that the order of the operations, so we have validate, authorize, and log, are hard-coded inside the web server class. So if in the future we wanted to disable login or authentication for certain scenarios, certain routes, certain web pages, we cannot do so. We'd have to come back and modify the code in the web server class itself. And this violates the open close principle, because if we wanted to change the order of the steps or add an extra step, we'd have to modify some existing code. And the chain of responsibility pattern solves this, as we can build a pipeline with a chain of objects for processing a request. And the request can be of any type, not just a HTTP request. Another issue with this solution is that because of the new keyword, so you can see here we're using the new keyword 3 times within this method inside the web server class. We can see that the web server class is tightly coupled to these concrete validator, authenticator, and logger implementations. So to solve this, we could extract interfaces from these classes and have our web server talk to iAuthorizer, iValidator, and iLogger interfaces. And this would make our web server class more flexible, because if we wanted to use a different type of validator or a different type of authenticator, we could then pass that into the web server so that it's not sort of tightly coupled to these concrete implementations. So let's now try to solve the problem using the chain of responsibility principle. So instead of having all of our request processing logic inside of the webserver.handle method, we can create a processing pipeline or a chain of objects. So here you can see that we have our incoming request, our HTTP request, and then we have a sequence of objects. So first of all, we have the validator, which validates the request, and then this points to the authenticator and passes the request to the authenticator, and if it's successful, the authenticator points to the logger and passes the request onto the logger, and if that is successful, then the user can be directed to the web page, or the web page is returned to the user. So here, each object only knows about the next object in the chain. So for example, validator only knows that the next object in the chain is authenticator. It doesn't know anything about the logger object, for example. So first, a request is passed to the first object in the chain, which in our case is the validator. And if this request is successful, it passes the request to the next object in the chain. If it's not successful, it will stop processing right there, so that the other objects aren't used. So here's the UML for the chain of responsibility solution. And you can see here we have our web server, which has a handle method, which takes the request. And a web server is composed of a handler, which is an abstract class with a setNext method for setting the next handler. So for example, validator, we would set the next handler as authenticator, and then for authenticator we would set the next handler as logger. And each handler needs to implement a handle method, which takes a request object. Okay, so we have an abstract class called handler that has a reference to itself. So it has a field called next of type handler. So with this, each handler can know about the next handler in the chain. And this is essentially a linked list data structure. And the handle method is an abstract method because at the time of implementing this class, we don't know how to handle a request. We determine or implement this in our concrete handlers, which are, in our case, validator, authenticator, and logger. So web server has a reference to the first handler in the chain. Okay, and that is the validator. Okay, so when the web server sees the request, it can pass the request to the first handler in the chain, which in our case would be the validator handler. So you should also note that web server is not talking directly to the concrete handlers, it's talking to a handler interface. So it's completely decoupled from the concrete implementations of handlers. And this satisfies the open-close principle because if we want to, for example, remove login, we don't have to go to the handle method on the web server and change its implementation. Also, if we want to add a new process, we can create a new class that extends handler, then add it to our chain. We extend the code, but we don't modify any existing source code. So here is the Gang of 4 implementation of the chain of responsibility pattern. So we can see here we have our abstract handler class, which has a next field of type handler. Okay, so which is the same type as itself. And we also have a setNext method, which takes a handler, and this is how we can set the next field. And we also have a handle method, which takes a request object. And in this handle method, we can see that we check if next is not null, then we call the next handler's handle method and pass the request. We then have our concrete handlers, which inherit from this handler abstract class. And then we have our client here. So this is how our client can create a chain using this solution. So we can see here we're creating a handler 1, handler 2, handler 3. And these are concrete handlers that it's creating here. So handler 1, handler 2, handler 3. You can see we're using the new keyword. And then we can set up our chain. So we can call h1, so handler1.setNext. And what comes after handler 1? It will be handler 2. So we pass handler 2. And then for handler 2, we call setNext and pass handler 3. And then to initiate the request, we get our first handler and call the handle method and pass the request object. So let's now implement this solution in code. So first of all, let's create the abstract handler class. So first of all, let's create the abstract handler class. And this needs to be an abstract class. And we need to store a reference to the next handler in the chain. So let's create a field of type handler, and we'll call this next handler. Okay, so let's create our setNext method as well. And this is going to return a handler as well as accept a handler. And we're just going to set the next handler equal to this handler. So why would we actually return a handler from this setNext function, or method I should say? Well, the reason for that is because returning a handler from this setHandler method allows us to link handlers in a convenient way. So for example, we could call handler 1, so h1, and if it lets me do it, let me just do it as a string, so h1, and it will be setNext, and we could pass h2 in here, so handler 2, and then because this setNext method is returning the handler, we can then simply just keep on chaining the setNext methods, and very conveniently can create our chain of responsibility essentially. Okay, so we can do it all sort of on one line rather than having to do it on multiple lines, so it's nice and convenient. And that is why we return handler from setNext. And if that doesn't make sense, it will make more sense when we actually use this solution in the program.cs file. So bear with me for now. So next up, we want to create our sort of handle template method. So let's go ahead and create that. And this is going to take a HTTP request. So what we want to do now is we want to have an if statement. So we're going to say if do handle request, and this should be do handle, and we're going to create this method in a second. So if do handle request, then we can return from this handle method. So what this essentially means is if do handle returns true, we return early and the request processing ends here. Otherwise, we are going to check if the next handler is not equal to null, then we are going to call the next handler .handle method and pass along the request object. So now let's actually create this do handle method. So this is actually going to be an abstract method that returns a boolean and takes a HTTP request object. Okay. So this do handle method is going to be implemented in the concrete handlers. So this is going to make more sense shortly. So again, bear with me. So let's now create the concrete handler classes. So first of all, let's create the validator. and this needs to extend the handler class. So let's implement this abstract class. So we need to create this doHandle method. And in here, we're essentially doing what we did before. So we get the username and the password from the request object, trim the white space, and set the appropriate fields as we did before. Okay, now this time we also need to return a Boolean value. So what should we return here? So returning false means that we are not done processing the request, so the next handler in the chain should be called, and returning true ends the request processing here. So in this case we should always return false, because there's no reason for the request to stop processing at this point. So here we can simply return request. Actually, what we can do is we can return true if the validated username or the validated password are empty strings. So if the user provides an empty string for username or password, then we will stop the processing here, and the user will not go through to the web page essentially. So let's go with that. So request.validated username equals empty string, or request.validated password equals empty string. So essentially, if we return false here, then we are not done processing the request. So if the user has provided a username or password, a username and password, then we will continue processing the request. Otherwise, the request ends here if the username or password is not provided. Okay, so now let's create our authenticator class. And this again needs to inherit from the handler. And for this one, I'm just going to copy and paste in what we had before. So you can see here, if the username equals Danny and the password equals 123, then this in the brackets will be true. However, true would mean ending the request. So what we actually need to do is stick an exclamation mark to negate, or make this the opposite of what the result in the brackets is. So if the username is Danny and the password is correct, then we actually are going to return false, and the request will continue on to the next handler. Okay, so that's what we want to do here. And just to remind you why that is the case, it's because in this sort of template method, this handle method, we are checking if doHandle is equal to true, and if it is true, then we end the request. Okay, so if we want to continue to the next request, the next object in the chain, then we need to return false from this doHandle method. So that's how that works. And finally, we're going to create our logger object. And again, we need to extend the handler class and implement all of the methods. And this is a very simple method. All we're going to do is log to the console and just return false to continue with the request. So essentially this means that this sort of step in the chain can never fail. Basically, it's a sort of fail-proof handler. Okay, so now let's have a look at how we code up the web server class. So let's create the web server class. Okay, so in here we need to store a reference to the first handler in the chain. So let's do that. And we can pass the handler in the constructor. Okay, so let's also provide a handle method. Just like we did before, it takes a HTTP request and we're just going to call handler.handle, and we pass that request object. Okay, so now let's actually use this solution in the client. So let's get rid of all this, and we can say var validator equals new validator. Let's see, I think it should be this one. Yeah. And let's also create an authenticator. Authenticate. Sorry, having some spelling issues there. And logger equals new logger. Okay, so now what we can do is, if you remember when I mentioned earlier that we are returning the handler from the set next method, and because we're doing that, we can just chain everything together in one line. So we can call validator. Now this is going to be our first object in the chain, and we're going to set next. So the next object needs to be the authenticator, so that's our next step in the chain. And because the set next is returning a handler, we can just chain on the next handler, and that is going to be the logger. Okay, so we can do that all nice and conveniently in one single line of code. Okay, so now we can create our server, and we pass the first step in the chain, the first object in the chain, which is validator in our case. And then let's create a HTTP request. And that's not what we want. Let's see. I think we actually need to create this HTTP request object inside of our new good solution folder. So let's actually let's create this HTTP request object, because we forgot to add it to this new good solution folder. And this is actually going to be the same, exactly the same as what we had beforehand. So let's copy and paste everything that we have inside here, and we'll paste it inside of here. So hopefully that fixes the issues that we had before. And in here we need to provide a username. So first of all, let's actually pass some credentials that are correct. So this will pass the validation and authenticator steps. So let's actually handle this request now by calling the server.handle method, and we can pass this request to the server handle method. So let's just check what happens here. And you can see that we validate, authenticate, and log. So it passes through all of the steps, no problem, and we can return the web page to the user. So this is like a successful request. So let's actually test what happens if we create a request with an invalid password. Okay, so if we give it a correct username, but the password is incorrect. Okay, so the password needs to be 8123 to pass. And then if we call server.handle request2, let's see what happens here. So let me comment this out just to make it clearer what's going on with this new request. So we can see here that we validate the request, no problem, and then we authenticate the request, but because the password is incorrect, the chain stops at the authenticating step and it never reaches the log step. Okay, so that is working perfectly. Now let's see what happens if we provide an empty username and password, so the user hasn't actually provided any credentials. As you can see, it just goes to the validating step. The validating step fails because we have two empty strings and the user is never authenticated. That we never get to the authentication step in the chain. So this is working exactly as we want it to. So here we now have a flexible solution that makes it very easy to change the order of processes. So as you can see, we can easily change the order of processes in the client without having to modify any code in the web server class. So this is super flexible and easy to change the order of processes. And it's also easy to add or remove processes without having to modify any existing code, which satisfies the open-closed principle. The visitor pattern separates the algorithms or behaviors from the objects on which they operate. So let's say that you are a developer for a marketing agency that has different types of clients. So they have restaurants, law firms, and retailers. So let's code up a quick solution for this. So here I've generated a client class, and this is going to be like the sort of parent or base class for each of the different types of clients. And you can see here we are storing the name of the client and the contact email of that client. So let's go ahead now and create the law client. So we can create a new C# class, and we're going to call this law client. And this needs to extend the client class. Okay, and then we just need to generate the constructor to satisfy the parent or base client class. And you can see here we just pass the name and the email to this client class. Okay, and we can also create a restaurant client and a retailer client. So let's go ahead and quickly do that. So we have a restaurant client, and we extend the base class, generate the constructor, and we can do the same for retailer. Okay, so we now have some very simple client classes that all extend this base client class, which keeps track of the name and email of the client. So, okay. So far everything is just a plain and simple C# object. There's nothing interesting going on so far. It's all very, very simple, straightforward stuff. But your manager comes to you and says that they need the ability to send a specialized email with marketing tips for each of the different types of clients. For example, restaurants need tips on how they can better market their food, but law firms don't. So it seems like a good idea to add an abstract method called sendEmail to the base client class, then implement that method in each of the concrete clients. So in the client class, we can create an abstract method called sendEmail. So let's go ahead and add that in. Okay. And we also need to make this class now abstract. Okay. And now you can see we have errors in each of our client classes. So we can implement the abstract class here. And let's just copy and paste this in because it's pretty straightforward stuff. So in our law clients, we are overriding this sendEmail abstract method from client, and we can just log sending law marketing tips, so specialized marketing tips, to the email address of this client. Okay, we can also do the same for restaurant and retail. So again, I'm just going to copy this in to save a little bit of time because it's very, very straightforward. We're just logging a basic sentence just to simulate sending an email, and we need to do the same for our retail client as well. So let's implement the abstract class and paste that in. Okay, so this all looks okay. So we can now send our emails by using polymorphism. So we can see here, I'm just going to paste this into VS Code. So what we can do, if we go into our program.cs file, which is going to be our client, we can create a list of clients. So I just need to import these classes now. let's see here, what do we have going on here? Let's see. Okay, these should be, we need to add client onto the end of these class names. Okay, so basically what we're doing here is sort of simulating getting a list of clients from a database. So let's just pretend this is some sort of database query where we get our list of clients from the database. And we have a retail client, a restaurant client, and a law client. And these are all of type client. Okay, so this is a list of clients. Okay, the reason for that is because all of these classes, law, restaurant, and retail, are all extending this base client class. Okay, so back into our program now. So now what we want to do is maybe every week we can schedule to send some sort of marketing email. So what we can do is we can loop through each client, and we can actually use polymorphism to send a specialized email. Okay, so our client here needs no knowledge of the actual specific type of client that we're dealing with, because the send email method is in the base class, which all of these classes are extending. Our clients can just call this send email class and delegate that to the specific client. Okay, so we're using polymorphism here. We don't need to know the exact client. So this appears to be a nice and elegant solution because we're using polymorphism. Everything looks okay. But the manager comes back to us and says that they need a way to export clients as PDFs and as XML. And you quickly realize that your manager is going to keep coming to you and asking you for more and more features for clients. So following our current design, every time that we want to add new functionality, we have to open up our code for modification. So we have to modify our base client class and then actually implement any methods, any specific methods in the client classes. So this is not good because this breaks the open-closed principle, and we risk breaking working tested code. And we're also violating the single responsibility principle, as clients are now responsible for storing client info, sending emails, and exporting clients as PDFs or XML. And also, initially, the clients were just simple, plain old C# objects. They were very simple objects. But adding the ability to send emails means adding third-party library code into these classes that calls email clients like Gmail and Outlook, and this can very easily break our previously working code. So here is the UML for this current solution. We can see that we have our client with name and email fields, and then we are adding a send email method, and we have our concrete or our sort of specific client classes such as retail, restaurant, and law, which implement any abstract methods in the client class. So to solve the issues that we saw previously, we need to extract the behaviors outside of the client classes on which they operate. So if you remember, the visitor pattern separates the algorithms or behaviors from the objects on which they operate. So let's implement the visitor pattern. So here is the UML where we implement the visitor pattern, and we have here an abstract client class, and you can see that we've removed the send email method from this class, and that will now be in the concrete email visitor class. Okay, so the behaviors have been abstracted into the concrete visitor classes, which can then be passed to the objects that they operate on, like so. So here we can see that we are looping through our clients and sending a marketing email. So we can see here we call the client.accept method, and you can see here that all clients must have an accept method which accepts some sort of visitor. And here we have an email visitor, which is used to send emails. And then within the specific sort of client classes, so for example in retail, we call visitor.visit retail, and then that deals with sending an email specific for retail clients. Okay, so we can see before that the send email logic was actually on the clients themselves, whereas now we've separated the behavior from the objects which they operate on. So if we have a look at the gang of 4 UML here, we can see it's pretty similar to what we have up here with a small difference. So we can notice that design patterns are not super rigid. So for example, in our case, the element class is an abstract class and not an interface. And this is because we want to provide some common fields and some common methods to all of the clients. So in our case, we have the name and email fields and also the get email method, which is common to all clients. That's why we're using an abstract class and not an interface where we can't sort of store any fields or actually implement any methods. Okay, so let's now implement this visitor pattern in code so that it makes more sense. First of all, I'm going to create a new folder inside of the visitor folder called good, and this is where we're going to put our sort of better solution that follows the visitor pattern. So first of all, let's create our base client method, which will have an accept method that takes a visitor object. So let's go ahead and create that. And this needs to be an abstract class. And here we're going to have the same as before. We're going to have 2 fields, one for storing the name of the client and another for storing the email of the client. And these are going to be set within the constructor of this client class, just the same as before. And we're also going to have a getter for getting the email of the client. Okay, so this is all similar to what we had before, but now rather than having a abstract send email method, we're going to have an abstract method called accept that that accepts a type of visitor. Okay, so let's create that method. So this is going to be a public abstract void method called accept, and this accepts a visitor object. And the visitor object is going to contain the behavior that will operate on a certain type of. It will operate on a specific client object. Okay, so this is hard to understand at the moment, so let's keep on going. It will make more sense as we develop the solution further. So next we're going to create our visitor interface. And in here we're going to create 3 methods, one called visit retail, and this is going to accept a retail client, and we don't actually want to import this from the previous solution, so let's ignore that for now. Okay, so let's just ignore these errors for now. They will go away as we actually create these clients. And we need one for visit law. And we also need a method for visiting a restaurant. And we need to just rename this to law client, and we need to rename this to restaurant client. Okay, so now we need to create the specific client classes. So let's go ahead and do that. So we'll start with the retail class. And this retail class needs to extend the client base class and then implement this abstract method, which is the accept method. Okay, so in here, what we're actually going to do is we're going to call visitor dot visit retail. And I think we also need to implement the generate the constructor. That's it. Okay, so I'm not sure what this problem is here. Oh yeah, of course, we have to pass this object to the retail visitor, because the retail visitor is going to operate on this retail client object. Okay, so that is the retail client. And now let's go ahead and create the restaurant client. And this is going to extend client. And we also now again need to implement the abstract methods and also generate the constructor. Okay, so in this accept method, we are simply going to call the correct method on the visitor. And here we are visiting a restaurant client. So we need to call visitor.visit restaurant. And then we pass the restaurant that we want to visit, which is this object. Okay, so next, our final specific client class is the law client. So let's create the law client class. And again, we're going to extend the client class. And we can implement the abstract interface and generate the constructor. And finally, we're going to call visitor.visitLaw and pass this object. Okay, so this is going to now make more sense because we're going to now create our concrete visitor class for sending marketing emails for each specific type of client. So let's create the email visitor class. And this is going to implement the visitor interface. Okay, so in here, this is where we implement the specific methods, and we have the behavior that is now separated from each of these client objects. So what we can do is to send an email for law clients. We can simply log sending law marketing tips email to, and then we can get the email from the law client by calling get email. So this is pretty nice. And if you can remember, so let me just try and tie this together a little bit for you now. So in the law client, whenever we call the accept method, we pass the visitor, which contains the behavior that we want to do. So if we want to send an email, we can say lawClient.accept, pass this email visitor, and then within this method we are calling visitor.visitLaw, and the visitLaw method is implemented inside of email visitor, and it sends a law marketing tips email to the law client's email address. Okay, so hopefully it's starting to make a little bit more sense for you. Okay, so in here we want to send a restaurant marketing tips to email to, and then we want to concatenate the restaurant client's email. And finally, for the visit retail, I'm just going to copy and paste this in to save a little bit of time. Sending retail marketing tips email to retail, and this should be retail client dot get email. Okay, so that is the whole solution. So let's now use this solution inside of our program.cs file. So let's actually use the namespace for our good solution. And we can see, as before, we can create our list of clients here. So we have a retail client, a restaurant client, and a law client. And we have the name of the client, so Debenhams or Frankie and Benny's, Hamlin McGill, for any people that have seen Better Call Saul. And we have our email for each client, our contact email. And what we can do now is we can again loop through each of our clients. And now remember that the send email logic is no longer stored on the client objects themselves. We've separated the behavior, which is send an email in this case, from the objects on which they operate, which are each of the unique specific client objects. So now what we can do is we can say client.accept, and then inside of this accept method we can pass any type of visitor. And in our case, we want to pass an email visitor because we want to send an email to each of the clients. So we can pass the email visitor. And if we now run our program, we can see that we are looping through each of the clients and sending them an email. We send an email, retail marketing tips email to Debenhams, a restaurant marketing tips to Frankie and Benny's, and a law marketing tips email to Howard McGill Law Firm. So this is working perfectly. So let's now take a look at why this is such a good solution, why the visitor pattern is a good solution to this problem. So let's say that our manager comes to us asking for new features, and we can now extend our code and we don't have to modify it. Beforehand, if our manager comes to us and asks if we can add some export as PDF logic, then we beforehand would have to modify the client class or each of the individual client classes. We would have to modify our code, breaking the open-close principle. Whereas now, to add a new functionality, such as export as PDF functionality, we can simply extend our code by creating a new type of visitor. So let's go ahead and actually create a new visitor to show you how this works. So if we go inside here and create a new class called PDF export visitor, and this is going to implement the visitor interface. And now here, I'm just going to copy these logs into here to save some time. So here we just say that we are exporting a law client as a PDF, and we can just do the same down here. This is going to be a restaurant client, and this is going to be a retail client. Oops. Okay, so this is our export as PDF visitor class. And then if we want to export a list of clients as a PDF, we can come back into our program class, and let's say we want to send an email, and then maybe we want to export as PDF. So let's now pass this visitor here, PDF export visitor, and I'm just going to comment this out actually, so we can see what's going on a little bit easier. And we can see we export retail clients as PDF, then the restaurant client and the law clients. So this is working perfectly. We didn't have to modify any of our existing working code. We just extended our code base by creating a new PDF export visitor. And then we can pass that to each of the clients. So this is perfect because we are now satisfying the single responsibility principle and the open-close principle. The interpreter pattern defines a way to represent and evaluate sentences in a language by using an abstract class for expressions, which concrete subclasses implement to interpret specific parts of the language's grammar. So the interpreter pattern is probably the most complex and least used of the gang of 4 design patterns, and most courses on design patterns that I've seen don't actually include this interpreter pattern. However, at the beginning of this course, I promised that I'd teach you all 23 gang of 4 design patterns, so let's give it a go. And after the example that we're going to go through, I'll also discuss why this pattern is rarely used. So here are some example use cases for the interpreter pattern. So it's used in parsing and executing SQL queries, where the interpreter pattern helps to parse the query syntax and execute it against a database. It's used in calculators or scientific software that interpret and evaluate complex mathematical formulas entered by users. It's also used in web frameworks that render HTML templates with embedded expressions or directives. So, for example, templates in web frameworks such as Laravel or Django. And for example, in Laravel, you have the Blade templating language where you can sort of write your variables within curly braces. It's also used in JSX and React. And then that is parsed by some parser and turned into or interpreted into some sort of HTML template. So let's say that we want to build a calculator app that takes some user input string and calculates the result. So here we have a user input string. So we have 1 plus 2 times 3. And an interpreter needs to convert or parse this input or expression into an abstract syntax tree or an expression tree. So you can see here that an expression tree looks something like this. It's kind of like a tree of a tree structure of objects. So you can see here 1 plus 2 times 3. We can't simply just go from left to right. We can't say 1 plus 2 and then times 3. We've got to respect maths rules. So the BODMAS rules, which mean that we have to perform the multiplication first, and then we have to add the 1. So we have to do 2 times 3 and then add 1 to that result. So 2 times 3 is 6. Then we add 1 to get 7. And that's the result of this expression. So when we build the abstract syntax tree, we need to respect BODMAS, so we need to get the order of operations correct. So you can see here we first of all have an addition expression which contains 2 more expressions. Okay, so you can see the first expression we do is the multiplication expression, which is the 2 times 3. So we can see here we do 2 times 3, and then finally we add the 1 onto that result. So essentially what we're doing here is we are converting or parsing an input string into a tree of objects according to the grammar rules that we specify. And in this case, the grammar rules are the sort of maths BODMAS rules. So the result of the expression that we have here can be found by calling its interpret method. So on this expression tree, all expressions will have an interpret method, and we can call this and it will find us the result of this expression, which we know is 7. So we can essentially use the interpreter pattern to get from the user input to create this abstract syntax tree, which can then be interpreted or evaluated to get the result. So here are the components of the interpreter pattern. So we have abstract expressions, which establish the interface for all expressions within the language. So the abstract expression is essentially going to be an interface which has an interpret method that all expressions will implement. So in our case, all the expressions that we have, the concrete expressions, are the addition expression, the multiplication expression, and number expressions. And all of these implement this I expression interface, and will have an interpret method which defines how these expressions should be interpreted. We then have terminal expressions, which represent the fundamental components of a language, such as numbers or variables. And in this above example, number expression is a terminal expression or a leaf that represents integers. So you can see here, we have number expression where you pass a number of some sort, and we can pass either a string or an integer in our case. And this can be, when you call the interpret method on a number expression object, it will just return an integer value directly. So in this case, if we pass 2 as a string, it will return 2 as an integer. And in this case, it will return the integer of 3. Okay, so they can be interpreted directly, basically, these terminal expressions. We then have non-terminal expressions, which represent more complex expressions that are composed of other expressions using operators or functions. So above, the addition expression and the multiplication expression are non-terminal or composite expressions. So this means that the non-terminal expressions are built up of sub-expressions. So you can see here we have multiplication expression, which is built up of multiple expressions. It's built up of two number expressions. And we can see here the addition expression is also built up of two expressions. We have this multiplication expression and we have this number expression. So you can see here, if we call the interpret method on a non-terminal expression, then it can't be directly interpreted, because if we look at this multiplication expression, it first of all has to interpret this number expression, then it has to interpret this number expression, so it has a left and a right expression, if you will, and then it has to multiply these results together. And you can see here this addition expression first of all has to evaluate this multiplication expression, which has to evaluate these number expressions, and then once this is evaluated, it has to evaluate this number expression. So non-terminal expressions can't be directly interpreted like the terminal expressions. They essentially have to be recursively interpreted. We have to recursively keep on calling the sub-expressions interpret method until we finally get to the results of the terminal expressions. And then we also have an interpreter which implements the logic for interpretation and determines how to evaluate different types of expressions. So I'm fully aware right now that you have no idea what is going on. So we're going to go through an example, and it will definitely help if you try to code this example out a few times. So first of all, we're going to create a context class that is going to contain any global information needed for interpretation. So let's create that context class. So in our case, for our simple calculator example, we don't currently really need this context class. But say that we wanted to interpret English language into Spanish, and each Spanish-speaking country speaks Spanish slightly differently. So this context object or class could contain the country and city that we are currently located in, and it could also contain the gender of the person that we are speaking to, as that could also affect the interpretation. But for now, we're just going to leave this as an empty object. So next up, we need to create the abstract expression interface. So we're going to call this iExpression, and each expression needs to have an interpret method where we pass the context to that method. So each expression will have access to any context data. So next up, let's create our first concrete expressions. So first of all, we're going to create the terminal expressions, and in our case we just need one, and that is number expression. Okay, so this needs to implement the expression interface. Okay, so it's going to have an interpret method. So in number expression, we need to provide a number when we create a number expression. So let's create a number field, which is going to be of type integer, and then we can create a constructor. So we're going to create a number expression constructor, which takes in an integer number, and we can assign that to our number field. And what we'll also do is we'll overload the constructor. So we're actually going to copy and paste this constructor down, and we can also provide a string number. And then what we can do is we can convert this string number. So if somebody creates a number expression object and passes a string, then we're just going to convert this string into an integer before assigning it to the number field. So this just makes this class a little bit more flexible because we can provide both integers and strings. Okay, so finally, in our interpret method, because this is a terminal expression, we can just return the number. Okay, so that's very simply what number expression does. Okay, so next up we can create our non-terminal expression. So first of all, we will create our addition expression. So let's go ahead and create that. And this needs to implement the iExpression interface. Okay, so if you remember, non-terminal expressions are composite expressions. In other words, they are built up from multiple sub-expressions. So what we need to do here is let's create two fields of type expression, and we're going to have a left expression, and we're going to have a right expression. So in addition, for example, if we have 1 plus 2, then the left expression would be a number expression where we pass 1, and the right expression would be a number expression where we pass 2. And then we can interpret both of those expressions and then add them together. And that's what we're going to do in our interpret method. But first of all, we actually need to create a constructor or some way of setting these left and right expressions. So let's go ahead and do that. And we can assign the fields in the constructor. So next up, we need to actually interpret these expressions. So we're just going to say left dot interpret, and we pass in the context, and then we need to add the right expression interpreted. So again, if these are number expressions, they will just interpret to their integer values, and then they will be added together. Okay, so that's what we have there. So next up, let's create another non-terminal expression, which is the subtraction expression. So subtraction expression, and in here again we're going to have a let's see, where are we? So let's copy and paste these two fields in. I'm also going to copy in what we have from addition expression, and we're just going to modify things a little bit. So this needs to be subtraction expression. So the constructor, we set the left and right expressions, and then in interpret, rather than adding them together, we are subtracting them. Okay, so finally we're going to create a multiplication expression. So again, this is going to be very similar to what we have in the addition and subtraction. Okay, so again we're going to have two fields, and we're going to set those expressions inside of the constructor. So let's see, let's copy and paste that in, change the name of the constructor, and this needs to also implement, in fact we forgot to implement the expression interface here, so let's implement that in the subtraction expression, and we also need to implement it here in the multiplication expression, and then implement the interface. And then here we're just going to return the left expression, and then we're going to interpret it, pass the context, and then we're going to multiply by the right expression. Okay, so that's everything that we need for our expressions. So next we need to create the interpreter, or the parser class, which needs to convert some input string, for example 1 plus 2 times 3, and it needs to convert that into an abstract syntax tree or an expression tree. And first of all, so let's go ahead first of all and create this interpreter class. So the interpreter is going to hold a reference to the context. Okay, and it's also going to have an interpret method which interprets the expression or builds the expression tree. So let's create that method. It's going to return an integer. In other words, the sort of final result from parsing the expression. So this needs to take a string, an input string, or some expression string. You can call that whatever you want. And what we're going to do is we're going to build an expression tree. So we're going to create a separate method for building the expression tree. So we're going to call this build expression tree. And in here, we're going to pass the expression that we want to build an expression tree from. And then finally, we're just going to return the expression tree. And we're going to call the interpret method on that tree and pass in the context. Okay, so that's going to return an integer value. So let's now create this build expression tree method, which is going to return a expression. and it's going to take some input. I'm going to call it input. You can call it expression, whatever you want. So this is where things get a bit more interesting, because building a parser that converts some input strings such as 1 plus 2 times 3 is actually pretty complex, because we can't just sort of traverse this from left to right. We have to perform this 2 times 3 first and then add the 1. So building parsers are complex, which I'm going to show you very shortly, and it's very easy to get them wrong. So for simplicity, we're just going to skip this building an actual parser for now, and we're just going to hard code in the expression tree for the input 1 plus 2 plus 3. And of course, in the real world, you would need to build an actual proper parser or download one from somewhere, from some package. So let's actually hard code in a few things here. So we're going to say the input is always going to be 1 plus 2 times 3. And we're then going to hard code our expression tree. So we'll say expression tree is equal to, and what we're going to do is we're going to build an expression tree for this particular input example. So first of all, we have to do the addition expression, and inside of here we need to first of all do the multiplication expression, which is 2 times 3. So we do a new multiplication expression. And in here, we can pass in the number expressions of 2 and 3. And we can pass 2 in here, or it can be a string. And we do new number expression 3. Okay, and then we also need to then add this 1. So we do new number expression, and we say 1. Okay, then from here we can return this expression tree. Okay, which is going to be interpreted in this interpret method. Okay, so now let's have a look at how a client would use this solution. Okay, so let's say that we have an input string of 1 plus 2 times 3. And in this case, it doesn't actually matter what our input string is, because we've hard-coded the result in here. We've hard-coded the input, and we've hard-coded the result of this input example. I am going to show you how to build, I'm going to show you what an actual parser for this would look like and how it would build this expression tree from this input. But for now, let's just hard-code things in for simplicity and for a little bit of sanity. So we can then create our context object, and we can create our interpreter, and we pass in our context object. Okay, so let's actually get the result from interpreting this input. So we can say interpreter dot interpret, and we can pass our expression, our input expression, and we can assign this to a result variable, and let's actually log this result to the console. Okay, so let's log this. We should get 7 back, because 2 times 3 is 6 plus 1 is 7. So let's see what we get, and we will get result equals 7. Okay, so that is all looking good so far. Next up, I'm going to show you what an actual interpreter class would look like if we actually parsed the input string correctly programmatically. So let me now show you what an interpreter class would look like if it actually parsed the input string into an expression tree. And for simplicity and a little bit of my own sanity, the interpreter only handles addition and subtraction, as handling multiplication, division and brackets in an expression would require quite a bit more complexity. For example, 1 plus 3 times 4 requires the 3 times 4 to be executed before adding the 1 due to BODMAS. So creating language or grammar parsers is actually very, very difficult to get right. Even for this simple parser that I'm going to show you now, it only actually handles addition and subtraction. I've not actually handled multiplication and division, and it's still fairly complex. It still takes quite a bit of thought to build out, and it's very easy to get wrong. So what I'm actually done here is I've already built out this second interpreter, which actually parses the input string, and it's exactly the same as the interpreter that we built before, up until this build expression tree method, where we actually now have an algorithm to parse the input. Okay, so we can see here, this only handles addition and subtraction. So first of all, what we do is we split the string into a list of tokens, or an array of tokens. So you can think of tokens as like the words in a sentence, or in our case, the tokens will be the operands and the operators. So the operands are these numbers, and the operators are like the addition and subtraction signs. Okay, so we build up a list of tokens by splitting the string via the spaces. We then create an output queue and an operator stack. And this is pretty complex and way beyond the scope of this course to actually go through what is going on here. This is a course on design patterns, not on algorithms. But essentially what we're doing is we're using an algorithm called the shunting yard algorithm to change the sort of format of our expression so that we can build an expression tree. And you can see here, depending on the token, we are creating new expressions of certain types. So here, if it's a plus sign, then we sort of add to the stack an addition expression, and we add the left and right expressions that we need to add. Okay, so it's pretty complex, and I don't want to go through all of this, and it's way beyond the scope of this course. But I just wanted to show you that even for just having a parser that handles addition and subtraction, it's actually very complicated. And if we wanted to actually account for multiplication and division and brackets, then it would be even more complex. So I just wanted to show you basically that building parsers is extremely difficult to get right, and yeah, it's something that you're not going to be doing too often in your life as a software developer. At least most of you won't be doing that anyway. So let's actually use this in the client now. So we're going to change the input. We can't do multiplication with this one, so we're just going to do let's see, 2 plus 3, and then we'll minus 4, and we will add 10. So this should give us a result of 5, 1, so it should be 11, okay? That's what we are expecting, and we're now going to use interpreter 2 instead of interpreter 1. Okay, so that should all be okay. So let's run this, and we should get 11. And as you can see, we get 11, so that's all working correctly. So what is actually going on here? So let's sum up what we have so far so that we can better understand what is going on here. So first of all, we have the client, our sort of program.cs file, which initiates the interpretation process by providing, first of all, an input expression to interpret, and it also creates the interpreter object and the context object with information that is needed for the interpretation process is passed to the interpreter. And in our case, we are not providing any context data. Okay, so next of all, the parsing and building of the abstract syntax tree. So the input expression is turned into an array of tokens in the interpreter. So if we go up here, we can see we're turning the input into an array of tokens, and tokens are analogous to words in a sentence. And these are parsed via some algorithm. So we have our big algorithm here that creates an expression tree that represents the input. And if we go into our first interpreter, the expression tree will look something like this. It builds an expression tree that sort of represents our input. Okay, so each operator and operand, so the operators being like the multiplication symbol or the addition symbol, and the operands being the numbers themselves, are each represented by a corresponding expression object. So the numbers are represented by the addition expression, and the operands are represented by the multiplication expression, or the subtraction expression, or the addition expression. Okay, and they're basically built of sub-expressions. Okay, so let's now have a look and have a think through the expression evaluation. So we've built our expression tree from our user input. Now we need to interpret this expression tree. Okay, so the interpreter, so if we go into this interpret method, we first of all create the expression tree, then we have to interpret it. And the interpreter traverses the expression tree and interprets each individual expression or node as it goes. So for terminal expressions, the operands or numbers such as 1, 2, and 3, their interpret methods directly return their numeric values. So if we have a look in the number expression, you can see number expression is just returning the numeric value. And for the non-terminal expressions, the operators such as plus, minus, and multiply, their interpret methods call their left and right sub-expressions, and then it calls these left and right sub-expressions recursively, and then performs their respective operations, so either add, subtract, or multiply. And what we mean by recursive, if we just have a look in here, you can see that we first of all have to call this addition expression. We call interpret on this, and then from in here we call interpret on this multiplication expression, and then we have to interpret this left expression, then the right expression, then we multiply them together, and then we have to interpret this number expression, and then we finally add them together. So we're recursively calling the interpret method on each of these expressions as we traverse the expression tree. Okay, so then we need to combine the interpreted results. So the interpreter combines the results of the sub-expressions according to the defined grammar rules that should be represented by the expression tree. And in our example, following BODMAS, 2 times 3 should be performed or evaluated first, and then we then add on the 1, so that the final output is then returned to the client. So here is the Gang of 4 UML for the interpreter pattern. So you can see here we have our abstract expression interface with an interpret method that takes the context object, which contains some sort of data that is relevant to the interpretation. And then we have our 2 groups of expressions. We have terminal expressions, which basically kind of return the building blocks or the kind of fundamental sort of words or digits in our language. So in our case, that was just integers. And then we have our non-terminal expressions, which are built up of sub-expressions. Okay, so let's now have a look at some commonly stated justifications for when to and when not to use the interpreter pattern. So if you need to interpret and execute expressions or commands in a domain-specific language, the interpreter pattern offers a flexible and extensible method for implementing the language's grammar and semantics. If your task only involves calculating simple operations that can be handled by general-purpose programming languages or by a library, then using the interpreter pattern adds a lot of unnecessary complexity. So most of the time, a general-purpose programming language or library will do the job for you. And if the grammar of your language is complex, then the interpreter pattern could lead to having a large number of classes and increased code complexity. And in this case, a dedicated parser generator or compiler would be a better option. So now we're going to take a look at why the interpreter pattern is rarely used. So Steve Yege, a software developer and blogger, says that the Gang of 4 book contains 22 patterns and a practical joke, and the interpreter pattern is that practical joke. So the problem with the interpreter pattern is that you must turn your language into an abstract syntax tree. And as you saw earlier with our calculator example, creating a parser or an algorithm for converting some input into an abstract syntax tree is a very difficult task to get right and is very time consuming. And for anything other than the simplest of languages, creating a parser is very difficult and likely to fail. So how did the Gang of Four book deal with this? They basically ignored the parsing problem altogether and said that it was a separate problem to the interpreter pattern. So I've actually copied and pasted a paragraph from the Gang of Four book about what they say about this kind of problem. So the interpreter pattern doesn't explain how to create an abstract syntax tree. In other words, it doesn't address parsing. The abstract syntax tree can be created by a table-driven parser, by a handcrafted, usually recursive descent parser, or directly by the client. But when we use the interpreter pattern, we have to somehow generate this abstract syntax tree. We can't just ignore the complex problem of parsing. And this is why Yege characterized the chapter as a practical joke, and why other programming techniques and patterns are almost always preferred to the interpreter pattern. And in your life as a software developer, most of you will rarely have to develop your own languages, so the other 22 design patterns will be of much greater use to you. However, there will, of course, be some specific good use cases for this pattern in the real world. Okay, so that's enough of this pattern. We're now going to move on to structural design patterns. Structural design patterns focus on the composition of classes and objects to form larger structures and systems. These patterns primarily deal with how classes and objects can be combined to form larger, more complex structures, while keeping these structures flexible and efficient. The key objective of structural design patterns is to provide solutions to design problems related to object composition and structure, allowing for better organization and management of code. So structural design patterns help to achieve several important goals in software development. They promote code reusability and modularity by defining clear and standardized ways to compose and organize classes and objects. And this makes the codebase more maintainable and scalable over time, as changes or additions to the system can be made more easily. They enhance flexibility and extensibility by allowing the system structure to evolve without requiring major changes to existing code, and this is achieved by decoupling the components of the system and promoting loose coupling between the different parts. And structural design patterns also improve performance and resource utilization by optimizing the way objects interact and collaborate within the system, thereby enhancing overall system efficiency. So overall, these patterns contribute to building robust, adaptable, and well-organized software systems that are easier to understand, maintain, and extend over time. So let's now learn some structural design patterns. The composite design pattern is a structural design pattern that enables the creation of tree-like structures to represent collections of objects, where both individual objects and groups of objects are treated in a unified manner. So to understand what this means, let's create a scenario, then code up a simple, naive solution, then fix it with the composite pattern. So let's say that we get an Amazon delivery of a large package that contains multiple items. So as you can see, the boxes can contain groups of other boxes and items, and the above this diagram shows how a package of items can be represented as a tree structure. So at the top we have the big main Amazon box that you would receive, and then within this box we have two more smaller boxes, and then within this smaller box we have a microphone, so our first item that we open, and then the second box contains two smaller boxes, and this box contains a mouse and this box contains a keyboard. Okay, and you can see that this is represented as a sort of tree structure. So say that we need to find the total price of the items within any package. So for example, the total price of all the items in this top main package would be the cost of the microphone plus the mouse plus the keyboard. whereas the price of the items within this package would be just the mouse or the keyboard, and the total price within here would be the keyboard. The total price of this package is the mouse. Okay, so the solution that naturally pops into the head is to create an array of boxes and items, then loop through them recursively to find the total price of the package. So here is the simple solution. So we can see here that we've created a keyboard class with a price, a microphone class with a price, and a mouse class with a price. We can then have a box, which is just a list of any type of object, and we call this items. And within this box class, we have a method for adding an item, and we just add it to the list of items. And then we have a calculate total price class, which first of all has a field called total price, which we set to 0. It loops through all of the items in the items list, and it checks what type of object the item is. So if item is a keyboard, then we cast the item to a keyboard object, which means that we can then access its price field. Okay, then we have to do the same for mouse. We cast it to a mouse and access the price field on the mouse class, add it to total price, and then we do the same for microphone. Else, if the item is a box, then we cast the item to a box and call calculate total price. So we're calling this method recursively. Then we just return the total price of the box. So you can see that this method is ugly because we're having to check the type of object and then cast the object to that type to be able to access its price field. So this is very ugly solution. First of all, it's very hard to read. This method is already bloated with just 3 types of items. So the more items we add, it's going to become even more bloated. And if we add more items or remove items, then we have to modify this class, breaking the open-closed principle. So if we use this solution to create the package demonstrated in the previous tree diagram, we can see here that we first of all create the big package to deliver containing box 1 and box 2, and then box 1 contains a microphone, box 2 contains box 3 and 4, and then box 3 contains a mouse, box 4 contains a keyboard, and then we're just adding the boxes to the correct box and adding the packages to the correct boxes, and then we can call calculate total price. So you can see that this solution calculates total price correctly, but it has some obvious flaws that we have already discussed. So we have lots of conditionals, which is very hard to read, and we're violating the open-close principle because whenever we add a new item, we have to modify the box class. Whenever we have lots of conditionals that are checking the type of an object and casting it to another object type, it's often a good sign that we need to use polymorphism. And we can use polymorphism by creating an interface called item and extracting common methods or logic between the objects into that interface, like so. So here we have an item interface with a getPrice method, and we can see that both box and each of the product objects or classes are extending this item interface, meaning that they will all have this getPrice method. So a box is essentially composed of a group of items. So you can see here, this is represented by the diamond arrow, and you can see this field here. A box is composed of a group of items, but a box is also an item itself, represented by the arrow. So a box is simply just a group of items. But a box and its contents can be treated the same way as items, thanks to polymorphism. So now let's go ahead and create the code solution. Okay, so I've created a new folder for our structural design patterns, and in here I've created a composite folder for this example. So first of all, let's create an interface called item. And items are going to have a single method, called getPrice, which returns a float. And we can now create our specific item classes. So first of all, let's create a keyboard class. And this needs to implement the item interface. So each class will need to have a field to store its price. So let's go ahead and create a private float called price. And I'm just going to set this for now as a constant. In a real application, it would be much more sensible to create a setter method for this, or set the price in the constructor. But for now, we're just going to hard code a value in for the price. And then within this getPrice method, we need to return the price. Okay, so let's now go ahead and create our other items. So we're going to need to create a microphone. And this needs to implement the item interface. And again, we're going to have a private float for the price. And again, let's just hard code this in for now, and we just return the price. Okay, let's create our mouse class. And I'm actually just going to copy and paste this in to save some time, as it follows the exact same structure as we have with our keyboard and microphone. Okay. So now let's create our box class. And a box, remember, is just a sort of class that stores a group of items. And a box is also an item itself. So let's implement the item interface. And now a box needs to actually have a field for storing a list of items. Okay, let's also provide a method for adding items to the list. Okay, now we need to implement the getPrice method. So what we're going to do is we're going to loop through the items in this items list, and we're going to add it to a total variable. So let's create a float called total. And then we're going to loop through each item in the items list. And we're just going to add it to the total. And here we can call item.getPrice. Okay, and we know that each item is going to have a getPrice method because all items are implementing this item interface. So we no longer need to check the type of item object. We can just treat them all as items. And here we are basically using polymorphism because this item object can take many forms. It can be a keyboard, it can be a microphone, or it can be just another box. Okay, so polymorphism is allowing us to, giving us a lot of flexibility here. And then at the end, we just need to return this total. So let's now actually use this solution in our program.cs file. And what I'm going to do is, rather than code all of this out, it's a pretty hefty bit of code. So we're just creating the tree structure that we had beforehand, basically. So what I'm going to do is just copy and paste this all in. And then let's actually import the correct namespace. So it is this one. Okay, so this all looks okay. So just to remind you of the tree structure that we are creating here. Let's see if I go over here. So if I just scroll up, so we're essentially creating this tree structure. So we have one big package that contains two boxes, then box 1 contains a microphone, box 2 contains two more boxes, and then we have a mouse and a keyboard. Okay, so that is what we have there. And let's see, so let me go back over here. Okay, so let's run this file to see what we get. And I think actually we've messed up the copy and paste in here, so let me just copy and paste this in. Okay, so that should hopefully be correct. And the total price of the package is $87.99. So if we quickly check what we have in the packages, we have a keyboard, a mouse, and a microphone. So we have 40 plus 29, which is $69.99. And then we have a mouse, so that's $87.99. So the total price of the package has been calculated correctly. Okay, perfect. So you can see that there has been no change in the way that the client would actually use this solution compared to what we had beforehand. The biggest change in using this solution is that it calculates the price, is in the way it calculates the price using the get price methods. Because we can now treat all objects in the box in the same way, as they all implement the item interface. And this means that we don't need conditionals to check the type of each item. And this satisfies the open-close principle, as our code is open for extension but closed for modification. So we can create a new item class, extending our code without needing to open any existing classes for modification. So here is the Gang of 4 UML for the composite pattern. So you can see that we have our component interface at the top, and then we have our composite class. So a composite meaning that it contains sort of multiple components. So you can see here that a composite has some children, or it contains some other components. So it has a list of components, and then it has a method for adding components to the list. And it also has an execute method to execute some sort of logic. And then we have our leaves, which are the sort of individual products themselves. Okay, so the composite pattern is useful for representing tree structures, for example, folders and files. And we can see here that a folder is like a composite. It contains either other folders or individual files. And you can see here this folder contains 2 files, as well as another folder which contains 3 files. And the composite pattern is very useful for representing these kinds of tree structures. And another example is a graphical editor that allows you to group shapes together and group groups of shapes together as well. So when you drag a group, all shapes should move together in the same way. So you can see here we have a group which contains a circle, triangle, and another group, and this group contains 2 groups, and this group contains 2 squares, and this group contains 2 circles. Okay, so you can see that this can be represented as a tree structure, and this is where you might start thinking that the composite pattern could be a good way to represent this in code. The adapter pattern is a structural design pattern that allows incompatible interfaces between classes to work together by providing a wrapper that translates one interface into another. So let's create a scenario that will help you to understand this pattern and the pattern's use cases. So say that we have a video editing application that allows users to upload a video and change the color of the video. The application provides preset color options for the user to select, such as black and white or midnight purple. So as you can see here, we have the original video with color. It then goes through some sort of black and white algorithm, and we finally get the edited video with all of its color removed. In this case, the video is made black and white. So the classes that change the color of the application are built by us. They are sort of our own, part of our own code base, our own custom code. And these classes implement a color interface, so some sort of common interface, so that we can use polymorphism to treat these classes in the sort of same way. So here's how the application looks. So we just have a sort of basic video class here. We have no methods and fields, but let's just pretend this class represents some sort of video. We then have a color interface, which has an apply method, and each apply method takes a video class. And this is the video that we are going to work on. So we're going to apply a color to this video. So we then have our sort of concrete color classes. So here we have a public class called black and white color, which implements the color interface and therefore has an apply method which accepts a video to apply this black and white color to. And in a real application, this would be some complex code to apply a black and white color to a video. But here we're just logging, applying black and white color to the video. We also can have other color classes, of course. So here we have a midnight color, which implements color and has an apply method, which takes a video that we can apply the color to. We then have our video editor class, which has a video field, and we pass a video to this video editor via the constructor. And we then have a method called apply color, which takes some sort of color object and then calls color.apply and passes the video that we want to apply the color to. Okay, so using this solution in a client, we first create a video editor by calling new video editor. We pass the video editor a video that we want to edit, and we then call video editor.apply color, and we can pass any color object that we want to apply to the video. So in this case, we are applying black and white color to the video. So this is all looking good so far, but we then decide to install a third-party library into our application that allows users to apply more types of colors to their videos, so more complex color options to the videos. So the problem is that all of the concrete color classes are expected to implement our custom color interface and have an apply method. But the concrete color classes from the installed library don't implement this color interface, meaning that we can't pass them to our video editor.apply color method like this. So you can see here that this rainbow class is a color class from the installed third-party library, and we don't have access to this code. And you can see here we can't just pass it to this apply color method because this is expecting an object which implements our color interface. And of course, this third-party class doesn't implement our custom color interface. So as mentioned, we cannot modify the third-party library code to make the color classes implement our color interface. So how do we solve this? So we can solve this by converting the interface of the third-party color classes to a different form using the adapter pattern. So far we can't use this third-party rainbow class because it doesn't implement our color interface, and we can't make it implement color because it's inside of a third-party package. So here's the sort of situation drawn out in your UML, where we have a video editor with an apply color method, where we can apply some sort of color, so any color that implements this color interface. And we have our own sort of custom color classes such as midnight purple and black and white, which implement this color interface. We then have our sort of third-party color classes such as rainbow, and these have some sort of update method which needs to receive a video. However, we can't pass these to the apply color method because they don't implement our color interface. So let's take a look at how we can solve this issue. So we can create a rainbow color class that implements color and is composed of the third-party rainbow class. We can then call the apply method in rainbow color, and inside the apply method call whatever methods that we need to call from rainbow to apply the filter. So we essentially adapt the class to a different form. So let's explain that again. So here we have our video editor. So again, just as before, nothing different here. We apply a color and pass it some sort of color. So any object that implements this color interface. And this color interface has an apply method which accepts a video. So now this is the new class that we've created. We've created this rainbow color class. This is our own custom class which implements color, has of course an apply method which takes a video, and then within the apply method we can actually call the rainbow class or the rainbow object dot update and then pass the video. And this rainbow color class that we've created is composed of, so it has a field of type rainbow. So essentially we've adapted this third-party rainbow class into a different form. We've adapted it into a color object. Okay, so rainbow color, this class that we've created, is the adapter. It's converting the interface of the rainbow class, so the adaptee, into a different form, and that form is color. So let's now implement this in code. Okay, so just a quick reminder of what we have so far. So we have a video class, which is just a class that represents some sort of video. We then have a color interface, which describes what a color class or a concrete color class should look like. And all colors should have an apply method that accepts a video object. We then have our concrete color classes, such as black and white color, which implement the color interface, have an apply method that takes a video, then the apply method applies the color to the past video, and midnight color is also a concrete color, similar to black and white color that implements the color interface. We then have our video editor class, which has a field which stores a video to edit. We pass the video via the constructor, and we have a method called apply color where we can pass a color that we want to apply to the video. So that's what we have so far. So let's now create the video class from the third-party library. So I'm just going to create, let's actually create a folder. So this is kind of going to represent a third-party library. So I'm just going to call this package. And in here, I'm going to create a rainbow class. Okay, so let's say that colors from this third-party library require some sort of setup. So we have to call a setup method before we can actually use the color. Okay, and maybe this would be some sort of method that we could pass some configuration options, such as, I don't know, the brightness of the color, or I don't know, anything like related to the color of a video. But we're just going to leave this as a simple method called setup, and I'm just going to log setting up rainbow filter. Okay, and then I'm also going to create a method called update, and this is going to be basically this a similar sort of method to our apply method. So we're currently calling the method apply. The third-party library is going to call the method update. Okay, and this takes a video and it applies the color to the video. So I'm just going to say applying rainbow filter to video. Okay, so this sort of represents what our third-party rainbow color class looks like. And currently we can't use this because it doesn't implement the color interface. So what we can now do is we can create an adapter class that adapts this rainbow class to use our color interface so that it can be used by our video editor class without having to modify this source code. Okay, so let's create a rainbow color class, and the rainbow color class is one of our own classes. It's not part of this sort of installed package. So inside of the adapter folder, we're going to create a class called rainbow color, and this is going to implement our color interface. And if you remember from the UML, we need to store a field of type rainbow. And this is composition. So rainbow color is composed of or has a rainbow object. So let's also create a constructor. And we can pass the rainbow object in here. Okay, and then in our apply method, we can actually interact with our sort of third-party rainbow object now. So we can call rainbow.setup. So this is something that the third-party library requires us to do. So we call setup. And then once we've set up the rainbow object, we can call the update method and pass the video. So now we have a rainbow color class which implements color that we can now pass to our video editor apply color method and use this rainbow color now as we would any other of our color classes. So we can now apply rainbow color to our videos just like the other colors. So let's now go into our program.cs file and let's see if we can apply a rainbow color. So let's call this rainbow color, and inside of rainbow color we need to pass the rainbow object. So let's see, and this is part of the third-party package. So there we go. So now we can apply our rainbow color just like we would our custom colors. So you can see here that rainbow color is a wrapper that translates one interface into another. So now to use any other color from this third-party library, we can create a new wrapper or adapter class to make it compatible with Video Editor, satisfying the open-closed principle. So we actually created our adapter via composition. So you can see here our rainbow color adapter class is composed of a rainbow object, and this is our third-party color that we have adapted into an object of type color. So we can also use inheritance to create our adapter classes. So let me show you how we can use inheritance instead of composition to create an adapter class. So let's create a new class called Rainbow Adapter. And what we're going to do here is we are going to inherit from the third-party rainbow class. And we're also going to implement the color interface. So let's implement that by pressing command and dot and implement the interface. So what we can do here is, let's just have a look what we did before. So we can see here, because rainbow color, our sort of previous rainbow adapter, is composed of rainbow, we have to call the methods on this rainbow object that we passed into rainbow color. Whereas here, we can call the methods directly because they've been inherited by the rainbow class. because you can see here this third-party rainbow class has a setup method and an update method, and we are inheriting them, so we can just call them directly, like this. Okay, so this does exactly the same as what our rainbow color adapter did. So these adapters both do the same thing, but one's using inheritance and one is using composition. So with inheritance, the rainbow methods can be called directly. Now, the problem with this inheritance approach is that it's not as flexible as using composition, because in C#, a class can only extend one class, and in this case, the rainbow adapter is extending this rainbow class. And in this case, this is okay. It's okay to use inheritance here because color is an interface. But you can see that inheritance is less flexible than composition, and therefore composition should be preferred. And that is because if color wasn't an interface and it was some sort of class that we'd need to extend, then you can see that C# would give us an error, because this rainbow adapter would then need to extend two classes, which is not allowed in C#. So as you can see, composition gives us more flexibility than inheritance, and therefore should be the preferred option. The bridge pattern is a design pattern that separates a large class or a set of related classes into two separate hierarchies so that they can be developed independently from each other. So say that we have a remote for controlling radios, and there are multiple different brands of radio, and there are multiple different types of remotes. So in this diagram we have an abstract class for what a remote should look like, and then extending remote or inheriting from remote is the LG remote and the Sony remote, and LG and Sony are different brands of radio. And then we have another different type of remote called advanced remote, which extends or inherits from this remote class. And underneath here we can see that we have an advanced LG remote and an advanced Sony remote. We then have another different type of remote called a mega remote, which will have some additional functionality that extends from remote. And then we can see that we have the brands LG and Sony for the mega remote. So here we can see that every time that we add a new brand, for example Samsung, we'd have to create 3 new classes. So we'd have to create Samsung remote, advanced Samsung remote, and mega Samsung remote. And if we create a new type of remote, for example radio and TV remote for controlling both a radio and a TV, then we'd have to create a new class for every brand of radio. So we'd need to create a radio and TV LG, radio and TV Sony, and radio and TV Samsung. So you can very easily see that this is not a maintainable solution. So let's have a look at how this looks in code. Here we have our base remote control class, which is an abstract class with 4 methods for controlling a radio. So we have a method for turning the radio on, turning it off, for turning the volume up and turning the volume down. So let's now create our advanced remote abstract class. And this is going to extend the remote control class. And as you can see, we're getting an error here because it's not implementing the inherited abstract methods from remote control. But we can solve that by making this an abstract class. And now we're just going to add an extra method called setChannel, which takes an integer of the channel number that we want to set the radio to. Okay, so this is now our advanced remote with 1 extra bit of functionality. Let's now create our radio and TV remote. So this is another type of remote control that can control both a radio and a TV. So let's call this, let's see. Radio and TV remote. Okay, and this needs to again extend or inherit from remote control, and this needs to be an abstract class. Okay, so then what we're going to do is we're going to add a couple of extra methods in here, and we're going to have a control TV and a control radio method, so we can select which device we want to control. So if we can call this method, we're controlling the TV. If we call the control radio method, then we will control the radio. So now what we're going to do is we're going to implement these remote control types for LG devices, so the LG brand. Okay, so we're not going to implement them for all of the brand types because that will take way too long. So for brevity, we will just implement these remotes for LG devices for now and not worry about Sony or Samsung. So what we will do is we will create the basic LG remote. And this needs to inherit from remote control. We then need to implement this abstract class with all of these methods. And to save a little bit of time, I'm just going to copy and paste these in for now to save some time. So let's see. Okay, so I'm just logging the some different stuff here. So if we call turn off, we just say turning LG radio off. And we also need to add the volume up method. Okay, so we're now implementing all of the abstract methods from remote control. So now let's create our advanced LG remote. And this is going to inherit or extend the advanced remote class. And then again, I'm just going to copy and paste to save us some time here because it's all very basic stuff. We just need to implement all of the methods from advanced remote control. So it's all the same as the regular LG remote, but we also have this additional set channel method. And finally, let's create the LG radio and TV remote. So let's create that. And this needs to inherit from radio and TV remote. And we can then implement the methods. So we have control radio, and we have all of the methods that we had before. Okay, so we just have an additional 2 methods here for controlling the radio or controlling the TV. Okay, then we can use this solution in a client. So if we go to our program.cs file, and let's empty this out. So first of all, let's create a LG remote. And let's just turn the radio on. And then turn the radio off. Okay, that's all working correctly. And then if we create an LG radio and TV remote, okay, so this needs to be LG radio and TV remote. And then we can control the TV and turn it on and then turn the volume up. Okay, so we control the TV. Now controlling LG TV, we turn the TV on and then we turn the volume up. So let's check that that is working correctly. Okay, so that solution is all working correctly. However, this solution is very inflexible because every time we add a new remote type, we need to create a new class for every brand of TV. And every time we add a new brand, we need to create a new class for every remote type. And the reason that we ended up with this structure is because our hierarchy is growing in 2 dimensions. So we have the abstract dimension, or the remote type, and an implementation dimension, which is the brand of the device. So we saw before that we have a structure that is growing in 2 dimensions, both the remote type and the brand dimension. So to simplify this hierarchy, we can break it down into 2 separate hierarchies. So here we have a sort of remote type hierarchy on the left, and on the right we have a sort of device or brand hierarchy. So you can see that these 2 hierarchies are connected via a bridge. So you can see here that remote control is actually composed of some sort of device, and it talks to each device via the device interface. So you can see here the remote control has a turn on method, and within this turn on method it just calls the device.turnOn. So it uses polymorphism to turn on the device, and it doesn't require any knowledge of the specific device that it is turning on because it's coded to this device interface. Okay, so whenever we have an hierarchy growing in 2 separate dimensions, we need to split them in half and connect them using a bridge, so that the 2 hierarchies can then grow independently from each other, meaning that we don't have to create a subclass for every combined remote type and brand. So let's now implement this solution in code so that it makes more sense. Okay, so first of all, we're going to create our device interface. And this is going to contain 3 methods. We're going to have turn on, turn off, and set channel. And the device interface defines all of the methods that a device should have. And currently we're just going to have these 3 methods. We're not going to worry about any other methods such as turning the volume up or turning the volume down. We're just going to keep it simple for now. So next up, we're going to create our remote control class. This is like our base remote control class. And remote control needs to be composed of a device. So we're going to say private device, and then we're going to pass a device into this remote control class via the constructor. Okay, so now we can define what a basic remote control should do. So a basic remote control, just like beforehand, if we go into our remote control from before, a base remote control can turn a radio on, or it can turn a radio off. We're not going to worry about volume up and down for now, just to keep things a little bit more simple and short. So let's create, first of all, the turn on method. And in here, we can just call device.turnOn, because we know that all devices will have a turn on method. We can then create a turn off method and simply call device.turnOff. Okay, so this doesn't matter what the brand of device is, whether it's LG, Sony or Samsung, because it's coded to this device interface, we can just simply call these methods on the device without checking what the brand of device is. Okay, so we're using polymorphism here, which makes our solution nice and flexible. Okay, so let's just leave it as that for now, keep things simple. So let's now also create our advanced remote control class. Let's see. And this needs to inherit from our base remote control. And this should be we need to generate the constructor and pass the device up to our base remote control class. Okay, so the advanced remote is going to do everything that a remote control can do. So it's going to inherit our turn on and turn off methods, but an advanced remote can also set the channel. So let's add a set channel method. Okay, so you can see that an advanced remote can do everything a remote control can do, but it can also set a channel by passing an integer of the channel number. Okay, so let's now go ahead and create our devices, our sort of concrete devices. So first of all, we're going to create an LG radio device. So we're going to call this LG radio, and this is going to implement the device interface. So let's implement all of those methods, and you can see here that in LG radio we need to implement all methods from device, and it doesn't matter. We're not actually worrying about whether this is going to be an advanced device or a regular base sort of remote. The remote type is no longer related to the device. We control the sort of limitations of what we can do within these remote control classes. So in remote control we can specify that if we have a remote control we can only turn on or turn off the device, whereas if you have an advanced remote control you can turn on, turn off, and also set the channel. And within these concrete device classes we just implement all of the methods possible for any different type of remote. So now what I'm going to do is I'm just going to copy and paste these methods in to save some time, because all we're doing is, well, we're doing exactly as what we did previously. So we're just logging a few things out when we call these methods. So let's also create a Sony radio now. So a Sony radio device. And again, this is going to implement device. And I'm just going to copy and paste these in to save some time. Okay, so you can see that Sony devices can be turned on, turned off, and we can also set the channel. Okay, so now let's have a look at how a client would use this solution. So you can see previously, if we wanted to control an LG radio with a radio and TV remote, we had to create this very specific subclass. So this solution is going to be a lot different. So let's actually create an LG remote control. In fact, let me just comment this out so you can see the sort of differences a little bit more clearly. So first let's create an LG remote control. And this should be a structural dot bridge dot good. Okay. So a remote control, you need to pass the device that we want to control. So the brand of device that we want to control is an LG radio. So we're going to pass an LG radio into here. And now if we call LG remote control dot turn on, and we can also turn the device off. So let's actually run this program, and you can see that that works correctly. So now we can see that we have two separate hierarchies. We have the remote type, which is separate from the brand or device type. Okay, whereas beforehand we were sort of combining them into subclasses. Here we have an LG sort of radio and TV remote. So radio and TV remote is the remote type and LG is the brand. Whereas now we are creating a new remote control object. So the remote type we specify here, and then we pass the device that we want to control. Okay, so we've separated the two hierarchies and we've connected them using this bridge, this device bridge. Okay, So let's also now have a look at how we could create an advanced Sony remote control. So let's do that. So here we specify advanced remote. We're not saying Sony advanced remote. And then to make this an advanced Sony remote, we just pass the Sony radio device, or the sort of brand that we want to control. And then we can pretty much do what we did before. So we can turn on, we can turn off, and we can also, let's see, set the channel to some channel number. So if we run this, we can see that that is all working correctly. So now, as remote control, our remote control class is now delegating. Okay, you can see here it's delegating the work to the device via the bridge, and the bridge is basically composition. So the device hierarchy and the remote type hierarchy can now grow independently from each other. So now if we add a new brand of radio, we only need to create one new class. So our code is now more flexible and easier to maintain. The proxy pattern is a structural design pattern that provides a proxy or agent object to control access to another object, allowing for additional functionality such as caching, logging, lazy loading, or access control without changing the client's code. So you can see here we have some sort of client object which is trying to reach a target object, but it has to go through this proxy object before getting to the target. So you can see that this proxy is like a sort of in-between object. So let's say that we have an application that fetches a list of YouTube videos from YouTube's API and displays those videos in a list. In our application, we are using a third-party YouTube package to handle fetching the YouTube videos from the YouTube API, and then we render the video on the screen with the video controls. So the problem is that every time a request is made to our application, our server has to re-download the videos from the YouTube API, and this takes a long time, especially if lots of requests are made to our application at one time. So here is the interface for what a video object would look like from our third-party video library from YouTube. So this is an interface called video, and we have a render method as well as a getVideoID, which returns the string ID of the video. And we also have in this third-party package a YouTube video class, which is a class again from the third-party YouTube library, which essentially creates YouTube video objects by fetching the video from the YouTube API via its video ID. So in the constructor you can see here that we pass the video ID that we want to fetch from the YouTube API, and then the video starts to download. So as you can see, whenever we create a new YouTube video object, it downloads the whole video. And as you can see here, we just log downloading video with video ID from the YouTube API. And then we also have a render method for rendering the video onto the UI. And we also have a method for getting the video ID. Okay, so that is basically the sort of third-party package that we would be dealing with for YouTube. So let's actually now create the code that would be part of our source code. So we're going to create a class called video list, and this is outside of the YouTube third-party package. This is our own sort of custom code now, and we're going to have a dictionary to store a list of videos. And then we're going to have an add method for adding a video to this list. And this should be a video.getVideoID. So it looks like I've imported the wrong type of video here. So let me import the correct one. So it should be from Proxy, Bad, Example, and the third-party package. Okay, so now we should be able to get the ID. There we go. And we're going to pass in the video. Okay, so as you can see, this dictionary has a key, a string key, and the string key is going to be the video ID, and the value for that key is going to be the actual video object itself. So next thing we want to do is we're going to create a method called watch. And this is going to take a video ID. It's going to get the video from the video list. And we can do that by accessing the video ID value. So we're getting the video at this key, and we can then call video.render. Okay, so that's everything we need to do in our video list. So we store a list of videos with a string key, which is the video ID, and then we store the value as the actual video object itself. So let's now take a look at how we could use this solution inside of a client. So first of all, let's create a video list. And then let's create a sort of list of video IDs. And let's call this video IDs. Okay, so just some random strings there. And then let's loop through these video IDs and add them to our video list. Okay, so here we loop through all of our video IDs, and for each ID we are adding to our video list a new YouTube video, and we pass the video ID to the YouTube video class, and if you remember, this class will download the YouTube video whenever we create this YouTube video object. So it automatically downloads. Okay, so then what we can do is let's actually watch a video. So let's say we want to watch the video with ID ABCDE. So we can say video list dot watch, and we can pass the ID of the video that we want to watch. So let's run this now to check that it's all working correctly. And we can see that we are downloading all of these videos. So 1, 2, 3, 4, A, B, C, D, E, and Java SC 1, 2, 3, all being downloaded, and then we render the video with ID A, B, C, D, E. So this one is ready to watch on the screen. Okay, so just adding a video to our video list causes that whole video to be downloaded. So even if the user doesn't want to watch that video, it's still going to be downloaded. And the user here only wants to watch the video with ID ABCDE. So it will be much more efficient to download the video only after the user has selected a video from the video list. And this is called lazy loading, or delaying the loading of something for when it's actually required. So the problem is that our YouTube video class is from a third-party library, so we're unable to modify its source code. So the solution to this is to use a proxy object, which we create ourselves. So you can see here that the video list, our video list, is no longer going to be talking directly to these third-party YouTube video objects. Instead, it's going to be talking to these video proxy objects which we are going to create, and these video proxy objects are going to lazy load these YouTube video objects. So here is the UML for the solution that we are going to come up with. So as you can see, our video list object will now talk to video proxy objects instead of these third-party video objects, and this UML shows that our video proxy object will implement the third-party library's video interface, which is this interface here. So this comes from our third-party package, and this means that we can add these video proxy objects to our video list, and video list won't care whether it's a third-party video or a video proxy as long as it is of type video. So you can see here that video proxy, which we're going to create, and the third-party YouTube video class both implement this third-party video interface, meaning that they can be treated the same in our video list. So now inside of our video list, we can add video proxy objects instead of our third-party YouTube video objects, which gives us some control over when the video is downloaded. So inside of the render method of a video proxy object, we can see here, we can check if the video field is equal to null, and if it is, we then create a new YouTube video and then render the video. So now a third-party YouTube video is only going to be created when the render method is called, which means that when the user actually wants to watch the video. So no videos are going to be downloaded until the user actually wants to watch them. So here is the gang of 4 UML for the proxy pattern, and as you can see, we have our client, which is talking to a subject, and we have a real subject and our proxy object. And you can see that the proxy object both implements the subject just like the real subject does, meaning that it can be treated the same as the real subject in our client. But it means that we can also run some custom code before we call the real subject's request method. And some things that we might want to do are lazy load or cache and or log some information before we call this request method on the real subject. So let's now implement this proxy pattern solution in code. So the first thing that we're going to do is we are going to create our YouTube video proxy class. So we're going to come into, we're not going to make this inside of the package, by the way, because this is our own code. Whereas this package, remember, is our third-party library code that we wouldn't actually have access to in a real application. So let's go ahead and create the YouTube video proxy class. And this class needs to implement the video interface from our third-party library. So we have a lot of videos here, so I believe it could be any one of these. Let's try this one. And okay, is this correct? Okay, I think that's correct. So yeah, we are implementing the video class from our third-party YouTube package, and then we need to actually implement the interface. Okay, so inside of this class we need a couple of fields. So first of all, we need a video ID field, and we also need a field for storing a reference to the actual YouTube video, and this is going to be of type YouTube video from our third-party library. So I've been a little bit inconsistent here with capitalizing the T's, but it'll be okay. So let's now create a constructor so we can pass in the video ID for the video that we want to download and watch. So we're going to create a public constructor called YouTube Video Proxy, and we're going to pass in the video ID. Okay, we're not passing in a video. Okay, so now what we need to do is let's actually return the video ID here, and then implement our render method. So inside of render, we want to actually lazy load the YouTube video. So if I just quickly show you what a YouTube video looks like from our third-party library, you can see that the YouTube video is downloaded as soon as we create one of these YouTube video objects. And we want to lazy load the video. So you can see here, whenever we create a YouTube video proxy, we just pass the video ID and we don't actually create one of these YouTube video objects, because if we do, it's going to download the video. And we only want to download the video once this render method is called, which means that when the user clicks on the video to actually watch the video. So what we can do here is we can check to see if the YouTube video is equal to null. So let's check if video equals null. And if it does, we can then set YouTube video equal to a new YouTube video. And in here, we pass the video ID that we want to watch. Okay, so this means that if the render method is called multiple times, then it's still only going to download the YouTube video once. It's only going to create this new YouTube video one time, because once this has already been called, YouTube video will no longer be null. Okay, so finally, we can call YouTube video dot render. Okay, and that's going to render the YouTube video. So we are now lazy loading YouTube videos with this YouTube video proxy. So now that we have these video proxy objects that implement video, we can now in our client, we can add these proxy objects in place of the real YouTube video class. So here we are adding YouTube videos, but instead what we can do now is add YouTube video proxy objects instead. So let's do that. And what we want to do now is get rid of our previous example code. Okay, so this all looks okay. So that's all we've done. We've just changed this from YouTube video to YouTube video proxy, and our video list doesn't care whether we add YouTube video proxies or whether we add real YouTube videos, because as far as the video list is concerned, they both implement the third-party video interface, and it can treat them as the same using polymorphism. So now let's see what happens. Okay, so when we watch the video, we can see that the video is downloaded from the YouTube API and the video is rendered. But if I comment this out, let's see what happens. So you can see nothing is logged to the console when we add videos to the list. Whereas beforehand, if you remember, let's actually show you what happened beforehand. So YouTube video. And let's play this, run this. You can see that even before even if the user doesn't click on one of these videos to watch them, whenever we add them to the list or create one of these new YouTube videos, the video had to be downloaded from the YouTube API. So this would take potentially quite a long time. Whereas now, using the YouTube video proxy, you can see that no videos are actually downloaded until one of those videos is clicked on or the user wants to actually watch one. So the video that we want, the videos are now lazy loaded. So the only video that is actually downloaded is this ABCDE video because the user actually wants to watch that one. The Flyweight pattern is a structural design pattern that aims to minimize memory usage by sharing common state between multiple objects, allowing for efficient handling of large numbers of lightweight objects with shared characteristics. So say that we have a farming game that includes different types of crops, such as potatoes, carrots, and wheat. And each crop is represented by a crop object that includes its X and Y coordinates, the crop type, and an icon for that crop. So here is the UML with its x-axis position, y-axis, the type of the crop, and an icon. And the crop type you can see here is an enum, which will have type of either potato, carrot, or wheat in our example. And we have an icon, and icons can be represented by an array of bytes. Okay, so here we have our crop type enum, which can take the value of either a potato, a carrot, or wheat. So these are the three crop types that we have in our game. So let's now go ahead and create the crop class. And a crop has a position on the screen, so an X and Y coordinate. It also has a crop type field. And it also has an icon, which we can represent as an array of bytes. Okay, so let's now create a constructor for this crop class. This needs to be of type crop type, and then we can set the values, set the fields, and finally this crop class needs a render method for rendering the crop onto the screen. So I'm just going to log drawing the crop type at the position of X and Y. Okay, so that's everything we need to do for this crop class. So let's now create a crop service class, which is essentially going to be used to fetch our crops. And these are going to be stored in probably some database. Okay, so let's create a method called getCrops. And this is going to return a list of crop objects. Okay, so let's first of all create a crop list. And then let's simulate fetching our crops from a database. So here what we can do is we can create some crops. So I'm going to say var carrot equals new crop, and we can say it can be at position 1, 4, and it can be a crop type of carrot. And I'm just going to pass null for the icon just for convenience rather than creating an actual array of bytes. So let's also create a few more carrots. So let's just call this carrot 2 and carrot 3, and let's just change the position that it will be rendered on the screen. Okay, so that will do. So that's kind of like simulating fetching our crops from a database. So next thing we can do is we can add these crops to this crop list. So we can call crop list dot add, and then we can add a carrot, and then we can also add carrot 2 and carrot 3, and then we can return this crop list. Okay, so you can see this kind of crop service, get crops method is just sort of simulating what we would do in a real application, which is probably fetch the crops from the database and then return the sort of list of crops. And each crop knows its position that it should be rendered, its type of crop, and also the icon for that crop type. Okay. So using this solution in a client now, so if we go into our program.cs file, we can first of all create a crop service. And we can then loop through our crops and render them on the screen. So we can say var crop in crop service dot get crops, and then we can just call crop dot that should be crop dot render. Okay, so now if we run this program, we can see that we are drawing all of our carrots at the correct position on the screen. So the problem with this solution is that for every carrot or crop that we create, we are storing a new object with all of the information about a carrot stored within that object. So this means that if we create 1000 carrots, then we'll be storing 1000 carrot icons in RAM. And that's going to take up lots of memory, and many mobile devices will struggle to handle that. So if we actually have a look at the crop object, we can see that this takes up 4 bytes. So integers take up 4 bytes. This is 4 bytes. The crop type is also 4 bytes. And the icon will be around 40 kilobytes. So if we actually create a new icon for every single crop that we create, if we have, say, 1000 crops in the game, that will be 1000 times 40 kilobytes, which is 40 megabytes for 1000 crops. And that is a lot of RAM for smaller devices such as mobile phones, and the game may slow down, lag, or crash. So this is not ideal. So what if we could share icons between crop objects of the same type? So if we have, say, 300 carrot objects, what if all of those carrot objects could share one single carrot icon rather than creating 300 of the same icons? So if a carrot is created with the crop class, then its icon and crop type fields will remain constant for the lifetime of the object, but its X and Y coordinates will vary as the crop can be harvested and moved around. So state that remains the same throughout the object's life is called the internal state of the object, and state that can be changed is called extrinsic state. So you can see within our crop object, the X and Y coordinates are dynamic. They can change throughout the crop's life cycle. So these are called extrinsic state. And the crop type and the icon are constant throughout the crop's life cycle. So a carrot is never going to become a potato, and a carrot is also never going to look like a potato. So this is constant, therefore we call it the intrinsic state of the object. So if we can extract the intrinsic or constant state out of this crop object or crop class and place it into a new object called crop icon, then we would only need to create 3 crop icon objects for potato, carrot and wheat in our application. Even if there are thousands of crops in the game, we only need to create 3 of these crop icon objects, and this is going to save a lot of memory. So we can then, for example, just have 1 carrot icon object stored in memory. Then all crops of type carrot can reference or reuse that carrot icon object throughout the game. So you can see here we have our crop with its X and Y dynamic fields, and it's composed of a crop icon object, and only one of these crop icon objects are going to be created per crop type. So carrots are going to all share a single crop icon object for carrots, and potatoes will also share a single crop icon object for potatoes, etc. So an object, again, an object that contains only intrinsic state is actually called a flyweight object. Okay, so let's just remind ourselves, the intrinsic state is the constant state, and you can see here an object that contains only intrinsic state is called a flyweight. So this crop icon object is going to be our flyweight object. But it should be noted that we shouldn't create crop icon objects directly. So we can create a factory class that creates an icon depending on the icon type and caches that icon in memory, ensuring that it's only stored in one place and ensuring that it's only created once. So here is the overall structure following the flyweight pattern. So we have our crop with its extrinsic state. We have our crop icon with the intrinsic state, so the constant state. We then have a crop icon factory, which is essentially going to ensure that crop icons are only created once per crop type and stored in a single place in memory. And then we have our crop service, which is going to sort of simulate getting our crops from the database and creating a list of crop icons. So here is the gang of 4 representation for the flyweight pattern. We can see that we have our flyweight object with some sort of repeating state. We then have our flyweight factory, which caches flyweight objects, ensuring that they are only created once. And then we then have our context, which in our case is like our crop object, with its unique state or its dynamic state that's going to change. It stores a reference to the flyweight object, and we then have some operation. So flyweight.operation with its unique state. Okay, so let's now implement this flyweight pattern for our farming game. So we are now going to refactor our code to follow the flyweight pattern, and we're going to basically store these fields inside of a separate class so that it can be cached in memory and we don't have to create multiple icons for the same crop. So we still have our crop type enum, so nothing's going to change there. But inside of our crop class, we no longer need these fields. Okay, so we're actually going to instead reference a crop icon object, which we haven't created yet. So VS Code is going to give us an error, and let's call this crop icon. And inside of our constructor, we can again remove these fields because we're not going to pass these anymore. We're instead going to pass a crop icon. And VS Code is going to give us again an error, and we can set this crop icon equal to crop icon. Okay, so in here we no longer have direct access to this crop type field, so instead we can call crop icon.getType because we are going to provide that method on the crop icon object. Okay, so that's everything that we need to do in our crop class, and we now have some errors that we need to fix. So let's go ahead and create the crop icon object. Okay, so this is going to be our flyweight class that stores intrinsic or constant state, the state that remains constant throughout the object's life. Whereas our crop class is storing our extrinsic state or our dynamic state that is going to change throughout the object's life. So in here, we can store two fields. So we're going to store the crop type, and we are going to store the icon, which is going to be, again, an array of bytes. And what we can do is we can actually make these fields read-only to ensure that once they are constructed, they cannot be changed. So let's make those read-only. Okay, so let's create our constructor now. Okay, and remember we also need to create a getter for the crop type so that we can get the crop type inside of our crop icon, inside of our crop object. Okay, so I think that is everything we need to do here. So now we need to create our crop icon factory class. So this class is going to ensure that each unique crop icon object is created only once. It is cached and then reused or shared between the crop objects. So first of all, let's create our crop icon cache. So this is going to be a dictionary, and in here the key for the dictionary is going to be crop type, and the value is going to be the crop icon. Okay, so now let's create our getCropIcon class, which is going to essentially ensure that icons are only created once per crop type. So here we are going to return a crop icon. That should be crop icon, and we're going to call this getCropIcon, and it's going to take a crop type that we want to get the icon for. So if we want to get the icon for a carrot, we can pass crop type.carrot into this getCropIcon method. So first thing we need to do is we need to check if the icon already exists inside of our cache. So I'm just going to make a little comment here to say that this is our cache. So what we can do is we can say that if icons, and this needs to be negative, so if icons does not contain key of the crop type, then that means that the icon does not exist in our cache, which means that we need to create one and add it to our cache. So let's create an icon. So var icon equals new crop icon, and we can pass the crop type, and for the icon I'm actually just going to pass null, and I'm just passing this again for convenience, but this could be, for example, a reference to some file location of the image. But just to keep things simple, I'm passing null for now to not make things too complicated. So once we've created our crop icon class, we can add this icon to the dictionary. So the key is going to be the crop type, and the value is going to be this crop icon object. Okay, so finally, if we get to here, we know that the icon exists. So the icon either already existed, so this wasn't necessary, so this conditional, we just skipped this bit here, or if the icon didn't exist, we created a new one. So if we get to here, we know that we have this icon, so we can return icons and access the crop icon object via its crop type key. Okay, so this all is looking good. So we now have our crop icon factory, which is ensuring that each crop icon object is only created once per crop type. Okay, so finally we can come into our crop service class and we can now do some refactoring in here. So crop service needs to store a reference to the crop icon factory. So we can create a field called crop icon factory, and we can call this icon factory, and we need to pass this via the constructor. Okay, so let's have a look at our getCrops method. So we are storing a list of crops, so we don't need to change this, and then we simulate fetching the crops from the database. So this is where we need to make some modifications. So we can see here that now in our crop class we are no longer passing the sort of constant state, okay, because this is now stored in our Flyweight object. So instead of passing the crop type and the icon, we now use our icon factory to create a crop icon object. So we can say icon factory dot get crop icon, and then we pass the crop type that we want to get. So we can say crop type dot carrot. Okay, and all of these carrots now are going to be sharing the same crop icon object, which is stored in cache due to our icon factory. So this is exactly what we want. And then here we add our crops to the crop list and return the crop list. Okay, so now let's go into our program.cs file, or our sort of client, and let's see how we now use this new solution using the Flyweight pattern. So here we create our crop service, and we can see we have an error here. So there is no argument given that corresponds to the required parameter icon factory of crop service.crop crop icon factory. So you can see here that we need to pass a crop icon factory. So let's go ahead and pass that in. And we are now doing exactly what we did before. We are looping through our crops and we're calling crop.render. So as you can see, there's not much difference in the way clients use this class. We just, the way the client uses this solution. We just now need to pass a crop icon factory to the crop service to ensure that, so that this is actually handling the creation of crop icons. Okay, so now if we run this file, run this program, you can see that we get exactly the same as what we did before, which is perfect. So to summarize, we have created 3 carrot crop objects, but only 1 carrot crop icon object. So this solution will save lots of RAM when rendering many crops at one time. The Facade pattern is a structural design pattern that provides a simplified interface to a complex system, encapsulating the complexities of multiple subsystems into a single unified interface for clients. So say that we have an e-commerce application that allows users to submit orders. Here are the steps involved in that process. So we have a user that is submitting an order, and then we have a server which has multiple steps for handling this order. So first of all, we have to authenticate the user, check inventory, so make sure that we have enough of the items that the user wants to purchase. We then connect to some payment service such as Stripe. We then fulfill the order, which might involve something like reducing the inventory, and then we charge the user, and send them a response, which can either be successful, or if any of the steps fail, then we can send some sort of failed response. So as you can see, there are 5 main steps involved in processing an order. So let's first of all implement this roughly in code. So I've created some classes to simulate the steps involved in processing an order. So let me show you what we have here. So we have an order request class, and this is going to be the request object containing the user's submitted data. So say that the user has some form, they enter their name, their card number. We also send the amount for the order, the address of the user, and the item IDs that the user wants to order. Okay, so this is like the order request object. We then go through some authentication steps. So I've just created an empty class for now to keep things super simple, but this might check the user's session, checks whether the session is valid, that their username all checks out. And then we have an inventory class with a couple of methods, so we can check the inventory for the item IDs, and we also have a method which can reduce inventory by a certain amount for the specified item ID. Okay, so and check inventory, we're just going to return true, so we're always going to say that we have an item in stock. And then we have a payment class for handling the payment step within the order process, and here we can set the name, card number, and the amount that the user owes for the order. And then we have a method called pay, which is going to simulate maybe connecting to some payment service and charging that user's card. And then next up we have an order fulfillment class, which is going to check the inventory, that we have sufficient inventory. So we can see here we have a fulfill method, which is going to loop through the items in the item list, so the items that the user wants to use, and it's just going to reduce the inventory of those items in the loop. And we also have, we've also logged inserting the order into the database, so that we have record of this order in our database, a sort of permanent record. So these are just sort of classes that are simulating the steps involved in the order process, just sort of some rough code that we can use to sort of demonstrate this example. So this is now the sort of important bit. So I'm going to show you how a client would actually use this solution. So first of all, we can create an order request object. And this is going to be equal to a new order request. We can then create our authentication object. We then need to create our inventory object. And in here, what we can do is we can loop through our order request item IDs. So you can remember in our order request object, just for convenience, I've sort of hard coded these values in. Obviously, a real order request wouldn't have these values hard coded in. I've just done that for convenience. So what we can do is we can loop through all of the item IDs in the order. So we can say order request dot item IDs, and then we can check the inventory for each item ID, and this is always going to return true, so we don't have to worry too much about that. This is just a quick rough example. Then we can create our payment object, so we can say var payment equals new payment, and in here we can pass the some information from the order request object. So we can pass the name, the card number, and the amount for the order. Okay, then we can call payment.pay. And finally, we need to do the order fulfillment. So let's create our order fulfillment object. And this should be lowercase. And in here, we just need to pass our inventory object. Okay, then we can call order fulfillment.fulfill, and we can pass the some information again from the order request object. So then we pass the address, and finally the order items, so the item IDs. Okay, so that's everything that we need to do for processing an order. Okay, so let's run this program to see that everything is working correctly. And we can see that we are charging the card with the name Danny. We insert the order into the database, and we are reducing inventory of all of the items that the user has ordered by 1. So we are fulfilling the order. So as you can see, every client that needs to make an order has to go through all of these steps to make a single order. So you can see here, every time we want to make an order, we have to go through all of these steps. And every client that needs to make an order becomes coupled to or dependent on 4 concrete classes: the authenticate class, inventory, payment, and order fulfillment. So if we had 10 classes that needed to make an order, then we'd have 10 classes dependent on these 4 classes. So that's a lot of coupling. So if one of these 4 classes changes, then that's going to be 10 classes that need to be updated. And this is not good, this is not maintainable. So each client that needs to make an order will depend on 4 classes. So here's the client, it's going to depend on these 4 classes. So let's now take a look at how we can solve this issue using the Facade pattern. So clients making an order don't actually care, or they don't actually need to know about the steps involved in making an order. They just want to make an order. So let's introduce a new class called order service with a single method called order that abstracts all of the logic so that all other classes that need to make an order only have to depend on this one class. So you can see here we've created an order class which has an order method that accepts an order request object. Now this order service class depends on these 4 classes, which are the sort of steps involved in making an order. So this order service is essentially containing all of the steps that we had here, all within this one method, so that now all classes that need to be able to make an order only need to depend on this one order service class, and not all of these individual sort of steps involved in making an order. So let's now go ahead and make our order service class. So this class is going to act as our facade that encapsulates all of the complexities and steps involved in making an order. So clients can then make orders without having to know about all of the details or steps involved in the order process. So let's create a single method called order that takes an order request object. And in here we can simply go through all of the steps in creating an order. And these are actually going to be exactly the same as what we have in our client over here. So let's copy and paste those in. Okay. So this is everything we need to do to make an order. And now inside of our client, we can remove all of this stuff. So all we need is our order request object. So this is our sort of incoming order request from the user, which contains all of the user's sort of inputted data, such as their name, card number, address, etc. We can then create an order service object. And we can then call order service dot order, and quite simply just pass this order request object. And now that's all we need to do to make an order. So let's run this and we should get exactly the same as what we got before. So we can see here exactly the same as what we had previously. So now clients can make orders without having to depend on many classes, and without having to know about all of the complexities involved in making an order, as all of these complexities have been abstracted away and encapsulated within this order service class. So now you can see it's much more simple for clients to make orders by using a Facade class. The Decorator pattern is a structural design pattern that allows behavior to be added to individual objects dynamically, enhancing functionality without altering the object's structure. And it's used to extend or modify the behavior of objects by wrapping them with additional functionality through composition. So say that we have an application that allows users to store data in the cloud. The data can be sent to the cloud as it is without any processing, or it can be compressed and or encrypted before it's saved to the cloud. So here's a UML diagram for a basic sort of almost naive solution to this problem. So here we have our cloud data class with a URL for the location where this data is going to be stored in the cloud. We have a constructor where we pass and set the URL, and we have a save method where we pass the data that we want to save to this URL location in the cloud. We then have some extra classes that extend this cloud data class and add some extra functionality. So we have an encryption class which also has a save data method, and here we are overriding the method in cloud data and adding some extra functionality to encrypt the data before it is saved. We also have a compression class which compresses the data before it's saved, and then we have an encryption and compression class which both encrypts and compresses the data before it's saved to the cloud. So far everything looks okay, but then the boss says that we need to create a new validation class to validate and clean the data before it's sent to the cloud. And we can see below that our code starts to look bloated, as we need to make lots of new classes just to add one extra feature. So you can see here our sort of class library is becoming very, very quickly bloated. So to add one new feature, this new validation feature, we have to create 4 new classes, and our class library is actually growing here exponentially. So this is not good, maintainable, or flexible. So let's see what this looks like in code. So first of all, let's create our base cloud data class. And this cloud data class needs to have a URL field. And we're making this a protected field so that the classes that inherit cloud data will have access to this URL field. If we made it private, then it wouldn't be accessible to all of this class's subclasses. So next up, we will create a constructor where we can pass the URL location of where we want to store the data in the cloud. So finally, we need to create a save method, and we're going to make this a virtual method so that it can be overridden in subclasses. And we're just going to make the data some sort of string to keep things simple for now. And we're going to log saving data to cloud at the URL location. Okay, so that all looks okay. So now we're going to create our compressed data class. and this needs to extend the cloud data class because we're adding some extra functionality. And here we can generate the constructor for cloud data. So we pass the URL location, and we can then override the save method inside of this class. Okay, so what we want to do here, let's remove this for now. So what we want to do is first compress the data. So I'm going to say for compressed equals compress, and then I'm going to pass the data to this method. So let's create this compressed, let's call this compress, and let's create a method called compress. And we can pass the data. And what we're going to do is we're just going to trim or sort of create a substring from the data. So we're going to return data.substring, and then we're going to go from the first character up to the 9th character in the, this will be the 8th character. So from index 0 to index 9 in the string. Okay, so we're just trimming the string down basically. And this is our way of sort of pretending or simulating compressing the data. So next up, let's create our encrypted data class, which will encrypt the data before it is sent to the cloud. And again, we need to inherit from cloud data, and we need to generate the constructor for the cloud data. And again, we're going to override the save class. And again, we're going to call base.save. So base is going to be the base class, which is cloud data. And we're calling the save method on cloud data and passing the data. But what we need to do is pass some encrypted data. So we can say var encrypted equals encrypt, and we're going to pass the data. So then we can pass this encrypted data to our save method. So let's actually create this encrypt method now. So this is going to be a public method that returns a string. It's called encrypt. It takes some string data, and we're just going to return some random strings. So we're going to pretend to encrypt the data. Okay, so this is like simulating encrypting the data basically. Okay, and we're going to pass that to our cloud data save. So here we encrypt the data, then we save it. Okay, so essentially we've added some functionality to this cloud data class by extending it. Okay, so finally let's create our compressed and encrypted data class. So let's create that. So we're going to say compressed and encrypted data. And again, we extend cloud data, generate the constructor, and we're going to override the save method. Okay, so in here what we want to do is we want to get the compressed data. And we want to pass the URL, which we have inherited from cloud data. And we want to call compress. And we need to pass the data to this method. So now we have the compressed data. Let's now encrypt this compressed data. So we can say encrypted and compressed equals new encrypt data, and we pass the URL, and then we can call encrypt and pass the data. And then we can pass this encrypted and compressed data to our base cloud data save method, so that we store it to the cloud. Okay, so this is everything that we need. So let's now go ahead in our program.cs file and use this solution. So I'm just going to copy and paste a few things in here to save some time. So here we have a URL for the location to store the data. So I've just put Google Cloud for now. We have our data that we want to save, and we have a boolean here that says compress equals true, and we have encrypt equals true. So here we want to store some data to this URL location in the cloud, and we also want to compress and encrypt the data. And this can essentially sort of simulate some sort of user input data. Okay, so the user might specify the location and the data they want to save, and whether they want to compress and encrypt the data before saving it. So now that we have the user this input data, we have to select the correct cloud storage object. So first of all, we can create our cloud data object. And we pass the URL. And then what we can do is we can add some conditionals to check whether we should compress and or encrypt the data. So we can say if compress and encrypt, then we can reassign cloud data to a compressed and encrypted data object. So we can say new compressed and encrypted data, and we can pass the URL. And then we can say else if compress, then we want to set cloud data equal to compressed data, and we pass the URL. Okay, and finally we want to check if we are just encrypting the data, and then we can say cloud data equals encrypted data and pass the URL. And that should be new encrypted data. Okay, so as you can see in the client, we have to check whether we should compress and encrypt, or just compress or just encrypt, and then we set the cloud data object equal to the appropriate class type. So finally, now that we know that we have the correct way of storing the data, we can simply just call cloud data.save, and then we pass the data to this method. So let's run this. Okay, so this seems to be working correctly. The data is being compressed and encrypted because these are both true. So as we discussed, our total number of classes is going to increase exponentially with this solution. But another issue is that we have to perform lots of conditional checks in the client whenever we use this solution. So for example, if we add a validated data class, then we'd have to add conditionals for encrypt and compress and validate, and also compress and validate, encrypt and validate, and also just validate by itself. So we'd have to have 4 extra conditional statements just to add one new feature. And this is really not good. And this is actually going to continue to get worse and worse exponentially as we add more classes or features. So this is a really bad solution. So let's now use a design pattern to solve this mess. So the solution to this is to move away from inheritance and use composition instead. So you may have noticed by this point that a lot of design patterns are based on moving away from inheritance and towards composition. So with composition, one object has reference to another object and delegates that object some work. And this allows you to use polymorphism and switch between objects at runtime, making your code more flexible. Whereas with inheritance, the object itself is able to do that work, inheriting the behavior from its superclass. So with inheritance, we have to create lots of new classes. With composition, we can wrap or decorate existing objects to add new functionality. So here we have the UML for the decorator pattern solution. So we can see here we have a data interface with a save method that accepts the data. We then have our cloud data class, which has, as before, the URL location for storing the data in the cloud. And we pass this via the constructor, and it has a save method which we have to implement from this data interface. We then have a data decorator class, and this also implements the data interface. And you can see here that we have a wrappee field, and the wrappee is essentially the object that is going to be wrapped. And in our case, that's going to be our cloud data object, because we're essentially, what we want to do is add additional functionality, or at least have the option to add additional functionality to this cloud data class. So we want to be able to add the ability to encrypt or compress, or both compress and encrypt. So here we can essentially wrap this cloud data object in a encryption decorator or a compression decorator. So you can see here we can pass the wrappee into the constructor, and we also have our save method because we are implementing this data interface. And then we have our sort of specific decorators. So this data decorator class is kind of like a little bit of a helper class that contains some sort of common logic for what decorators should be able to do. So if I just read this paragraph here, so above in this UML, we are making the encryption and compression objects decorators because they are decorating the cloud data object with some additional behavior. Because decorator classes have some common logic, for example, referencing a data source object, we have created a data decorator class where this logic can be inherited to prevent code repetition. So this means that encryption decorator and compression decorator will share some common fields and logic. And for example, in our case, both of these classes need to wrap the cloud data object. And this should probably be referencing a cloud data object. So essentially, our decorator classes are composed of, or are decorating or wrapping, a cloud data object, or any object that implements the data interface to add extra functionality. So let's take a look at the gang of 4 UML for the decorator pattern. And as you can see, it's basically the same as what we have in our solution. The only difference being the names of the classes. So if this isn't making much sense, then don't worry, because things will become a lot clearer as we code out this solution. So now we're going to implement our solution using the decorator pattern. So first up, let's create the data interface. And this needs to have a single method for saving the data. Okay, so next let's create our cloud data class, and this is going to be the class that we are going to wrap or add functionality to. In other words, decorate. So we're going to decorate this class with additional functionality. But first of all, let's actually create this cloud data class, and this needs to implement the data interface. So let's implement the interface. And in here, again, just as before, we need to store reference to the URL that we want to save to. So I'm actually just going to copy and paste what we had beforehand because it's exactly the same. So you can see here that we have a URL location for storing the data. We pass that via the constructor. Then we have a save method for actually saving the data. So this is exactly the same as what we had before. The only difference is that we are now implementing this data interface. So now let's create our data decorator abstract class. And again, this needs to implement the data interface. Okay, so this needs to store reference to some sort of data object. So this is going to be the wrappy object, or the object that we are decorating or adding functionality to. So let's create a protected field of type data. And the reason it's protected is because the encryption decorator and the compression decorator need to have access to this data field. So that's why we are making it protected and not private. So next up, let's create the constructor so that we can pass a data object to wrap. And then we can set the data object in the constructor. And then we have our save method. So we actually don't want to implement this method inside of the data decorator class itself. We want to make this method abstract so that it can be overridden or implemented in the compression and encryption subclasses. So we can make this an abstract method, and then we need to make this class abstract, and that is everything we need to do inside of this data decorator class. So now we can go ahead and create our compression decorator. And this needs to extend data decorator. We then need to generate the, we need to implement the class and also generate the constructor. So we're passing the wrappy object again to this base data decorator class, and we're also overriding this abstract save method from data decorator. So this is where we're going to add our compression logic. So this is going to actually be the same as what we had beforehand in our compressed data class. So we can copy and paste the save and compress methods from what we had before, and that is all okay. We just have an issue here because we actually need to say base.data. So we're now using composition here. So we call base.data to get the data field, and then we call the save method on that data field, and we can pass the compressed data. Okay, so that's all we need to do there. So I'm also just going to log whenever we call this save method so that it's easy to see what's going on. So I'm just going to put compressing data. Okay, so I think that's everything we need in our compression decorator class. So let's now go ahead and create our encryption decorator. And this needs to extend the data decorator. And let's now implement the abstract class and also generate the constructor. So you can see here that this data decorator is just a kind of class that makes it easier to create the different decorators. It's just basically a kind of helper class where we have some basic setup for a decorator, which is essentially just passing some sort of wrappy object into the class. And it saves us from having to write this logic inside of both of these classes. We don't have to bother recreating this. Okay, so it's just preventing a little bit of repetition basically. So here we have our encryption decorator, we have our constructor. So now we can implement the logic for encrypting and saving some data. So let's copy what we had before because it's not going to be any different in terms of the logic. So let's copy and paste those methods, and again, instead of calling base.save, what we need to do is called base.data.save. And then we pass the encrypted data. Okay, so that is everything we need to do. So now let's actually use this solution in the client. So what I'm going to do is I think I'm going to remove all of this. And I think I'll also remove this. And let's re-import these objects. Okay. So first of all, let's create our cloud data object. So this is going to be called cloud data, and it's going to be equal to new cloud data. And in here we need to pass the URL that we are saving to. Okay, so next up we can add our conditional statements. So we can say if encrypt is true, so if the user wants to encrypt the data before saving, then we can reset cloud data equal to new encryption decorator. So let me show you, actually this is going to be easier to just show you. So cloud data equals new encryption decorator. So we create a new decorator and we pass the cloud data to this class. Okay, so you can see here that we are wrapping or decorating the cloud data with an encryption decorator. Okay, so we're adding some additional functionality by wrapping this object inside of a decorator. Okay, rather than creating a new specific subclass. Okay, we're wrapping using composition instead of using inheritance and creating a new encryption data class like we were before. And now what we can do is we can say if we want to compress, so if we want to also compress or just compress alone, we can wrap this cloud data inside of a compression decorator. Okay, so that's all we actually need to do. Those are the only conditionals that we need. We only need to add one extra conditional for every type of feature that we have. So then at the end, we can call clouddata.save, and then we can pass the data. And then let's run this program. And we can see that we are compressing the data and then saving data to the cloud at google.com. So we are compressing and encrypting the data. If we make compress false, let's see what happens. We can see that we are just encrypting the data. If we make both of these false, let's see what we get. We just save the data as it is, and everything seems to be working as it should be. Okay, so this is perfect because now if we, for example, want to add a new feature, say a validation step, then we just have to add one more conditional. We just have to say if validation is true, then we can wrap in a validation decorator. We don't have to create a load of new subclasses. We just create one new decorator class, a validation decorator, and we just have to add one new conditional to the client. We don't have to create a validation plus compression, a validation plus encryption, a validation plus compression plus encryption subclass. We don't have to create all those subclasses and then add conditionals for all of those new combinations of steps. So this is a much more maintainable solution using the decorator pattern. So far we've looked at the behavioral and structural design patterns, but last but not least, we need to look at the group of creational design patterns. So first of all, massive congratulations on getting this far into the course, and your award is that creational design patterns are probably the easiest group of design patterns to learn and understand. So if you feel like giving up at this point, please don't. The hardest work has been done. So creational design patterns are a category of design patterns that focus on object creation, dealing with the best way to create objects while hiding the creation logic and making the system independent of how its objects are created, composed, and represented. So some benefits of creational design patterns are that they help to encapsulate object creation logic, hiding it from clients, and this promotes loose coupling and allows the system to be more flexible to changes in how objects are instantiated. And they enhance flexibility and extensibility by providing ways to create objects dynamically based on varying requirements or conditions, and this makes the system more adaptable to changes and new features. So we also have improved code reusability by encapsulating object creation logic in reusable patterns such as factories or builders. Developers can leverage existing patterns to create similar objects in different parts of the application, promoting code reuse. We also these design patterns also help to promote the separation of concerns. So creational patterns helps to separate the responsibility of object creation from the rest of the system's logic. And this separation of concerns improves code maintainability and readability. Creational patterns also provide support for dependency injection. So they often play a crucial role in supporting dependency injection by providing mechanisms to manage the creation and injection of dependencies, promoting modularity and testability. And if you're not really sure what dependency injection is, we will cover it throughout the design patterns, and it's a very, very common term that you'll come across in software development, and it's used in back-end frameworks such as Laravel, Spring Boot, or .NET. And creational patterns help to centralize the control over how objects are created, allowing developers to apply consistent instantiation strategies across the application. And creational patterns also encourage adherence to important design principles that we've covered earlier, such as abstraction, encapsulation, and separation of concerns, contributing to a more robust and scalable architecture. So in summary, creational design patterns offer numerous benefits that contribute to the overall quality, flexibility, and maintainability of software systems by providing effective solutions to object creation challenges and promoting best practices in software design. Each pattern addresses specific aspects of object creation, catering to different scenarios and requirements in software development. So now let's learn all of the Gang of Four creational design patterns. The prototype pattern is a creational design pattern that allows objects to be copied or cloned, providing a mechanism to create new instances by copying existing objects without explicitly invoking their constructors. And it's used to efficiently produce new instances with identical properties to existing objects. So say that we have a GUI, a graphical user interface, that allows the user to create new shapes on the screen, such as circles and rectangles. When the user right-clicks on a shape, an Actions menu opens up, and the user can then select Duplicate to clone the shape. So you can see here we have the original shape on the left. If the user right-clicks and then clicks on Duplicate from the Actions menu, the shape is duplicated and rendered on the GUI. So let's come up with a solution to this problem. So you can see here we have a shape interface with a draw method. And then we have our concrete shape classes that implement this shape interface. And then we have a shape actions class that contains the logic for duplicating each shape. And this duplicate method and this shape actions class is dependent on all of the shapes that can be duplicated. So you can see here that we can see that this class depends on all of these concrete shapes and that's represented by this dotted arrow. So can you see the issue with this solution? And can you also spot what solid principle we are violating? And as we code out this solution, the issue here is going to become very obvious. So let's go ahead and do that. So first of all, let's create a new folder for our creational design patterns part of the course. And then we'll create a new folder for this prototype pattern. Okay, so first of all, let's create the shape interface. And this is going to have a single method called draw. Now let's create a few concrete shapes. So let's first of all create a circle. And this is going to implement the shape interface. Okay, so we have the draw method here. And let's just log here drawing circle. Okay, so we also need to give the circle a property for its radius, because all circles need to have a radius. So we'll say public int radius, and then we'll give it a getter and setter. Okay, so they're nice and simple. And I think what we'll do, so whenever the user sort of creates a circle on the screen, so if they click, a little circle icon that produces a circle to appear on their canvas, then I think it would be nice to give it a default radius. So let's give it a default radius of 5 for all newly created circles. Okay, so next up, let's create the concrete rectangle shape. And again, we implement the shape interface, and all rectangles have a width and a height. So let's go ahead and give it a width and height property. And also a height. And again, let's give it a default height of 10 and a default width of 5 and a default height of 10. Actually, no, we'll go with 10 and 5. Okay. Okay, so let's just log drawing rectangle here. Okay, so that's all we need to do for our shapes. So now we can create our shape actions class, which is going to depend on all of these concrete shapes. Okay, so let's create our duplicate method, which is going to accept a shape. So it has a shape parameter. Now in here, what we need to do is we need to duplicate any shape that's passed into the duplicate method. So first of all, we need to actually check what type of shape has been passed in. So we can say if shape is circle first of all, and let's see what's going on here. The type namespace circle could not be found. Let's see. I've misspelled circle here, so let me correct that. Okay, and that fixes the issue. So let's see. So first of all, let's cast this shape object into a circle. So we'll call this copied shape. So the shape that we are copying, and we'll cast it into a circle. And that's how we cast. And again, I spelled circle wrong. There we go. Okay, so now we will create our new shape, which is going to be the clone. So I'm just going to make a note. This is the copied shape. And then we will have our new shape, the duplicated shape. Okay, so we create a new circle, and this is the clone. And then what we can do is we can set the new shape's radius equal to the copied shape's radius. Okay, and then we can draw this shape onto the canvas by calling the draw method. And then we also need to check if the shape is a rectangle. And if it's a rectangle, again, we're going to create, we're going to cast the shape into a rectangle. Okay, so now we can treat this shape as a rectangle. So we also need to create our new shape, or our clone. This is going to be a new rectangle. And then we can set the new shape's width and height equal to the passed in shape's width and height. So we can say new shape dot width equals copied shape dot width, and we can say new shape dot height equals copied shape dot height, and then we can draw the new shape onto the canvas. Okay, so it'd also be a good idea to check at the end here. So if the shape is not a circle or a rectangle, then we could just throw an error. So let's do that. So we'll throw a new argument exception, and we'll say invalid shape provided. Okay, so we can't duplicate a shape that isn't a circle or rectangle in our current implementation. Okay, so here's how a client would use this solution. So let's go ahead and show you how this solution would be used. So we can create a circle, and I cannot spell circle today. So let's create a new circle, and let's draw that circle. So render it onto the canvas, and then let's simulate the user clicking the circle and dragging to resize. So this is like user clicks and drags to resize. So we can say circle dot radius equals 12. So we increase the radius, and let's say that a user adds a new rectangle to the GUI. So I'm just going to copy and paste this in for now to save a little bit of time. So we can see here we create a new rectangle, draw it onto the GUI. So this is like the user adding a new rectangle to the GUI, and then the user clicks and drags the rectangle to resize the width and height. So now let's take a look at how we could duplicate these shapes. So let's simulate the user right clicking and clicking and selecting duplicate. Okay, so we can simulate that. So shape actions equals new shape actions, and then we can call shape actions dot duplicate and pass the shape that we want to duplicate. So if we want to duplicate the circle, we can do that. If we want to duplicate the rectangle, we can do that. Okay, so let's run this program to see if everything is working correctly. And as you can see, we are drawing the circle and rectangle onto the GUI. So that's these two methods here, so circle.draw and rectangle.draw. And then we duplicate the circle, so we draw the circle again, and then we duplicate the rectangle, so we draw the rectangle again. So this is all working correctly. So hopefully by now you have spotted the main issue with this solution, and it should be pretty obvious that the issue is in this duplicate method. So here are some of the obvious issues that I can spot. So first of all, we are violating the solid open close principle, as we need to modify this shape actions class every time we add. So that means extending our code base a new shape. So whenever we add a new shape, we're going to have to modify our existing code, because we're going to have to add a new conditional block of code to check for this new shape and add the logic for duplicating that particular shape. And you can also see that shape actions is coupled to the concrete shape classes, and so far that's circle and rectangle. So you can see it's coupled because we're calling the new keyword here. And so shape actions has to know about or depend on all kinds of shapes and their specific fields and methods. So you can see here that this shape actions class has to know that circles have a radius field, and it has to know that rectangles have a width and height. So it has to know about the specific implementation details of each of these concrete shapes. And at the time of writing code, shape actions has to know about all of the shapes that we support. So what if we wanted to make this app extensible so that other developers or other people can build plugins for this application so that they can define other types of shapes that can be added to the GUI. And that can't be achieved with this current implementation because at the time of writing code or at compile time, this shape actions class has to know in advance about all of the types of shapes. So this is not a flexible solution, and it currently depends on concrete implementations of shapes. So let's now take a look at how we can solve the issues that we found previously. So the logic for duplicating a shape can be moved to each concrete shape class rather than having it all in the shape actions.duplicate method. So in other words, we can move all of this duplication logic for a circle and add it into the circle class. And we can do the same for rectangle, put it all into the rectangle class. Okay, so we can then decouple shape actions from all of the concrete shapes and have it talk to the shape interface, which is much more flexible and maintainable. So note how the shape actions class has been sort of lifted up to talk to the single shape interface rather than having it talk to many concrete classes. So you can see beforehand it depended on the many concrete classes because we had to check what the type of shape was before duplicating it, whereas now it's been lifted up to talk to the shape interface, and we've added the duplication logic for each shape into its own class. Okay, so let's have a look at the gang of 4 representation of the prototype pattern. So here you can see we have the prototype interface with the clone method, and then the concrete prototypes implement this clone method. So each concrete prototype knows how to clone itself, rather than having this clone logic inside of some sort of client or other class as we had previously. And this means that the client can use polymorphism and talk directly to the prototype interface rather than talking to the many concrete prototype classes. So let's now implement this solution in code. Okay, so now let's refactor our code to use the prototype pattern. So the first thing I'm going to do is I'm going to change, I'm just going to add an extra method to the shape interface so that all shapes can be duplicated. And you can see the duplicate method is going to return a shape. So next up, we need to solve a few errors that we're now getting. So you can see here that circle does not implement interface member shape.duplicate. So we need to implement this duplicate method. So we've already created the duplication logic beforehand in our shape actions class. So what we can actually do is we can copy this here. So we can say new circle and shape.radius equals copied shape.radius. So let's add that into circle. And you can see here that we don't need to reference this copied shape anymore. We can just use the radius field directly on circle. Okay, then finally we need to return this new shape. Like so. So here we create the new shape to clone, and then we just set the radius equal to the current circle's radius and return that new shape. Okay, so new circle. And let's actually rename this now to new circle. Okay. So next we need to do the same thing for rectangle. So let's implement this shape class. So we need to add the duplicate method, and then we can copy and paste the logic for copying a rectangle. So let's add that in, and we actually need to create a new rectangle. Okay, so we create a new rectangle, and then we set the width and height equal to the current rectangle's width and height. Okay, so let's again change the name of this to something a little bit more specific. So new rectangle, And then we need to return this new rectangle from the duplicate method to satisfy the method signature. Okay, so that's everything we need to do in the concrete shapes. So now we can go to our shape actions class, and we can see here this very bloated, ugly method can now be refactored into something much cleaner. Now all we have to do is return shape.duplicate. Okay, and we're actually going to return a shape this time from the duplicate method. So I'm just changing the kind of implementation details a little bit here. So rather than drawing the shape onto the screen, we're just going to return the shape and allow the client to decide what they do with that duplicated shape. Okay, so I'm just also going to log, just so it's clear, duplicating shape, just so it's clear what's going on when we run the program. Okay, so now let's go into our client and see what happens if we run this. As you can see, everything seems to be working correctly. Okay, so what I want to do here is, because now duplicate is returning the new duplicated shape, let's see if we can, let's see, new circle equals that. So now we can store this return shape in a variable. So let's say shape new rectangle equals that. And then we can decide in the client whether we want to draw it on the screen or do whatever we want with this new cloned or duplicated shape. So let's actually draw it. So this is basically now doing exactly what we had beforehand. We duplicate and draw the shape on the screen, but we're now controlling whether we draw it or not in the client. So it's just a slightly different implementation detail that gives the client a little bit more control over what they do with this duplicated shape. So let's run this now. And I think what I'm going to do is actually duplicate, create the new circle, then draw it, just so it's a little bit more clear. Okay, so we can see here, we first of all draw a circle, just the same as before. We then draw a rectangle. We then duplicate the circle. We then draw this new duplicated circle on the screen. Then we duplicate the rectangle and draw the rectangle on the screen. Okay, so this is all working perfectly. And we can now also add new shapes without having to modify existing code in the shape actions class. So the great thing about this prototype pattern is we are now satisfying the open close principle, because we can create a new shape such as a triangle and we don't have to modify any existing code. The Singleton pattern is a creational design pattern that ensures that a class only has one instance and provides a global point of access to that instance. The single instance is commonly used for managing shared resources, configuration settings, or logging functionality within an application. A common use case of the Singleton pattern is to use a single global instance of a database object throughout an application. This means that all clients that need to connect to a database will retrieve the same database object and will not be creating new separate database objects. The database object is only created once, the first time it is needed, and then all other clients that need to connect and query the database will use this same database object. So here's a user making a request to fetch some products. There are two classes, user authentication and products. Both require fetching things from the same database. Notice that we are not using the new keyword to get the database object. We are using a method called getInstance that returns the exact same database object throughout the application, ensuring that we always use a single database instance. So you can see here we have our user, which goes through two classes. So first of all, we authenticate the user, and to get the database object, we are calling db.getInstance. We are not calling db equals new database, whatever. Okay, so we're not using the new keyword. We're using this sort of factory to get the same instance of the database object. So it's going to be cached somewhere in memory. So you may be wondering why we can't just create a new database object every time we need to connect to a database. So here are some good reasons to use a single global database object in all clients. So you can see here we have two clients. The Authenticate user class is a client of the database object, and this products class is also a client. Okay, so here are some good reasons to use a single global database object. So first of all, for resource efficiency. So database connections and resources are typically limited and can be expensive to establish. So by using a single instance of a database object, you minimize the overhead of creating and managing multiple connections, optimizing resource utilization. Also, consistency and state management. So having a single database instance ensures consistent state management and transaction handling across different parts of the application. Changes made to the database state are visible universally within the application, avoiding inconsistencies that could arise from multiple database instances. So we also simplify configuration and management. So with a Singleton database instance, configuration settings such as connection parameters, credentials, and initialization logic are centralized and managed in one place. And this simplifies application setup and maintenance. We also have performance optimization. By reusing a single database instance, you can optimize database query performance and reduce latency associated with establishing new connections or reinitializing database resources. So the Singleton pattern is great for storing app configuration settings. It's also great, I should say, for storing app configuration settings, logging configuration, session information, authentication tokens, and making this information available globally via a single instance, ensuring that it is the same throughout the app. So you can see there are many reasons why we would want to keep a single instance of an object throughout the application, rather than creating new versions of that object in multiple clients. And we can see here some more specific reasons why we would want a single database instance. So say that we need to keep an app settings object that stores global variables such as the name of the application, the database configuration, for example, what database type we're using, whether it's Postgres, SQL, MongoDB, the username and the password. And also logger settings such as the file location for our log file, the format, whether it's text versus JSON, etc. And we need to create only a single instance of this object throughout our application to ensure that it only needs to be configured once in one place and to ensure consistency throughout the application. So first of all, we're going to create a poor solution to this problem. So first of all, let's create a new folder for our Singleton pattern example, and that is a creational design pattern. So let's create it in there, and this is called Singleton. Okay, so first of all, let's create our app settings object, or class, I should say. So app settings, and in here we're going to create a dictionary field, and each dictionary the dictionary is going to have keys which are strings, and the values are going to be objects. Okay, and this is where we're going to store our settings. Okay, and each setting is going to have some key such as app name and then some object, and the app name could be design patterns mastery, for example. Okay, so first of all we need to create a method called get for getting values from our settings object. So here we first need to check if the setting with this key name actually exists in our settings dictionary. So here we can say if the settings and contains key. So if the settings does not contain the key provided, then we're just going to return null. Otherwise, we can return the settings object corresponding to the provided key. Okay, so next up we can create a sept method. and this is for setting settings values. So we provide a key and an object value, and here we can simply call settings key equals value. Okay, so we set a settings value with this key and this value. So next up, let's have a look at how we can use this solution in a client. So what we can do is first of all create a settings object. So we'll create new app settings equals new app settings. And then let's actually set a few settings. So we can call settings.set, and then we'll say app name is design patterns mastery, and let's also set another setting for app creator. And I'm just going to put my name, so Danny. Okay, so then let's actually console log one of the settings just to check that it's working correctly. So we can say settings.get, and let's get the app name. Okay, so this should be design patterns mastery. So let's run this. And we can see that it's been set correctly, and we are retrieving it from the settings object without any problems. So next up, let's actually test getting a setting from a different client. So this is here a client, a class that is using this app settings object. So let's now create a test class. And in here, I'm just going to create a method called run, so run the test. And let's see, so first of all, we need to get our settings object. So let's get our settings object here. And then what I want to do is retrieve this app name. Okay, so as you can see in program.cs, we are setting the app name, and then we get the app name here. And then in a different class, in a different client, a client has some class that's using this app settings object or class, and we are trying to get the app name which was set in program.cs. So now let's actually run this test. So maybe if we make this static, we can just access it directly just for convenience. And let's run this program. And we can see we get null. So null is returned here because in test, the app name does not exist. Okay. So you can see here that we need to use the Singleton pattern to ensure a single instance of app settings is maintained throughout our application, because here we can see we are creating a completely new app settings object. And this is kind of fine if this is the first time we're doing it, but then we're also creating another app settings object, a separate, different settings object, and then we're trying to access app name on a different object to what we created in here. So we're going to need to use the Singleton pattern to solve this issue, because every time we need to use the app settings object, currently we are using the new keyword, and so creating a new object. So the solution is to use the Singleton pattern. So to ensure that we have only a single instance of this app settings class, we first have to make the constructor private. So notice in this UML diagram that the constructor, so this app settings constructor, has a negative symbol in front of it, meaning that it's private. And this means that we won't be able to use the new operation or the new keyword with this app settings class. And also notice that we have a private static. So static is being symbolized by this underline here in the UML. So notice that we have a private static instance field that holds an instance of the app settings class. In other words, this class is responsible for maintaining a single instance of itself. And we also have a getInstance method, and this again is a static method for getting that single instance. And the reason that this method is static is because that static fields So this static field here, for example, and static fields are only visible to static methods. So if this wasn't static, it wouldn't be able to access this instance field because static fields belong to the class itself rather than the objects that are instantiated from it. So let's have a look at the gang of 4 representation here. We see it's very similar to what we have up here. We have a class called Singleton with an instance, a static private instance of itself. We have a private constructor so that the new keyword cannot be used outside of the class itself. And then we have a getInstance method, which basically returns the instance of itself. So to implement the Singleton pattern, you have to do a few things. So first of all, we need to make the constructor private so that the new keyword can't be used to create multiple instances of this class. Okay, so we can only create an instance of the class inside of the class itself. So another point is that we have to create a private static instance field to keep reference to the single instance that is created inside of the class. And we have to create a public static getInstance method for creating that single instance the first time the method is called in the application, then returning that very same instance every time the method is called. So let's now implement this solution in code. So let's now refactor our AppSettings class to adhere to the Singleton pattern. So first of all, we need to create a private static field for holding a reference to the instance. So let's create that. So private static AppSettings. So this is going to be an instance of itself. We're going to call this instance and we're going to leave it as null initially. So next up, we need to make the constructor private. This is a very important step in the Singleton pattern to ensure that instances of AppSettings cannot be created outside of the class itself. So this means that the class itself will be able to create and maintain a single instance of itself throughout the application globally. So let's make the constructor private. So private constructor, and it's just an empty body. So next up, we need to create a method for creating a single instance of this class. We're going to call this method getInstance. So this is going to be a static method called AppSettings, and we're going to call it getInstance. And what we're going to do here is we need to check if the instance is null. And if the instance is null, so the first time that this method is called, the instance is going to be null. So we need to create a new instance. Okay? Otherwise, we just return the instance. So the second time that this getInstance method is called, instance will be set to an AppSettings object, and therefore this will not run, and we will just return that very same instance as we returned previously. Okay, so I believe everything else should be the same as before. So we have our get method for getting certain settings via their key, and we have our set method for setting different settings. So I believe that's everything that we need to do. So now what we can do is we can go into our program.cs file, and I'm just going to change the namespace to this new solution. And let's see, what is the error we get here? So AppSettings is inaccessible. Okay, so now we can see that because we were previously using the new keyword to create an AppSettings object, it's now giving us an error because AppSettings.AppSettings, so this is the constructor, is inaccessible due to its protection level. So if we look in AppSettings, the constructor is now not accessible outside of the class, so we're going to get an error. So now to create the settings object, we need to call AppSettings.getInstance, and this now returns an instance of the settings object. And we can use the settings object just as we did before, so we set some values here, and then we log the app name at the bottom. So let's test that this works correctly as it did before. And we can see that we get Design Patterns Mastery just as we should. Okay, so that's perfect. So now let's actually test out getting this instance in a different client somewhere else in our application. So if we go into our new example folder and create a test class, and in here I'm going to create a public static method called run. And what we're going to do is we're going to again get our settings instance, and I'm going to try to retrieve the app name. So let's actually see if this works. So now if we run test.run, we should get Design Patterns Mastery, because here we get the instance from settings, from our app settings, and this creates a new instance and caches or stores this instance in the instance variable on the class. So you can see that this is a static field, meaning that it's stored on the class itself and not within new objects created elsewhere in the program. So let's see if this works. And as you can see, we get Design Patterns Mastery logged twice. So this is perfect. We now have a global instance object for our settings. The factory method pattern is a creational design pattern that defines an interface for creating objects, but allows subclasses to alter the type of objects that will be created, providing a way to delegate the instantiation logic to subclasses, enabling flexibility in object creation without changing the client code. So say that we are developing a new Model View Controller backend framework, or MVC framework, to rival the popular PHP framework Laravel. So let's code out a basic solution. So I've created a view engine interface with a render method, and this takes a file name. So this is going to be the file location of our template, and we can pass that template some data. And then this view engine is going to render this template. It's going to pass it the data and turn it into a regular string of HTML and return that HTML so that it can be understood by a browser. And we also have a couple of template engines. So here we have a Blade view engine, which implements the view engine interface with a render method. And here we're just returning view rendered from file name by Blade. And then we have a Twig view engine. So this is just a different templating engine. And then we're just saying view rendered from file name by Twig. And this is all within our MVC framework folder. So this is part of our framework that we are developing. And these view engines will actually be third-party code to our framework, because we are going to be sort of downloading these view engines, installing them into our application as packages. So we would not have access to the source code to these view engines. Okay, so now let's create a base controller class to handle requests made to our application. So let's create a controller. And in here we're going to have a method called render. And this is going to take a file name for the template that we want to render. And we're also going to have some data that we can pass to it. Okay, so first of all, let's create a view engine object that we want to use. And we're going to use the Blade view engine. And then let's actually use the view engine to convert our template and pass it the data, and then convert it into some regular HTML. So we can say var HTML equals viewEngine.render, and then we can pass the file name and the data. And finally, what we're just going to do is we're just going to log to the console this HTML. Okay, so this is our base controller class. So remember, this is all part of our MVC framework that developers can use to create their own back-end applications or APIs. So developers can extend this base controller class to create their own controllers to handle requests to their application. For example, a controller that deals with order-related requests. So let's come out of this MVC framework folder and create a new class called Orders Controller. And this is going to extend our base controller from our MVC framework. Okay, so remember, this would be some developer creating this, some other developer not related to our MVC framework. They're creating their own, maybe e-commerce application, and they're using our MVC backend framework. So in here, what we can do is we can create a method called list orders. And what I'm now going to do is I'm just going to copy and paste some code in here to save some time. Okay, so this is basically simulating fetching some orders from a database. So we can see here we have a dictionary and we have the name of the item and the price. Okay, so this is just to simulate fetching some sort of order data from a database. And then below this, we can call the render method, which we have inherited from controller, and we can then pass the location of our template file, so the template that we want to render. So this will be our blade template in this case, because in controller we are using the blade view engine. So this will be a blade view. So maybe we can call this, for example, orders.blade.php, and then we can pass the data that we want to populate our template file with, and that's going to be this orders data. Okay, so I think that is everything that we need to do for now. I've also created a method called getOrder to get a single order by ID inside of here. So I'm just going to paste that in for now, just to save again a little bit of time. You can see here this is just another controller method that we can use to get a single order, okay, by ID. And here I'm just simulating getting an order by ID. We're not actually getting it by ID because we don't have a database set up, but it's just to show you a different method that we could add to our controller. So our backend framework code, where our base controller class is stored, we can see here, will be downloaded by developers as a third-party framework. So other developers will be downloading this MVC framework folder essentially as a package so that they can use our framework to create their own applications. And this orders controller is an example of what a developer might create using our framework, where they extend our base controller class. Now, so developers won't actually be able to modify the code directly in this MVC framework folder. So this means that if the developer wants to use a different view engine or template engine, then this solution is poor, because our controller class is tightly coupled to this blade view engine, and it cannot be changed by developers. The developer has no way of switching to a different view engine. So for example, if they want to use the Twig view engine to create their templates using the Twig templating language, then we have provided them with no way of switching to a different view engine. So let's try a different approach. What if we allowed developers to pass a view engine as an argument to the controller.render method? So currently we have the file name and the data that we want to pass to the view, but let's also allow the developer to pass the view engine that they want to use whenever they render a view. So let's pass the view engine that we want, the the developer wants to use. And now we can actually remove this view engine. We don't need to create the view engine because it's been passed here. And then, just as before, we can call viewEngine.render, and then we can log it the resultant HTML to the console. So this allows developers to select a view engine every time they call this base controller.render. So if we come into our orders controller, we can see that we now get an error because we are not passing the view engine that we want to use. So the developer now needs to pass the view engine that they want to use. And if they want to use the Twig view engine, for example, they can pass the Twig view engine. So here we can pass again the Twig view engine. So this is a more flexible solution because it allows the developer to choose whatever view engine that they want to use. However, the problem is that we have to now pass, or the developer has to now pass the view engine every time they call the render method. And usually developers will be using one view engine for all of the templates in their application. So it doesn't make much sense to make the developer to have to keep passing a view engine every time the render method is called. So the solution is to create a template method, and we can add a create view engine template method inside of our base controller class. And by default, we can return the blade view engine. But if the developer wants to switch to a different view engine, such as Twig, then they can use our alternative controller class, Twig controller, that overrides the create view engine template method. So here is the UML. And you can see here we have our base controller class, which is part of our MVC framework package. And we have our render method just as before. And we also have our create view engine method, which by default returns a new blade view engine. So if the user doesn't specify any different view engine, then they will get the blade view engine. And also within our MVC framework package, so this is part of our package, our backend framework code, we're going to create a Twig controller which extends the base controller and overrides the create view engine method, and instead it returns the new Twig view engine instead of a blade view engine. So if the developer wants to use the Twig template engine, then they can extend the Twig controller instead of the regular base controller. So create view engine is our template method. Let's show this in code. So let's now refactor our code to follow the template method pattern. So let's actually remove this view engine parameter from the controller's render method. And we're actually now going to use a template method to create our view engine. So this is going to be a protected virtual method that returns a view engine, and it's going to be called create view engine. And by default, the default implementation is that we return a new blade view engine. So now up here we can create our view engine by calling this create view engine method. Okay, so by default the view engine for our framework will be blade. Okay, so now we can actually create our alternative controller that the developer can use. So we're going to create a Twig controller. So this is going to extend our base controller class, and we're going to override the create view engine template method. So we're going to say protected override view engine. So it's going to return a view engine, and it's called create view engine. Okay, so what we're going to do here now is return the Twig view engine. Oops. Okay. So now if the developer wants to switch to the Twig view engine, they can extend our Twig controller class rather than the base controller class. So if we go into our orders controller, we can see here we are getting an error because we no longer have three parameters in this render method. So we can remove this last argument because we no longer need to specify the controller type in the render method. And if we want to use the Twig template language now, we can just extend the Twig controller and our render method will use the Twig template language because this create view engine is a template, meaning it can be overridden and it will affect the behavior of the render method because we are calling it in here, and this can return different types of view engines depending on whether it is being overridden or not. So essentially, as we've said, this create view engine is acting as our factory method as it returns a new object. Okay, and it can be a different type of object depending on if we override it or not. So essentially what we've done is we've deferred the creation of an object, the view engine, to a subclass. And in this case, the subclass is Twig controller because it's a subclass of the base controller class. And another option would be to make this create view engine method an abstract method and force subclasses to implement it. So in this case, we have made it just a regular method and we've provided the virtual keyword, meaning that it can be overridden. But we could also make it an abstract method with no default implementation, so no body essentially, and force subclasses to implement it. So in that case, we'd need to create a blade controller that implements this create view engine method and returns a blade view engine so that it would force the developer to select either blade view engine controller or the Twig view engine controller. Here is the gang of 4 representation for the factory method pattern. So we have some creator class which has an operation method that calls the factory method, and you can see that a factory method returns some object. And then we have our concrete creator classes which can override the factory method from the creator class. And you can see here each factory method can return a different type of object. And you can see here the factory method is called inside of the operation. So essentially we can change the behavior in the creator class by overriding this factory method. So the objects returned from factory methods are referred to as products in the Gang of 4 book. And the factory method pattern is often misunderstood. It relies on inheritance and polymorphism to add flexibility to the design. Inheritance allows methods to be overridden in subclasses, and polymorphism allows different objects to be returned from the overridden methods. And many people implement the factory method pattern incorrectly, for example using a static method such as this. So var engine equals view engine factory dot create view engine. But static methods cannot be overridden, so there's actually no flexibility when using a static method, it isn't correct. Because we cannot change the implementation of the create view engine method. So using the factory method pattern, we can defer the creation of an object to its subclass or subclasses, and this is possible through inheritance. The abstract factory pattern is a creational design pattern that provides an interface for creating families of related objects without specifying their concrete classes, promoting encapsulation and allowing for the creation of object families that can vary independently. So say that you have an application for Windows and Mac. The UI components such as buttons, checkboxes and text boxes are different for each operating system, but each type of UI component will have the same behaviors. For example, a checkbox will have an onSelect method no matter whether it's on Windows or Mac. So our application needs a way of knowing what the current operating system is and then selecting the appropriate family of UI components for that operating system. So first, let's implement a more obvious solution in code. Okay, so inside of an Abstract Factory folder for this example, I've created an enum for the different types of operating systems that our application is going to support. So far we have Windows and Mac. I've also created a UI component interface for the different UI components to implement. So all UI components, whether they're going to be Windows or Mac, need to implement this UI component interface, and it has a single method for rendering a UI component into the UI or the GUI. So next up, I've created a checkbox interface, and this extends the UI component interface. So all checkboxes are UI components, and I've not actually created any checkbox methods just for simplicity, but we could have, for example, onSelect method and any other checkbox related methods. I've also created an iButton interface, which also extends the UI component interface. Okay, so now for the concrete Windows components. So I've also created a UI Windows folder for all of the actual concrete Windows UI components. And here we have a Windows button, which implements the iButton interface and also implements the render method. And we also have a Windows checkbox, which again implements the checkbox interface and also implements this render method. We also have the Mac components, the Mac UI components, and we have a Mac button, which implements the iButton interface, the render method, which is just logging Mac render button, and we have a Mac checkbox, which again implements the iCheckbox interface. Okay, so this is the way we are set up here. So now for the app that we are actually building. So these, all of these classes so far would be probably installed as some sort of package. So next up, let's actually create our sort of application class. And that's going to be called a user settings form. So let's create a new class. And let's say we have some sort of form which will have a checkbox and a button. So what we can do is we can create a render method which will accept the operating system type. So whether we should render for Mac or Windows, and then we can check what the operating system type is. So if we can say if OS is equal to operating system type dot Windows, then we can create a new Windows button and render it to the screen. So we call the render method, and we can also create a new Windows checkbox. Okay, then we need another conditional statement to check if the operating system is Mac. And then we can render a Mac button and a Mac checkbox. Okay, so hopefully you can already start to see what solid principle we are going to be violating using this solution. But let's first of all, before we discuss that, let's go ahead and actually use this solution as a client would. So if we go into program.cs, first of all, let's specify the operating system that our app is running on. So this would probably be some sort of environment variable or some sort of system variable, some sort of thing that we could obtain from the system that the application is running on. But for now, we're just going to say var OS is equal to operating system type, and then we're just going to say Mac. So we're running on Mac. Okay, so then let's render our user settings form. So we can say new user settings form, and let's then render this form. So we can say user settings form dot render, and we can pass the operating system type, which in our case is Mac. And then let's run this program. And as you can see, we are rendering for Mac, and the button and the checkbox for Mac. If we change to Windows, we should render for Windows. Problems with this solution can be seen in this user settings form class. So for every UI that we develop, we're going to have conditionals to check what the current operating system is and render the correct concrete UI components for that particular UI. And this is a maintenance nightmare, as every time we add or remove a type of operating system, we have to modify a load of classes, which is going to violate the open-closed principle. And another issue is that we have to conditionally render concrete UI components. So you can see here we're having to render these concrete UI components. And it is, in this case, it's easy to make mistakes, such as accidentally rendering a Windows checkbox on the Mac operating system, because we're going to have lots of different UI components. This is just different UI, so different pages or different forms, maybe like a home page, an about page, a different window for giving some information after a user has clicked a button. Lots of different UI elements which are going to be built from these base UI components, and we can see that as the application grows, it's going to become easier to accidentally render the wrong type of UI component for a certain particular operating system. And our program isn't going to know if we've actually done that by accident. It's only going to result in an error when the application runs on that particular operating system. So the solution to the issues that we faced previously are to create an abstract factory class to create families of UI components, such as the family of Windows UI components or the family of Mac UI components. So here you can see we have an interface called UI component factory, which has a create button method and a create checkbox method. And we then have our concrete component factory. So here is the Mac UI component factory. And this create button method will return a Mac button, and the create checkbox method will return a Mac checkbox. And we also have a Windows UI component factory, which will do the same but for Windows components. So essentially we're going to be able to create families of UI components from these component factories. So here is the gang of 4 representation of the abstract factory pattern. And you can see here we have our abstract factory interface with create, with methods to create different products. And then we have our concrete factories, which actually implement these methods. So rather than discuss the advantages of using this method here, I think it's going to be better to implement this in code and then discuss as we code. So continuing on from our previous code, we can create the abstract factory interface. So I'm going to create this in the abstract factory folder, and this is going to be called UI component factory. And here we just need to create 2 methods, one for creating a button and another for creating a checkbox. Okay, so now we can create our concrete factories. So first of all, let's create our Mac UI component factory. and this needs to implement the IUI component factory. So UI component factory, and then we need to implement this interface. So here we very simply just have to return a Mac button. Okay, so let's import this correctly. So there we go. And then here we just need to return a Mac checkbox. Okay. So that's everything we need to do there. So let's now create our Windows UI component factory for creating families of Windows UI components. And again, we need to implement the UI component factory interface. And very simply, we just have to return a Windows button here. And that should be Windows button. And then let's import, use the correct namespace. And here we just have to return a Windows checkbox. Okay. So now in our form class, so let's go to our user settings form. We can see here that beforehand currently we're having to check the operating system type before rendering the operating system specific UI components. So now what we can do is we can actually use polymorphism so that this client requires no knowledge of the specific of the operating system. Basically, it can just call it can just use the UI component factory to create a button or checkbox and then render it to the screen. And it can do that because we're going to pass the UI component factory into this render method. So now rather than having to perform all of these checks, we can simply use polymorphism. So we can call UI component factory.create button, and we can render that to the screen. And then we can do the same thing for the create checkbox. Okay, so here you can see that we're using polymorphism by talking to a factory interface to create related UI components. And this client requires no knowledge of the specific operating system. Okay, so this is much cleaner. We no longer need to perform all of these checks in every single UI that we create, such as this user settings form. So let's now have a look at how this solution would be used. So if we go into our program.cs file, we now need to do a few extra things here. So first of all, let's create the UI component factory. And we're not going to assign this any objects initially, because what we now need to do is we have to perform our operating system checks inside of the program.cs file. So we can say if operating system equals operating system type dot Windows, then we can assign the UI component factory equal to a new Windows UI component factory. And then we can do another check here for Mac. Then we can assign it to a new Mac UI component factory. And if the operating system doesn't match any of the supported operating systems for our application, then we can throw an exception. And here we'll just say unsupported operating system. Okay. So now here I'm just going to do this on one line actually. So rather than calling render on a separate line, I'm just going to create the user settings form and then call render directly on this line. And then we can pass into this render method the UI component factory. Okay, so that should be everything that we need. So let's run this program. Okay, so you can see here that it's rendering our user settings form correctly. And if we switch to Mac, then we should render for Mac. Okay, perfect. So this is all working correctly, just as it was beforehand. But here, you might be wondering, what is the advantage of using this abstract factory pattern compared to what we did previously? Because we're still having to have all of these conditional statements to check the operating system type. We're just doing it now in a different place rather than within our settings form class. And the advantage of this is that these checks now only need to be done just once upon app initialization. Then throughout the application, the UI component factory can be used to ensure that the correct family of UI components are used for the current operating system all throughout the application. So here, once we've assigned the correct UI component factory, it can be used all throughout our application, and we no longer need to check what the operating system is in every single sort of UI class that we create. So if we create a different class, such as, I don't know, maybe orders page, for example, which lists all of the orders that a user has made from some e-commerce store, then we wouldn't have to do all of these checks inside of that class and every other class that we create. We can just pass the correct UI component factory that has been initialized here just once. So that is the advantage of using the abstract factory pattern. The builder pattern is a design pattern used to construct complex objects step by step, providing clarity and flexibility in the creation process. So let's say that we have a class called car, and we use this to create car objects. And we also have a manual class that is used to create car manuals for certain cars. So you can see here that a manual has a set of fields, and a car also has the same set of fields here. So you can see that a car or a manual is composed of these fields. And we can see we have the car type, and if I just go into this components folder where I've stored all of these kind of components to make up a car or manual, we can see that car type can either be sports, SUV or saloon. The dashboard can be configured to either have a rev counter or not. We have an engine class here, which we could provide methods and fields for the speed, model, etc. A GPS navigator class, and also a class to represent wheels. And I've just put the diameter of the wheels in inches as a sort of example field. So we can see here in car and manual, they share a lot of common fields. And currently we have 7 fields that are shared between car and manual. And also in car we have a field here which is specific to this class, so it's not relevant in the manual class. And this field is called fuel, and this sort of represents the amount of fuel that is in the car. And then in manual we also have a print method, which is used to print the text or create the manual from the fields or information that has been set on the object. So let's take a look at how a client would use this solution to create cars and their corresponding manuals. So first of all, let's try to create a sports car. So we can say sports car equals new car, and this needs to come from the builder pattern. And now we have to provide the sort of configuration options for a sports car. So first of all, we need to provide the type of the car, and we can use the car type enum for this. So we can say car type dot sports, and then we need to provide the number of seats. So a sports car will have 2 seats. We then need to provide is convertible. So we're going to say false. This is not a convertible sports car. We need to provide an engine, and that's everything we need there. We need to provide a dashboard, and we can provide whether this has a rev counter or not. So what I'm going to do is I'm going to type out the name of the field just so it's nice and clear, and put true. Okay, so then we need a wheels object, And then we need to provide the diameter of the wheels in inches. So let's say 20 inches. And then we need a new GPS navigator. So let's provide GPS navigator. And finally, I think actually that is everything that we need to provide. Okay. So that is our sports car. And then we can also specify the amount of fuel in the sports car. So let's just say it's full, 100% filled. Okay, so then we could also create an SUV. So rather than type out all of those configuration options again, let me just copy and paste an SUV. So we have the car type SUV. So I believe this is the number of seats. So I guess it would make sense here to again provide the name of the field, and then is convertible. So we could do that. Okay, so you can see that there are a lot of configuration options that we have to provide every time we create a sports car, or a car I should say. And also I just noticed that we don't need this or this. Okay, so let's also now create a sports car manual. And again, we have to provide some configuration options, lots of configuration options, and then I'm just logging out the sports car manual print. So we print the sports car manual and log it to the console. And we can also do the same for SUV. And you can see that when we create a manual and when we create a sports car, so a sports car and a sports car manual, we're actually providing the same fields to create these things, but they are two separate objects that are not really related. Okay, they don't share a common interface because a car is different from a manual. So let's run this to see what we get. And you can see we have the two different manuals. So we have a manual for sports car here, and we have our manual for our SUV. So as you can see here, there is a large number of configuration variables that we have to pass to the constructor of car or manual when creating them. So as you saw with the example, there are a large number of configuration variables that we have to pass to the constructor every time that we create a car or car manual object. And this is pretty ugly. And also, a large number of the configuration options are not needed most of the time. For example, most cars are not convertibles, and therefore we have to just keep on providing false for all of our cars or car manuals for many of the fields. So one way of not having to specify all of the configuration options when creating a new object would be to create subclasses for each type of car or manual. So here we can see we have our original base car class, and we have some subclasses to create specific types of cars. And we also have the same thing for the manuals here to create the manuals for these cars. So the problem with this solution is that our library of subclasses is likely to grow very large as more configuration variables are added to car. And also, if we, for example, change the wheel size on a sports car, then we'd also have to change the sports car manual class to correspond to this changed wheel diameter. So the above solutions here are ugly and difficult to maintain. So let's now introduce the builder pattern to solve these issues. So here is the UML solution for the builder pattern. So we can see here we have a builder interface with a few methods. So we have here set car type, set seats, and we'll also have the rest of the methods such as set engine, set dashboard, etc. So these methods kind of represent the steps involved in building either a car or a manual. And then we have these sort of concrete builder classes. So we have one for building a car and one for building a manual. And you can see here in this car builder that we store a reference or a field of a car object. And then we use these methods, so such as set car type, we'll set the car type on this car object, and then we have set seats. And we'll also implement all the other methods that we need from this builder interface. And then finally, at the end, we have a getCar method, which will just return this built-up car. And then we have the same thing for manuals, where we have a manual field. So in this manual builder, we're going to be building up a manual using these methods that we have implemented from this builder interface. And then again, finally, we have a sort of getter method where we can return this built up manual object. So a car and its manual are two different objects that don't share a common interface. However, they can be constructed using the same steps, as each specific component in a car needs to be documented by its manual. So by abstracting the object creation logic into builder classes, we can create cars and manuals by only specifying the steps required to build that specific car or manual. So let's take a look at how we can implement this in code. So let's now solve this problem using the builder pattern. So first of all, let's create or recreate our car class. So you can see beforehand that the way we were creating cars is that we pass all of these values into the constructor. Now what I'm going to do is I'm just going to provide, I'm going to change these from fields to C# properties just for convenience. And you don't have to do this. We could still have car exactly the same as we had it beforehand. As we had it in here, we could pass all of the fields into the constructor. However, I'm now just going to build up a car by setting the properties with getters and setters. So let's now import these components. And then let's create our manual in the same way. So we're going to move away from passing the values into the constructor, and we're just going to use properties to set the fields within the builder classes that we are going to create. So let's create a manual class. And I'm just going to copy and paste this in because it's pretty much what we had before, but we're now using C# properties rather than setting the values in the constructor as we did before. So we just need to import these components. So we're going to use this namespace. Okay, so now we can build our builder interface that will contain all of the possible steps for building a car or a manual. So let's call this iBuilder. And in here we're going to have some methods. So first of all, I'm going to provide a reset method, and this is going to essentially, in our concrete builders, it's going to reset the kind of object field. So for example, if we have a car builder, the car builder has a field of car, and it builds up that car with the methods that we provide in here. And the reset method is basically just going to kind of reset that car object to a brand new object. So this is just a common method that is often included in the builder pattern, and it'll become more clear when we actually use this method. So next up, I am going to create a set car type method, and this is going to return an iBuilder. And the reason we're actually returning a builder from this set car type is because it will allow us to chain methods onto each other when we are creating a car. So again, hang on, this will become much more clear if you don't understand when we actually use this solution. So I'm just going to copy and paste in the other methods now to save some time, because it's pretty obvious what we are doing. So we're just adding in the other methods. So as you can see, we have all the steps that we need here to build a car or manual. So we can set the engine, we can set the wheels, we can set the dashboard and pass a dashboard in, etc. So now let's build the concrete builders. So first of all, let's create the car builder. And this is going to implement the iBuilder or the builder interface. So let's implement that interface. So let's see, so the car builder, if you remember, needs to store a field of a car, of type car. So let's go ahead and do that. And then in the constructor, we can call the reset method. Okay, so essentially, whenever we create a new car builder object, we are going to set this car equal to a new blank car object, a fresh car object. So to do that, we can first of all create a constructor, and we don't need to pass anything to this constructor. We just want to call the reset method. And inside of the reset method, I'm actually going to move this up so it's a little bit more clear. We're just going to set the car field equal to a new car. Okay, so next up, let's implement some of these methods. So first of all, let's implement the set car type method. So where is that? Okay, so in here we pass the car type that we want to set the car to, and so the way we can do this is we can just call car.type equals type. Okay, and then remember we need to return an iBuilder at the end of this method, so we can just return this builder because this is a car builder, which is a builder because we're implementing the builder interface. And again, this will become clear why we're doing this shortly. So what I'm going to do is I'm just going to copy and paste the rest of these methods in because it's again very obvious and a little bit laborious. So let me just copy and paste those in. So I'm just going to copy and paste the whole class in actually. Okay, so that should be everything we need. So let's just go through what we've done here. So again, we have a car object, which we are setting to a blank object upon the builder's construction. We then have our methods, which are the steps involved in building a car. So here we can set the car type, we can set the dashboard, and we pass the dashboard in. We can set an engine, the GPS navigator, the seats is convertible, set wheels. And then finally we have our getCar method, which will return the car at the end. And we can see here that we store the car in a variable and then we call reset so that we are essentially resetting our car as a new car object once we get the car. And this isn't necessary in the builder pattern, but it's just something that's commonly done. So it's kind of like an optional step whether you reset the object when you get the object or whether you just leave it as it is. Okay, and then maybe call reset from the client. So that's just an implementation option, I guess. So next up, let's build the car manual builder class. And we need to implement the builder interface. Okay, so what I'm going to do again is I'm just going to copy and paste these methods in to save us some time. So it's going to be exactly the same as what we have in our car builder because it's implementing the builder interface. The only difference is that we are storing reference to a manual rather than a car. That's the only difference that we have here. And we just need to import or use this namespace for the components folder. Okay, so that's everything that we need to do here, and as you can see it's exactly the same as what we have before. So if I just go through one method, we have the set car type method here where we pass the car type and then we call manual.type, which is a property on this manual object. We set the type and return this car manual builder so that we can chain the methods onto each other whenever we are building a car manual. And again, that will become clear when we use these classes. And finally, we have our getManual method, which stores the manual in a new variable, calls reset to reset the manual field to a new manual, so a new blank manual, and then we return the manual. Okay, so that's everything that we need to do here. So let's take a look now how we would use this class in the client. So I'm actually just going to, let's comment this out, and let's go down here, and first let's create a car builder. Okay, so then we need to import this. Okay, so next up, let's actually build a car using the car builder. So we can say car builder dot set car type, and then we can set the car type to car type dot sports. So we're going to build a sports car again, exactly the same as we did beforehand. We can then set the number of seats. Let's see, set seats. Do we not have a set seats method here? Maybe we're missing a method. Okay, so it looks like we didn't actually include our set seats method in here, so let's add that in. And we're going to set it to, okay, so we pass in an integer for the number of seats, and then we actually need to add this method into our car and car manual builders. So let's just come down here and we'll say public iBuilder set seats, and then we'll say int seats, and we'll set the seats and return the builder. Okay, so let's see, what have we done wrong here? Car builder already defined set seats with the same okay, so we've actually provided this method already. Okay, so we didn't have it in the builder interface, but we did have it in the builder itself, the concrete builders. Okay, so we just needed to add it here. Okay, so let's go back into our client, and we can now set seats, hopefully. There we go. So this is going to have 2 seats, and we can set the engine to a new engine, and let's see, set dashboard to a new dashboard. Let's see, what do we need to provide here? Has rev counter, we'll say true. And let's see, so we've got a dashboard, set the wheels, and it will have 4 wheels. Actually, we need to provide the wheels components, and then we set the diameter in inches to 20, and that, I believe, is everything we need to do to create a sports car. So now we should be able to get the sports car. So we can say car builder dot get car, and let's see, we then should be able to set the fuel on the car. Sports car dot set maybe it's fuel, and we'll say 100. Okay, so let's run that to make sure that we've got no issues here. And I believe that's all okay. So let's now create our manual builder for a sports car. So here you can see we're using the car manual builder, and then we are calling all of the same methods as we did previously, and then we get the sports car manual by calling manual builder.getManual, and then we are logging the printed manual to the screen. So let's see if that logs correctly. Okay, so that all looks good. So this is a nicer solution, as we now only need to specify the car or manual properties that we need. For example, we don't need to specify if the car is convertible like we did beforehand when we had to provide all of the data in the constructor of a car or a manual when we were creating those objects. And also notice how we can conveniently chain methods onto each other, because we are actually returning the current object from each method call. So if we check set seats, you can see in this interface we have to return the builder, which means that we can keep on chaining these methods onto each other. And we could also return void from each of these methods and then call each method line by line. So for example, carBuilder.setCarType, and then we'd say carBuilder.setSeats. But it's just nice and convenient to be able to chain these methods onto each other. So the problem with this solution here is that we still have to specify a large number of fields when creating cars and manuals. And also because Car Builder and Car Manual Builder both implement the same iBuilder or builder interface, we can now use polymorphism to create cars and manuals, as producing a manual for a specific type of car, for example a sports car, requires the exact same steps. So for example, if a car has a GPS, then it also needs to be documented in the manual. So we can implement this using a director class, which I will show you next. So you can see here we still have the exact same builder pattern that we had beforehand. We can see we have the builder interface and then our concrete builders, which implement the builder interface. But we've now added this director class to our pattern. And you can see this director class has two methods here, one for constructing sports cars and one for constructing SUVs. And you can see that we pass the builder that we want to use into each of these methods. So for example, if we wanted to construct a sports car, this method would contain all of the steps in this sequence for producing a sports car. And if we wanted to produce a sports car, a sports car, then we would pass the car builder. If we wanted to produce a sports car manual, then we would pass the manual builder. And because the steps for producing a sports car and a sports car manual are the same, we can just pass the builder and it will construct the sports car or sports car manual correctly. And we could also do the same for different types of cars, different such as SUV or any other type of car. So we can see here that we have this dependency relationship between the director and the builder, and that's because we're passing the builder into as an argument into each of these methods. So the director class is actually optional in the builder pattern, as the build steps can be specified in the client, and that's what we did here. But it's often useful for putting common construction routines into this director class so that they can be easily reused throughout your application. So let's now take a look at the gang of four representation of the builder pattern. So you can see here we have our director class, which has methods that contain commonly used routines, and we can pass the builder that we want to use into each of these methods. We then have our builder interface with a reset method for resetting the object that we are constructing to a new object. And then we have our build steps. We then have our concrete builders, which implement the builder interface. And each concrete builder needs some sort of method for getting the result of the builder after the product has been built. So note that above we are passing a builder to each method in the director class, but it's also fine to store a reference to a builder and then use methods for changing the builder at runtime like so. So here you can see we have a different way of implementing the director class. So rather than passing the builder to each of the methods, we can actually pass the builder to the director's constructor when we are creating the director object. And then we provide a method for changing the builder. So for example, let's say we first of all want to build a sports car. We pass the car builder, then we call construct sports car. And then if we wanted to produce a sports car manual, we can call the change builder, pass the manual builder, and then construct the sports car again. And this time it will produce a sports car manual. So as you can see, both ways of implementing the director class are totally fine. I just wanted to show you a couple of different ways of implementing this class. So let's now build the director class in code. So let's create a new class called director. And we're going to give this class two methods, one for constructing a sports car and one for constructing an SUV. So first of all, let's create the construct sports car method. And we need to pass the builder to the method. And then we can call the builder, we can call all of the build steps on this builder. So what I'm going to do is I'm just going to copy them from our client code that we have here. And this needs to be builder. And we also need to import our components. Okay, so I think everything should be okay here. Okay, I'm just going to move this in a little bit. Okay, so that should be okay. So let's now also create a method for constructing an SUV. And again, we pass the builder. And then I'm just going to copy and paste this code in that I have here. So this time I've actually called the steps on the methods on the builder line by line. So just so you can see the difference between chaining the methods and sort of calling them one by one. So just two different ways to do it there. Personally, I like chaining. It's a little bit more convenient and we don't have to keep on writing the builder over and over again. But both ways of doing things are totally fine. So note that we don't actually return the product, so the product being either a car or a manual, from this director, from each method within this director. And that's because each product is returned from its respective concrete builder. And this is because car and manual objects don't share a common interface. So let's now go into the client and see how we can use the director class. So I think what I'm going to do is I'm going to comment out all of this code here. And let's first of all create our car builder. And then let's create our director class. And then let's create a sports car. So we can call director.construct sports car. And then we want to build a car. So we pass the car builder. And then we can say sports car is going to be equal to our car builder dot get sports car. Actually, sorry, it should just be get car. Okay, so then we have our sports car. And let's just check here. So that should be sports car. Then we can call sports car dot fuel and put it equal to 100. Okay, so that's pretty nice. So let's also now construct an SUV. So we can say director dot construct SUV, and we can pass the car builder, and then we can get our SUV. Let's say SUV car equals car builder dot get car. Okay, and then we can set the fuel to, let's see, dot fuel equals 40. Okay, so let's now produce some manuals for these cars. So we can first of all create a manual builder. And this should be car manual builder. And then we can call director.construct sports car. So just the same as we did here. But instead of passing the car builder, we now pass the manual builder so that we build a sports car manual. So then we can actually get our sports car manual. So we can say sports car manual is equal to manual builder.get manual. Okay, and then we can print the manual to the console. Okay, so you can see that VS Code is giving us no errors here, because here we are returning a car object which has a fuel property, and here we are returning a manual object which has this print method for printing out the manual. Okay, and we can also do the same for an SUV. So I'm just going to copy this in to save a little bit of time here. So you can see that we are also constructing a manual for SUV. So let's run this program to make sure everything is working correctly. So let's see what we have here. So we have, first of all, we have our sports car manual. So we can see the car type, sports, the seats, the diameter of the wheels, etc., which is all correct. And then we have our SUV with 5 seats, a slightly smaller diameter of wheel, etc., etc. So this is all working as it should be. So here we have used the builder pattern to reuse the same object construction code or build steps to build different kinds of products, so cars and their corresponding manuals. So other creational patterns focus on producing objects that share a common interface, but the builder pattern differs in that it can construct objects of different types, providing that they share a common set of build steps. Congratulations, you have now completed this design patterns course, and you now have all of the tools to create readable, maintainable, flexible and top quality software. So I hope you found this course useful, and I thank you for watching. If you did find this course useful, please do like, comment and subscribe to my channel. It will help a lot. Thank you very much, and I will see you in the next one.